Graphs are one of the most popular data structures that I personally struggled a lot with. So today I have decided to create an entire course on graphs. We will understand that what graphs are, when to use it, what are the different types, their applications, how to store them, and we will learn 22 most asked, most popular and most like lead code problems that has literally been asked at hundreds of companies thousands of times. So without any delay, let's get started with this course. Graphs are one of the most powerful tools we have in computing and also in real life to establish connections and define many of the relationships. We all have studied graphs in our schools and in our past careers. But now let's try to understand that what the graph is from the point of view of data structure and algorithms. So the idea is quite straightforward. Typically, a graph is defined by connection between more than one parties, and these parties are connected with each other in some sort of fashion. And this is an example of a graph that I just created. Now we can notice that graph contains two entities. There are these circular entities and there are these lines that are connecting them. And this is actually defined by nodes. So these circular entities are nodes, and they can also sometimes called vertices, so we can use vice versa. And the connection between these are defined as the edges. That's it. If you master nodes and edges, you basically master graph, but it's not as simple as it seems. Now let's say that I want to show you some practical examples of what a graph is in a real life scenario. Let's say that I want to explain that how does my Facebook or Instagram looks like in a picture or in a diagram. So how would I represent it? Well, one way to represent it is that this I can define it as my profile. So my name is Parth, so I'm defining it as P. And let's just say that I am currently friends with 5 different people on Facebook. So I can define these 5 people as dots and their own, and these edges define that I am currently friends with them and they are also currently friends with me. So that's why there are no arrows pointing towards each other. Now these friends can have their own friends, and it could be possible that I might have some mutual friends who are also friends with each other. So this creates a whole big new social network where everyone is connected with everyone and many people are not connected with everyone. Now in this example, let's say that I want to build a recommendation system, that I want to recommend new friends for myself because I currently only have 5 friends. So one logical way I can go about is that whoever are my friends or like immediate friends of my friends could also be potentially possible that they might be my friends as well. So I can start recommending these people to my profile who are not my friends but friends of my friends. But I would not recommend people like this who are friends of friends of friends of my friend. So that would be like 1 degree advance. And this is just one practical application. Now think the companies like Facebook, Twitter, TikTok, they all completely run on the concepts that are currently generated by graphs. So that's why they are so significantly important. Now when we talk about graphs, there are actually 4 different basic types that we can talk about. First one are the trees. And yes, trees are a different data structure on its own, but the thing is they are also a type of graph. The only difference between a graph and a tree is that trees are connected, which means every single value or every single node inside a tree is connected and they do not have any cycles. That's the only difference. Next type of graph that we can think about is that is typically a directed graph. So what does a directed graph means? Now let's try to understand this with an example of Twitter. There is a very famous profile for Eminem. Now Eminem has millions of followers. He has a lot of people following him, but Eminem does not follow anyone. So if I have to represent the graph of Eminem, I can define that currently Eminem, let's say I want to define whoever is following Eminem, I just mark their profile arrows pointing towards Eminem. So this defines that all of these people are currently following Eminem, but Eminem does not follow anyone. So there would not be any arrow pointing out where Eminem is following someone. So this is one way to define relationship where one party is connected with the other party but other party is not connected with the other party. Next is undirected. Now same way we can see the example of Facebook, where if I am friends with A, where A is friends with B, then B is also friends with A. So in this case we can say that there are actually two directed edges that are going or pointing towards each other. Or if I have to just mention it simply, I can just simply say that there are two nodes and they are just connected with each other where there is no direction specified. Then there are two more distinctions of graph, and for that is connected graph and unconnected graph. So what does a connected graph means? Well, as the name suggests, let's say that if there are all of these different nodes, and we can define that all of the nodes are connected with each other in some sort of edge, then we can define it as a connected graph. But if we have a graph like this where there are only three nodes, but this node is not connected with any other node and it's in a separate island in its own, still this is part of a graph. It can be possible on Facebook that I have created a profile where I don't have any friends and no one is friends with me. So I am still a profile, I'm still a node, but I just don't have any edges, and that is absolutely valid. Now, when we talk about traversing graph, we mainly talk about two methods, depth first search and breadth first search, and which is typically defined by DFS and BFS. Now, DFS simply means that let's say I'm currently located at this particular node. So from this node, I can see that I have edges pointing towards these five different nodes, which means from this node, if I have to travel, I can very easily traverse to all of these five nodes, and through these five nodes then I can traverse to subsequent nodes. Now if I follow the depth first search methodology, then the logic is going to be that I pick a neighbor, and for that neighbor I would keep on going subsequently down to its neighbor. Once again I would pick a neighbor, and then once again I would keep going down towards that path. Now let's say that I exhausted all the possibilities and I reached out to this neighbor where it currently does not have any more neighbors that I can visit. In this case, I can do a backtracking operation. I can check that whether there is any other node whose neighbors I haven't visited. In this case, once again, this does not have any neighbors. So once again, I would do a backtrack operation. Once again, this does not have any more neighbors. And once again, I would do the backtrack operation to my root node from where I started and repeat the same operation in the other direction as well, and so on and so forth. So I'm going down in a particular direction in depth first search manner. Second option to traverse is that instead of traversing in depth, I can start traversing in breadth. So what does that mean? Well, for any particular node, I will visit all the nodes that are currently associated with that particular node or all the neighbors, and then I would start visiting subsequent neighbors. So let's say that once again I start to traverse from this end and I want to traverse in a breadth first search fashion. So first I would visit this node, then I would visit this node. Now notice that this node has some children of its own, but I'm not going to visit those. I'm going to visit all the neighbors of this node first. After visiting that, now I would pick on this node and once again start visiting its neighbors. So let's say that this node, and if let's say that this node also had these two neighbors. So once again I would visit this node, then I would visit this node and this node, and after visiting all of the children, then I will start visiting these nodes. So in one fashion you are moving out in breadth, and in other fashion you are going in one particular direction in depth till you reach to the end of the path, and then you do the backtrack operation. So this is just couple of ways to understand or traverse over the graph. Now one last thing, and that is that if I have to define that what are the different ways to represent a graph, then there are actually couple of ways. First way is, let's say that let me just draw a quick graph. So one way is to define them using adjacency list. What adjacency list means is that I typically use a hash map like data structure where I say that all of these nodes, so 1 2 3 4 and 5, all of these nodes I am defining. And now for these nodes I can define in these values that what are the neighboring nodes of that. So for 1 I can define the neighboring nodes are going to be 2 and 3. Now for 2 I can define the neighboring node to 1, because remember this is an undirected edge, so which means 1 is neighbor of 2 and 2 is also neighbor of 1. So once again for 2 I only have one neighbor, that is 1. For 3 I only have one neighbor, that is 1. For 4 I only have one neighbor, that is 1, and I did not define 4 over here but 4 over here as well. And for 5 I only have one neighbor, that is 4. And this would be a representation of this graph in adjacency list manner, where we are clearly defining what the nodes are and what are all the different neighbors connected with each. And the second way to represent the graph would be using adjacency matrix, And in the adjacency matrix, we are simply defining all the nodes that we currently have, and then whenever we see an edge between them, so let's say that we currently have an edge from 1 to 4 and 4 to 1, so from 1 to 4 we can mark as true or 1, and same way for 4 to 1 we can mark it as true or 1, and for all the other values we can define it as 0 or false, something like this. So this would be two different ways that we are going to represent graph inside our computer programming, and both of them are very useful and very popular. Just a quick suggestion when to use which one. If you are dealing with less edges, then it would make sense to use adjacency list, because you are only dealing with small number of connections. But if you are dealing with lot of edges and lot of dense graph, then it would make sense to use adjacency matrix, because remember over here the retrieval would be big O of one time, because you can directly see that whether two nodes are edges of each other or not. In this case, in the worst case scenario, this can be big O of n, because notice that over here we are facing some contention, so that's why it would make sense. But the thing is, the time complexity for space complexity for this one is big O of n square, that is more expensive, and for adjacency list it is much less expensive. So I explained, I gave you a brief intro. Now let's try to learn the 22 most asked, most popular, most like LeetCode problems. And by the end of these 22, after completing these 22 questions, you would be pro in all sorts of graph questions. That is my guarantee. So without any delay, let's get started. So the LeetCode problem we are going to solve now is called maximum area of islands, and we can see that this one is a medium problem and also a very well liked problem. The statement is quite straightforward. We are given an m cross n binary matrix named grid. Now for this particular grid, we are given bunch of different ones and bunch of different zeros. Now we are being told that ones represents an island and 0 represents just water. Okay, then we need to return the maximum area of an island that we can make inside the grid, and if there are no islands that we can form, we need to return 0. Plus we are being told that every single cell with value 1 is the island, and if there are bunch of different ones connected with each other, then we need to basically do the addition of all of those cells, and then we can consider them as one entire block of an island. So let's try to understand this with an example. Here is an m cross n grid we are given, and we can see that there are bunch of different zeros and bunch of different ones. Now some ones are isolated, so this is just an island in its own, and we can see that the area of this particular island is going to be value number 1, because it is only connected with just one island by itself. But if we take a look at some other islands, we can see that they actually form bunch of different ones that are adjacent to each other amongst all 4 horizontal values, and that increases the area of those particular islands. So we will have this island that is of size 4, same way this island of size 5, and so on and so forth. Now we need to return the island that contains the maximum value. So in this case, this island chain or this connection of ones are actually total area of 6. So in this case, we will need to return the maximum area of islands as 6 as the answer. So this is what we need to return. Now let's try to understand that what are the different logic we can take to solve this problem. Now we know it's a very straightforward problem. The idea is that we are going to iterate in one single direction from the starting point, and the moment we identify that there exists some island or value number 1, then we need to iterate over every single possible neighbor of this particular one. And the moment we exhaust all the possibilities by exploring every single neighbor, we can determine that that has been the current area that we have been able to find. Plus we will also need to keep track that what is the maximum island chain we have been able to identify it so far. So let's try to understand the most common basic approach to solve this problem. Let's say that we start iterating from this very first cell in sequence, in just regular sequence. So we say that this is water, this is water. So there is no area we can find. We come to this node. This value is 1. So the moment we identify 1, we will have to take a look in all 4 directions to see if there are any possible island chains that we can make. since in this case there are no island chains we can form, we can say that the area of the current value we have been able to identify so far is 1, and so far we have only found one island with area 1, so the maximum area we found so far is also 1. After doing this, we will have to mark this one as being visited because we have already visited this node. And why are we marking it visited? I'll just explain it to you later. So let's say that we mark this one as visited as well. Okay, that this one has already been taken care of. We iterate again, nothing, we don't find anything. Once again we find one more one over here, which means we will have to do the iteration for our current updation right now. So once again we start looking in all 4 directions. The moment we go to this direction, we find one more one. So once again for this particular one, we will have to repeat the same operation, look in all 4 directions. And here the problem may arise. Let's say that we look in this direction and this direction, and then we decide to look up into this direction. So this is also a neighbor of 1, and we can also by mistakenly calculate this one once again, so as part of the island, which means we may stay inside an infinite loop. And that's why, in order to prevent that issue, the moment any particular value that we have visited, we are just going to mark that that value has been visited, so we don't recount those values again. So let's say that we count this value, then we go into this direction, and so far we have visited all of these 4 ones, and the current area so far we found is 4, which means maximum area also needs to be updated. So we are going to update the maximum area once again. Now we start our iteration in the similar fashion. These are all zeros, so nothing to do with this. Once again, this one would have been 1, but since we already visited this one, there is no point in redoing the same operation. So we are just going to go and ignore this case completely, and once again we are going to ignore all of these cases. Once again we identified 1 1, so far the area is going to be 4. We cancel out all of these 4 nodes as well, and we keep on repeating the same operation until we find the maximum area, which we would find when we get to this particular one as value number 6. And this is what we need to return in this case. So the moment I was explaining this solution, it should completely come to your head that this is actually a graph problem, where this given m cross n grid is actually the matrix we are given that represents a graph. It's an adjacency matrix. And for this adjacency matrix, all we need to do is we will have to find that what are all the connected components for any particular graph, and the cluster of the connected components, whichever has the highest value, we simply need to return that as part of the answer or as part of the area we have been able to calculate so far. Now we know with any particular graph problem, the most important thing is that how we are going to iterate over the graph. So we know that iterating over an m cross n grid is quite straightforward. We simply need to run 2 for loops to iterate over that. The moment we identify any particular one, then we will have to explore in all 4 directions and iterate over the entire set of directions where whichever the value is 1, and we will have to keep on repeating the same operation. So logically, all we are doing is a depth first search whenever we identify any particular one that exists. We can also do a BFS, but DFS in my opinion would make much more sense in this case because we need to go in any particular direction. It won't change the result, but I just like to use DFS for this particular type of case. Then in order to complete the DFS and not run into the issue of recounting the same value, we will have to keep track of all the visited nodes. For that, we have 2 options. One option is that we can try to manipulate the existing input, but let's say that your interviewer is very picky and he or she does not want you to play around with originally given input. So instead of playing around with originally given input, you can also create a m cross n matrix and just mark all the values by 0, whichever the ones that you have visited so far. So that way also you can just keep track of all the nodes that you have visited, and you are only going to do a DFS on unvisited nodes. So that's it. That is the whole solution. And on top of it, for the entire duration, you are going to keep track of the current area that you have found so far and the maximum area that you have been able to find so far. and combination of this would actually solve this problem quite simply, quite easily. Let's try to understand the time and space complexity in this case. Time complexity is simply going to be big O of m cross n, because we will have to iterate over every single cell, and even for our DFS operation we are going to mark those nodes as visited. In terms of space complexity, because we are using an extra space to store all the visited nodes, it is also going to be big O of m multiplied by n, or nodes multiplied by edges. So in this case, overall this is a very good time and space complexity. Once you understand that this one is actually a graph problem, it becomes very simple to solve and also move forward. So now let's quickly see the coding solution for this one. So the coding solution is quite straightforward. We are given our max area of island that we need to find, and we are given the grid as part of the input. First thing we are going to do is to check that if the given grid is equal to null, then we are simply going to return 0. It's an edge case. Then we are going to initialize a variable called max area, and initially the value is going to be 0. Then we are going to iterate over every single value that is currently present inside our grid using two loops, I and j. And for every single value, first thing we are going to check is that if the given grid position, if that is equal to 1, then we will start calculating the area of this current one that we have been able to identify so far, and we will have to iterate over in all four directions, and that's where we are using the DFS method. Next thing, for every single one that we have been able to identify so far, it could be possible that that particular value could be the maximum area we have been able to identify so far. So we are going to compare the maximum area we have so far and the new area or the current area we just found for this particular through this DFS call. Now let's understand this DFS call and how does it work. In the input, we are providing the grid that we are working with. We are also providing the current I and jth position. Very first thing we are checking is that if the given grid is going out of bounds, in either one of these cases, we are simply going to return 0, or if the given grid position I and j that we are working with, if that is also 0, then also we can return 0. If that is not the case, we are going to mark this cell as visited. Now in this case, I'm not using an extra hash set. I'm just using the same grid to update the call. But if your interviewer asks you that you cannot change the given input, then you might need to create a new instance of new m cross n matrix and repeat the same operation. Then we are going to add value of area by 1, and then we are going to make 4 different calls in all 4 directions, and we are going to do the plus and equal to operation for the area, which means for every single one that we are being able to identify in each of these 4 areas, we are going to add that value to our existing area, and we are simply returning the area in the end. So this is our helper method, where recursively we are using the DFS operation and we are updating the area of the current area we have been able to identify it so far. In the end, we simply need to return the max area we have been able to identify so far once this for loop call ends. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions, which is exceptionally good. So once again, the solution is present in our GitHub repository, so feel free to go ahead and check it out. Thank you. So the LeetCode problem we are going to solve now is called network delay time. This is a pretty popular LeetCode problem. So let's understand the statement. Basically, we are given a network of n nodes marked from 1 to n. So in total, we are given 3 items. First one is times, that defines that in order to reach from one particular node to next node, how much time it takes. So if we take a look at this example, let's say 2, 1, 1, then we can say that in order for us to reach from node number 2 to node number 1, it is going to take 1 unit of time. So this is how bunch of different times we are given. Then we are given told k as a starting point, and that says that we will have to start iterating over our journey from k is equal to 2. So in this case, from second node, and this n defines the total number of nodes that we currently have. Now the problem is asking us to solve is that we need to return the minimum time it takes for us to travel all the n nodes to receive the signal. And if it is not possible for all the n nodes to receive the signal, then we need to return -1. So let's try to understand this with an example. Say for an example, in this case, we are given an input like this. So we can see that in total, we are dealing with 4 different nodes and we are given 3 different edges. So first edge is from node 2 to node number 1, it takes 1 time. Same way from node 2 to node number 3, it takes 1 time. And same way from node number 3 to node number 4, it takes 1 time in order for us to reach. Now we are given k is equal to 2, which means starting from k, we will have to make sure that are we able to send a signal that reach every single node and what time it takes for to reach all the nodes in the minimum. So during the very first minute, we will have a signal that can go to node number 1 and node number 3. So we can say that these two nodes would have been visited after 1 minute. And then from node number 3, we still have to visit node number 4. So we can say that in order to reach node number 4, it is going to take 1 more minute, which means it took 1 minute to reach over node number 3 and then 1 more minute to reach to node number 4. So in total, it took us 2 minutes to reach to node number 4 and 1 minute to reach to node number 1 and 3. So in the minimum time 2, we can reach or a signal can reach every single node starting from node number 2. So this is what the problem statement is asking us to return. Let's say in this case, instead of 2, if we are being told that our k starting value is at 3. So in this case, now we are starting our iteration from value number 3. So once again, we will have to check that how many nodes can we reach. So we know that in the k3 only points to one node. So during the first minute, we would visit node number 4. But the thing is, we don't have any way for the signal to visit to node number 2 and node number 1. So in this case, we will have to return -1. So this is the whole problem statement. Now let's say that this is the input we are currently given and we are trying to deal with that how we can actually find the network delay time starting from any particular node. The thing is, we don't know that what node we are going to be starting our code with, but all we have is the information about the total number of nodes that are currently present and the distance it takes in order to reach from one particular node to other particular node. The logic is quite straightforward. We treat this one as a classical graph problem where starting from any particular node, we will try to see that if there exists a shortest distance that can cover all the nodes that are currently present. If we are able to reach to all the nodes, then we will have to check that which is the farthest node and how much time it took us to reach to that particular level. Let's try to understand this with this example that we were starting our node at node number 2 and it took us 2 minutes to reach to node number 1. Then the amount of time it takes to reach to this node number 3 and node number 1 is obsolete because we are only concerned about the minimum time it takes to reach to every single node, and that should be our key focus. So few assumptions we can make is that number 1, we can use this as a graph problem. This one is going to be the Dijkstra's problem that in order to reach us to the shortest minimum span, and I don't know the spelling of Dijkstra, so sorry about that, and no worry. Now coming back to the question, basically we need to, number one thing is have a graph like structure. So what I'm suggesting is we create some sort of an adjacency list or adjacency matrix kind of a structure. So let's say that we do create an adjacency matrix or hash map that contains all the information related to nodes and what are all the different distances that we can travel from those nodes. Now we all know that what are the different edges it takes us from any particular node that we can iterate over. So because we are given the information in this fashion like x, y and t, where x and y are the nodes and t is the amount of time it takes to reach there. So we can just simply take this x, put it in the node section. So this would be the key for us to search inside our hash map, and this y and t defines that in order to, let's say that in order for from x, we can have an information like this one, that y and 1. So we can say that the node is x. If we have to reach to y, it takes us 1 time. So let's try to build a graph like that for all the nodes that are currently present in this case But the thing is, we are also going to do one thing smarter, and that is that instead of just pointing out the nearest neighbor any particular node can visit, we will also try to sort these values based on the shortest value first and the longest value later. Why are we doing that? Because we are trying to, we have two objectives. Number one objective is to reach to all the nodes, and second objective is to do it in the minimum time. So we will have to find the quickest route possible. Next objective is that we will have to iterate over all the nodes that are currently present. So we are going to fulfill all of these goals by making some adjustments in the way we do our calculation. So for that, first let me just set up the graph structure that I'm suggesting, and then we will start tackling over the other problems. Now in this case, we are only dealing with 4 nodes. So starting with node number 2, we have two options. If we have to reach to node number 3, it takes us 2 times. So it makes sense that this is the shortest distance. So we can mark the values as, in order to reach to node number 3, it takes 2 times, and in order to reach to node number 1, it takes 3 times. So we are going to mark things like this. Same way, starting at node number 3, once again we have two options. In order to reach to node number 4, it takes us 3 times, and same way, in order to reach to node number 1, it takes us 6 times. Same way, from node number 1 we only have one option, and that is, in order to reach to node number 1, it takes 5 times, and from node number 1 we don't have any option. So at the node number 1, we basically just don't have any edges that are going out, so we will not mark anything. Now we knew that these are the 4 edges that we will have to traverse over. Next thing is that we also need to keep track that what are the nodes that we have visited so far. And also the other thing is, we need to know that is the node visited if that is the shortest distance that we found so far. Now in order to tackle both of this problem, what I'm suggesting is we create a new array that is of size n. So we will have values like this one, like 0, 1, 2, 3 and 4. But the thing is, in this case we are only dealing with nodes starting from 1 to n, so not from 0 to n. So the thing is, for the very first value inside the array, we are just going to ignore this one. Okay, so let's say that we ignore this, and initially we will set this array up to a very large value. So let's say that we are populating the entire array with the maximum value possible, and then the only time we will update this array is, number one, if we find out a path to reach to that particular node by some smaller value, and number two, if we cannot find that, in the end it would be able to show us that there are some nodes we are not able to reach, so we can just return -1 in those cases. So let's try to start iterating over our solution now. It would make much more sense. Let's say that in this case our given k is equal to 2. We are starting our iteration from node number 2. So what is the minimum time it would take us to reach to all the nodes? Now from at node number 2, we can see that the very first possibility is that if we have to reach to node number 3, then we will have to do, we can do it in 2 times. Currently node number 3 has not been visited. So we found a shorter way to visit node number 3. So we will mark it by 2. And then same way we are going to ignore or pop this case out from our given list. Basically we are dealing with a priority queue or a hash map like a structure. So inside the hash map we will add the value number 3, but we will pop out this value from the priority queue. Now from this node number 3, once again we are going to repeat the same process. And by the way, currently inside the priority queue we only have these two values present. So first value was 3 2, and second value was 1 3. Now we add one more value, that is the value 4 3. So now notice that we popped one value out, and we have two more values that we will have to deal with. Okay, and we would keep on iterating in terms of priority queue, and we would always try to find the shortest distance that we will try to kick out. In this case both values are 3. So let's say that we decide to update node number 1 first. So node number, in order to reach to node number 1, we can do it in 3 times. So let's mark this one. Now once again at node number 1 we don't have anything, so we cannot add anything to our priority queue. Then we are located at our node number 4. So sorry, node number 3. So at node number 3 we added one value, that is 4 3, and we also have to add one more value, that is 1 and 6. So for the 4 3, currently 4 has not been visited, so we would mark value number. In this case, we would not mark value number 3. Why? Because in order to reach to node number 3, it took us 2 times. So we will have to do the sum with 2. So in order to reach to node number 4, it is actually going to take us 5 times. So we are going to mark 4 and 5. And same way, if we have to follow this path and reach to node number 1, then it would have taken us 8 times. So we are going to mark this as 1 and 8 inside our priority queue. And this is the important step where we are updating the total number it takes in order to reach to that particular node based on the previous value we had for in order to reach to that node. So in this case, once again, the node for 4 has not been visited, so we will update it by value number 5. But notice that this 1 8 does not need to be updated, because we already know that we can reach to 1 in 3 times. Then why would we choose a path that reaches 1 in 8 times? So we will ignore this one. And then now we are at value number 4. So from 4 we have one more path then we can go in order to reach to node number 1, and this takes 5 times. So if we choose that, then it becomes 5 plus 5, so 10. But the thing is, we still don't need to update because we already have value number 3. Now the thing is, because we are starting from k is equal to 2, which means from k is equal to 2, in order to reach to k is equal to 2, it is only going to take 0 time. So we should have updated this at the beginning. So I forgot to update, but let me just do it right now, that in order to reach to k is equal to 2, we can do it in 0 times. And now we can see that we are done with our entire iteration. Our priority queue has to be empty because we took care of all the nodes, and we are left with this array. Now in this array, all we need to do is we need to iterate over all the nodes. Ignore the first node because we are only concerned with between 1 to n nodes. Check that if we found at any particular moment any value that was the original max value that we started with. If that is the case, then we can simply return -1, saying that there were few nodes that we were not able to reach. If we don't find any value with -1, we are going to find that what is the maximum value we have in this current array, and currently the maximum value is 5. So we can say that 5 is the minimum number of time it takes for a signal to reach to every single node starting from k nodes, and this is what we can return. So this is a beautiful solution. It has a lot of practical application like aviation industry, network routing industry. All the things use methods like this in order to compute that what is the shortest distance to travel from one point of the plane to the other point of the plane, which is pretty awesome and pretty nice. Now let's try to understand the time complexity. Now it makes sense that we will have to do big O of n multiplied by v work for every single node, and at every single node we will have to check that what is the shortest distance. For that we will have to add those entries inside our priority queue. So it is going to be multiplied by logarithm of n, and this is a pretty decent solution where n is the total number of nodes and v is the total number of vertices. And sorry, not vertices, but this should have been edges, so n multiplied by e. If we look at the space complexity, well, we are using quite number of additional data structures. We are using a graph like data structure to store all the values. We are using a priority queue. We are using bunch of different pointers and stuff like that. So overall, the biggest one is the graph like structure, that is big O of once again vertices multiplied by edges. So this is going to be the space complexity that we would be dealing with. So now let's quickly see the coding solution for this one. So the very first thing we are going to do is that we are going to create a graph-like representation using an adjacency list. And for that we are using a hash map to store the nodes as integers and its subsequent edges as the linked list type of structure. We are simply iterating over every single edges. We are marking the very first node that we currently have as part of a key, and then the second value and the third value is being represented as the edge and the time it takes to reach to that particular level. Then we are initializing a new priority queue where this is going to be a min heap, and we are going to be checking that what is the minimum amount of time it takes to reach to any particular node. Then we are going to be adding the very first value as saying that in order to reach to node k, it takes 0 amount of time, and this would be the starting point for our min heap or priority queue. Next thing is that we will have to initialize the distances of an array with the starting value as maximum value. So we create a new array starting with n plus 1 nodes, plus we fill out all the values that we currently have with the maximum value possible, and the value at the kth position, in order to reach to kth distance, we mark it as 0 because it takes 0 amount of time to reach to node number k. Now then our priority queue iteration starts, that while the priority queue is not empty, number one thing we are going to do is pop out the very first element that is present inside the priority queue, mark the current node with the very first value inside the priority queue and the current distance in order to reach to that node as the second node of the tuple. Then we are checking that if the current distance is greater than the current distances that we have already found, then which means we can simply ignore that case and we don't need to do anything with that particular node. But if we don't have calculated or we found some value that is smaller, then we are going to check that what are all the neighbors for that particular node, and we are going to be marking all of those neighbors in our graph like data structure and adding those to the priority queue. On top of it, we are going to be updating the distance that we need to calculate by adding the current distance plus the new distance that we found in order to reach to that particular neighbor. So this way we are continuously updating all the values we can inside our array. Lastly, all we need to check is that inside the new maximum distance array that we have created, that we need to check that in the given array what is the maximum value we currently have. Notice we are skipping the very first element inside the node because we are starting from n is equal to 1 index, not 0th index. And then we can simply check that if we found that the maximum distance to be the maximum value possible, then we need to return -1. If that is not the case, then we simply return whatever the maximum distance we found inside the array. So let's try to run this code. Hopefully it should be working. Seems like our solution is working as expected. Let's submit this code. And our code beats almost 70% of all the other solutions, which is pretty great and pretty awesome. So once again, you can find the coding solution for this problem in our GitHub repository. Link is in the description. Take care. Hello friends, hope you are having a fantastic day. So now we are going to do an awesome LeetCode problem called rotting oranges. We can see that this one is a medium problem and also an extremely well-liked problem. The statement is quite straightforward. We are given an m cross n grid where each cell have one of these three values. First value is 0, that represents that there is an empty cell, which means there are no values over here. Second potential value can be 1, which represents that there exists a fresh orange on that particular cell in the m cross n grid. And next value is 2, which represents that there could be a rotten orange or a bad orange placed in that particular cell. Now there comes the interesting part, that with every single minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. So after every single minute iteration, we will start finding more and more rotten oranges, and they would keep on growing. Now we need to return the minimum number of minutes that must elapse until no cell has fresh oranges. That is number one thing that we are being asked. If that is the case, we need to return the minimum number of minutes. And if it is impossible to rotten every single oranges, then we need to return -1 as part of the answer. So let's try to understand this awesome LeetCode problem. Okay, so suppose this is one of the example input that we are given. Now notice that the values are 2, 1 and 0 given in different sections of this 3x3 cell. Now we know that value number 2 refers to a bad orange, so I have denoted that as like B over here in this grid, and 1 refers as normal orange, so I have just marked O or like 0, that represents a fresh orange. Okay, don't confuse this with like value 0, because value 0 I have left it as empty because there are no oranges or nothing on that particular place. So now let's focus on our input. Now the way we are given this problem, this is a bad orange. Now let's say that this is the current starting position, so at minute number 0, this is currently what is happening right now. But we know that after every single minute, all the oranges that are adjacent in 4 direction to this bad orange will start getting bad. So after 1 minute passes, we are going to have 2 more oranges that have gone bad, and that are these two oranges. So we can mark them as bad oranges, and all the other oranges that we have are going to remain as it is. This happens during the first minute. During the second minute, once again more oranges are going to get bad. So since this orange is right adjacent to this one, this will go bad, and this orange will go bad in the next minute. So these two oranges will go bad. So if we mark the number of bad oranges, it is going to keep on increasing in this fashion, and now we are only left with two fresh oranges. And during the third minute, basically we are also going to have this orange go bad, because notice that this is directly adjacent to this orange. So during the third minute, this orange will also go bad, and all the other oranges we already have, they are bad. And during the fourth minute, basically because in the third minute this orange is fresh, but during the fourth minute this orange will also go bad, and now we don't have any fresh oranges. So we can say that after 4 minutes, basically every single oranges that could go bad, they have all gone bad. So in this case we need to return 4 as the answer. Now let's say for the same example, we are basically given one more scenario. Let's see that what would happen in this case. Well, we know that during the first minute the adjacent orange is going to get bad. So now we are going to be left with 2 bad oranges and few other good oranges. During the next iteration, once again the same thing is going to happen, and now in this next iteration, basically this orange is going to go bad. So then we are going to be left with these 3 bad oranges and then these 3 good oranges. During the next minute, once again same thing is going to happen, and basically we are going to be left with this orange as becoming bad orange as well, and all the other oranges would remain good. And during the next iteration, basically this orange will also go bad. But notice one thing, that despite every single orange being bad, we do not have any particular way for this particular orange to go bad, which means no matter how many iterations we take, even if all the oranges went bad, this orange will still remain fresh. So in this case, because we cannot have every single orange becoming rotten, we need to return -1 as the answer. So this is what is being asked us to solve in this problem. Now I know this problem looks really interesting and really important in terms of many different aspects. So first let's try to start breaking the problem down and start understanding different things on what we can do to solve this problem. Let's say that in this problem we are given oranges like this and all the other cells are simply empty. Logically, what is the most simple thing we are going to do? Well, we need this is the initial position, so we are going to have a value called minute, and in this particular minute we are going to mark that all the minutes that has elapsed so far. So during the 0th minute, this is the position. So during the first minute, what is going to happen? We are going to start noticing that this orange will go bad. Okay, then during the second minute, this orange will go bad. During the third minute, this orange, and during the fourth minute, this orange will go bad. So this case, it's going to take 4 minutes for every single orange to get rotten. So the thing is, we can visualize it very quickly and very easily, but how can we implement this programmatically? So that's where few important concepts come into the place that let me start describing. Number one concept is that basically for every single position we will have to understand that what is the rotten or bad orange, and then we will have to start iterating from that particular element. So far we were lucky that the very first element was actually a rotten element, but let's say in the same scenario, instead of this being rotten, what if this was a rotten orange? Once again the answer would still be 4 minutes, but in this case we would have iterated over all of these cells before finding this rotten cell, before we start branching out. So that is number one thing, that we need to first of all find that what is a rotten orange. Okay, that is number one thing. Next thing is, the moment we find the rotten orange, what we do is we start branching out. But the question is, are we branching out in the depth first manner or a breadth first manner? Well, logically in this case we are actually iterating in the breadth first search manner, because for every single node that we iterate over, we try to iterate all of its neighbors before visiting before visiting their neighbors. And let me give you a very simple example for that. Let's say in this example, During the very first iteration, we simply visit this neighbor. Okay, so we are going to mark this as a bad orange. But in the next iteration, rather than going in one particular direction, we are going to branching out in two directions and marking both of these as bad apples. And then after exhausting all the neighbors of this particular orange, then only we will start exploring more neighbors of these remaining oranges. So this is also another important point to be understood. Okay, that we will actually have to use breadth first search in this case to solve this problem. Okay, we took care of two items. Now let's try to understand that how we are going to keep track of the number of minutes. Well, logically the answer is quite straightforward, that whenever we have to make any single new BFS call, we are going to keep track or keep incrementing the number of minutes that we will have to make. So this would be our minute counter that we are always going to update with every single new BFS call we make. Now we know that in order to use a breadth first search, we will have to use a queue, and logic is quite straightforward, that first of all we are going to iterate over all the oranges that we are given and try to find all the bad oranges we have. In this case we only have one bad orange, but it could be possible that we may be given multiple bad oranges. So let's say that we are only given just one bad orange, so we are going to put this bad orange in the queue, and with every single iteration we are going to branch out in all four directions from this bad orange. The moment we identified a good orange, we are going to mark that also as a bad orange and push it down the queue in order to be processed in the next iteration, and that next iteration will happen in the during the next minute. So this is the second important logic that we will have to understand, that how we are going to be processing the queue. Now comes the interesting question, that how would we know that we have actually isolated or completed every single oranges that we could, and whether we need to return the minutes or do we need to return -1. So for that, during the first time when we are actually iterating over to find all the bad oranges and pushing them on the queue, at the same time we are also going to have a counter that stores the number of good oranges we have. And what we are going to doing is that, let's say in this case we realize that we have 4 good oranges. Now every single time we add one value to the B, we are going to reduce one element from the good oranges. We are going to be doing the breadth first search as long as we are able to reach some oranges, and then once we get out of our loop, we will try to check that, hey, uh, do we still have any more good oranges. So in this case we would not have any good oranges, so we can simply say that we did not find any good oranges, so we can return the minutes. If we do find some good oranges, then we need to return -1. That's it. This is the whole problem and this is the whole solution. Now I know that we can use queue plus we can use recursion to complete the BFS call. Also for this given m cross n grid, we are actually treating it as an adjacency matrix for our graph kind of problem, and every single node we are treating it, every single node that contains the value of either a bad orange or an orange as a node, and connection or the neighbors of each other are being treated as sort of like edge between them. If we see time and space complexity, in this case time complexity is going to be simply big O of V multiplied by E, vertices multiplied by edges. And for the space complexity, well, since we are not using much space except storing a queue, the space complexity would be directly dependent on the number of bad oranges or number of total oranges present, because in the worst case we might have all the oranges that might go rotten. So this is the whole time and space complexity. Now let's quickly see the coding solution, so my solution would make much more sense over there. So the very first thing we are doing is to check that if the given grid is equal to null, we can simply return -1. If that is not the case, we are going to define the values of m and end. Then we are going to initialize a count called fresh count. This is to store the fresh oranges that we have at the beginning of the queue. And then we are going to start our queue where we are going to be storing all the rotten oranges that we found so far. Now the first thing is count the fresh oranges, and we are also going to push down all the rotten oranges down to this queue. So we simply use two for loops to iterate over all the values, and we are going to be counting that what are all the fresh oranges we found. And if we identified that the value is 2, which means that particular cell position is a position of a rotten orange. Okay, so now that's good. Now the very first thing we are going to check is for the edge case, that if there are no fresh oranges, we can simply return 0, that during the 0th minute all the oranges are rotten. If that is not the case, we are going to initialize a variable called minutes with the starting position 0, and we are going to have direction array to iterate over all 4 neighboring directions for any particular cell. So these are nothing special, just the 0 and 1 combinations of adjacent cells, and that we can simply add to the current I and j positions. Now we start our BFS operation, where we first check that if the given queue, we are going to iterate until the given queue is not empty. First thing we are going to check is the size of the given queue. Then we are going to check that for any particular given I position, while it is less than the size of the queue, we are going to first of all pop one element out, marking it as rotten, and then we are going to be iterating in all 4 directions. So notice that with the by using the direction variable, we are actually going to calculate the x and y positions of all the adjacent cells. Then we check that are we going out of bounds. If we are not going out of bounds, then we are going to be turning the fresh oranges into the rotten, and we are going to be reducing the count of the fresh oranges that we found so far. On top of it, we are also going to be updating the rotten queue and adding those values inside our queue as well. Lastly, we are going to be updating the minute variable for every single new breadth first search operation that we make, because this is the increment timer for every single level of BFS. Now in the end, we simply have to check that if the given fresh count is equal to 0, we are going to return minutes. If that is not the case, we are going to be returning -1. That's it. Now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs extremely fast, and it beats 99.99% of every single solution, which is pretty great, pretty awesome. Once again, you can see the coding solution on our GitHub repository, so feel free to go ahead and check it out. Thank you. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Graph problems have always been a big no-no for me. I have always been afraid of graph problems, but the thing is now I have decided to take them heads on, and today we are going to start doing more graph videos. So this is the first of many graph problems to come. And this question has been really popular with Facebook recently. It's been asked 44 times, which is a huge number. Also, key other companies like Amazon, Google, Bloomberg, Microsoft, Twitter, they are also asking this question. But the thing is, Facebook for some reason has been really interested. So I highly urge you to go and check this video if Facebook is one of your dream companies to join. Okay, this is a LeetCode medium problem, and we are given a reference node in a connected undirected graph. So first let's understand the meaning of these two values. Suppose we are given a graph like this. Notice that there are only 4 nodes, and from any single node we can reach to all the other nodes in the given graph, which means that this is a connected graph. So this is what connected means. And undirected graph means, suppose we are given a graph like this, and we establish that A is B's neighbor, which means that we can traverse from A to B, and also we can traverse from B to A. So there is no restriction regarding the direction of any edge between 2 nodes. So we are given a reference point to that, and we need to return a deep copy of the graph. So what does a deep copy of the graph means? That suppose we are given a graph like this, so we need to return a graph like this, where if you see the values of the nodes, they are all the same. But the thing is, we are not using the exact same nodes. We are using different nodes with same node values, which means that this would be a legitimate case where we can consider this as a deep copy of this original input. The thing is, if we create a graph like this, over here we are using the same node to represent over here. which means that we are not creating a copy of this original graph. We are just referencing this point to whatever value we had over here. So this is not what we want to give. And also if we create some graph like this, if we see the values of the nodes, the values remains the same. But the thing is, the ordering is different, that in terms of neighbor selection and how they are perceived, they are different. So this is also a false case. We need to return a copy of this exact same input, just with the nodes that are copied from this one. So at the beginning, the most basic idea we are going to have is that, okay, we are given an input, we are given a reference point, we know that the input graph is connected, which means that there are no loose ends that we have to worry about. So why don't we just traverse through the given input graph? At every single node, we start creating a copy of it. We start creating the same sort of neighbor connections that we have in the original graph, and then just try to return the new graph. That would be a perfectly good logical rational person would think, and that would be a good entry point to start our solution. But the thing is, we are going to see that with that approach, what would be the issue, how can we remediate that issue, and what would be the final solution. So let's start. So first of all, suppose in this given input we start at this one position, so we create a new node 1. Okay, now from this one we can go to any neighbor, we can go to 2 or we can go to 4. Let's say that we go clockwise, so we go to 2. So we create a new neighbor over here called 2. Again from this 2 we go to 3, and over here, keeping the same logic, we create a new node. Now notice one thing, that initially we created a clone over here, we went to its neighbor. Again we created a clone over here, we went to its neighbor. Again we created a clone over here, we will go to its neighbor. So basically we are doing the same problem again and again for different kinds of input. So that should immediately click in your mind that this we are going to solve recursively. So just keep this in mind, that this is a very good way to use the recursive approach. And now at this 3, again we go to its neighbor. So we'll create an edge and we'll create a new node 4 for this one. So from this 4, again we go to its neighbor. Again we go over here. But the issue with this approach is that for this our recursion to end, we need to have a terminating case. But in this scenario, we are not terminating it anyhow, because the thing is, the graph is connected. We are terminating in a scenario where if the graph is empty, we return something empty or something like that. But the thing is, over here again, when we come back to this 1, we are still going to see that, okay, this is 1. We need to create the clone of it. We will create a clone of it again over here, which means that we are going to overwrite whatever value we have, which would be the same value. Again we would go to 2, we would again create another clone, again we would go to 3, again we would create another clone, again 4, again another clone. So basically we are going to end up inside the loop again and again infinitely. This is almost like Infinity War. Thanos is gonna snap his fingers, something like that, because we are completely destroying our computers resources, our company's resources, because it's an infinite loop. It's never gonna stop. So, and the reason it's never gonna stop is because we are doing the repetitive work again and again and again, and that is the issue. So somehow we need to resolve the issue. So how we are going to resolve the issue? Well, basically the idea is simple. If at any point, suppose we create an additional data structure, in that additional data structure we keep track of whatever the value we have traversed already or we have cloned already. If we know that, which means that initially when we start, we are going to check in that new data structure first that, hey, this element, have I cloned it already? If I have cloned it already, I would skip over, I would go to next element. If I haven't cloned it already, I would create a new clone of it, and then I will put the same entry in the hash map first before I go to the next element. So that way, when after this first circle comes and when I come back to the same position, I would know that, okay, I have already calculated this one, which means that I don't need to calculate it again and I can skip over it. First of all, let's see that what kind of additional data structure we are going to create, where we can immediately find that whether we have visited any particular element or not, which means that we are going to do a lot of searching. Hence, we will need a data structure that is very quick and efficient in terms of finding the any element, that whether it contains that element or not. And the answer is pretty simple. If that kind of scenario happens, we need to use hash map or hash set or something with the hashing. We cannot use the linked list over here. It would work fine, but it's going to add that much more additional time strain or on our system. So make sure that you justify your reasoning. I mean, in the interviews, people are not typically going to ask that why did you use hash map? This is a given. But the thing is that thinking should be clear in your mind that why you are using it. And in most of the graph problems, uh, typically hash map is being used. Now inside this hash map, we are going to store two values. So as a key, we are going to store a node, and as a value, we are also going to store the node. But the thing is, as the key, we are going to store this input node, and as the value, we are going to store the cloned node that we will create. So let's see that what should be the algorithm for our solution and how we are going to approach it. So initially we start at this position 1. Now at this position 1, first of all, we check that whether we have this entry inside our hash map or not. Okay, we don't have the entry inside the hash map because we can find it in constant time. If the entry does not exist, we first of all create a clone node. Okay, clone node has been created. Now after creating the clone node, immediately before even we check for the neighbors of this one, immediately we are going to add an entry inside the clone node. So the value would be the cloned value that we have created, and the key would be the original input we are given. Now this is done. Now we are going to check for this one's neighbor. So one, let's say we end up at this neighbor number 2. So again, for this neighbor number 2, first of all, we are going to check that whether neighbor number 2 exists in this hash map or not. It does not exist, so we will create a clone. Now the clone has been created. First we will add the value to the hash map, and after adding the value, we would again go again recursively do find for the 2's neighbors. So in this case, the 2's neighbor would be 3. So we will create first we will check that whether 3 exists in the hash map. 3 does not exist, so we create the node, and then we create this one. Now again we check for the value number 4. 4 does not exist, so again we create an entry inside the hash map. We provide the key value, and then we create the clone node 4 again. Now for the 4th, we again check for its neighbor. So 4's neighbor, one neighbor is 1, which we already have it in hash map, which means that now we can ignore this case because we have already dealt with 1. Now second neighbor for 4 is 3, which already exists in the hash map, which means we can be dealt with it. We go back, 2 is already done, 1 is already done, which means that now we are running out of neighbors to track from inside the given original input. And we know that the original input is completely connected graph, which means that there is at no point there is a possibility that there exists some value 5 over here that is part of this graph, but it is not provided using this connection, because all the elements are connected, which means that this would be our final clone graph that we need to return. So after the loop ends and the recursive termination cases trigger, we can simply return whatever the clone graphs we have found, because from any single location we are able to guarantee to reach all the other elements, and once that is done, essentially we are done. So this is a very effective solution. Basically all we are doing is just we are traversing over the given graph, and during the traversal we are doing something. So in this case we are cloning it. We are using the hash map to keep track of whatever the visited elements that we have been through, and this solution is pretty efficient. It's not the most difficult problem in the world, but the thing is I am very bad at graph problems. So and I have always been scared of graph problems, but the thing is now I have decided to spend more time on graph problems, because if you want to join Facebook, you can't even think about not doing graph problems. Okay, so today is first of many problems to come. If we see the time and space complexity, the time complexity in this case would be big O of V plus E, where V is the vertices and E are the number of edges, because notice that over here we are only doing this much work, we are not doing any additional work. So that's pretty simple. And in terms of space complexity, it would actually be big O of V in terms of number of vertices, because over here we had 4 vertices, and in the hash map we created 4 entries. So whatever the number of vertices we are provided, we are going to use that, and that would be your space complexity. So this solution is actually pretty efficient. We are using depth first search to solve this problem, but even we can solve it with using breadth first search. So it makes no difference in terms of time complexity. The thing is, I just did this using depth first search. Next one I'm going to use breadth first search maybe. So first of all, we are going to create a new hash map, and we are going to name it visited to keep track of whether we have already visited the node or not. Now inside the method, first of all, we are going to check that if the given node is null, which means that we can return the node. Okay, and also we are going to check that if we have already visited the existing node, then we are simply going to return whatever the value we have stored inside the visited hash map. Okay, if this is not the case, first of all, we are going to create a clone node. So let's just name it clone node. And inside the clone node, we are going to give it the value of whatever the node value that we currently have, and we are going to assign a new array list. We are going to add the new clone node to the visited node. We are going to run a for loop for all the neighbors of existing node. So inside the loop, we are going to iterate over the neighbors of the existing node, and we are going to create the clone nodes for that. And inside the current clone node, we are going to put the neighbor as an array list. So, and over here, we are going to make the recursive call with the neighbor. After this loop ends, we are simply going to return the clone node. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit the code. Okay, our solution works, and it works pretty efficiently. There is still room to make a lot of improvisation, as we can see that our solution is not the most efficient. But the thing is, I'm really bad at graphs. So it took me a lot of time to make this video because I need to understand very thoroughly by myself first before I can create the video. But soon I'm going to do a lot of graph videos. So so my video quality is gonna improve, and also my coding is gonna improve. So hope for the best, and let me know in the comments what do you think about the video. And yeah, see you next time. Thank you. So the LeetCode problem we are going to understand now is called redundant connections. This is one of the most popular questions in my opinion. Why? Because we are going to be dealing with graphs. On top of it, we are also going to be learning about the trees, a data structure, and we will learn a new data structure called disjointed set union. So this problem contains two of the most popular data structures that we already know, and one very popular method that can come in handy in all sorts of different cases. So let's understand what this problem statement is asking us to solve. First, we are given the difference between a tree and a graph. The only difference between a tree and an undirected graph is that graph is connected and it can have cycles. Meanwhile, tree is completely connected and it can never have any cycles. That is the only difference. Now we are told that we are given a graph that was originally a tree, which means it could be possible that this graph may be not connected or it may contain cycles. Okay, this is the important clue, that originally this was a tree, but then it turned graph and now it is no longer tree, which means there has to be some cycle existing inside this given graph that contains total n nodes, and we are given the number of nodes as to be 1 to n. On top of it, we are also given an edges array that defines that any particular edge between any two array 1 to 2. Now the thing is, we need to return an edge that if we remove it, so that the resulting graph actually becomes a tree of n nodes. That's it. So we need to basically remove an edge that is part of the cycle, that removing that edge would not have any impact on all the nodes of this particular graph or tree from being connected. And if we can remove that, then basically there should not be any cycles inside the existing graph. So let's try to understand this with few examples. Let's say that we are currently given three nodes, 1, 2 and 3, and we are given bunch of different edges between them like this one. So in this case we can clearly see that this is not a tree. Why? Because there exists a cycle inside this loop, and wherever there is a cycle it can never be a tree, so this is currently a graph. But imagine in this case, if I just remove this particular edge between these three nodes, then this is a very clear example of a tree. Why? Because we can see that it currently has three nodes. All three nodes are connected with each other, because that is one of the conditions of being a tree, that all the nodes has to be connected. On top of the connected portion, we can also see that there are no cycles, which means that removing 2 to 3 was one of the good decisions. And in this case we need to return 2 3 edge as part of the answer, that if we remove this edge then we can completely generate our answer. Now the question comes that why do we only decided to remove edge 2 to 3? In this case, if we had removed an edge, let's say 1 to 3, then also the answer would have been perfectly fine. We would still have a tree that looks like this. But thing is, we are given in the problem that if there are multiple answers that we can remove the edge, then we need to return the answer that occurs in the last input, which means like the last edge in this case made sense to be 2 to 3, so that's why we removed 2 to 3 and not 1 to 3. Okay, so now we already understood that what does the problem statement is asking us to solve. Basically we are given a graph that contains bunch of different endpoints, and amongst some endpoints there exists some sort of cycle, and we need to first of all detect that which particular cells contain are part of the cycles, or which edge is part of the cycle, and then try to see if we are able to remove that edge or not. So if we once again take one more example, in this case once again we can see that removing this edge from 1 to 4 makes no sense. Now why? Because it does not solve our problem. Number one, there is still a cycle persisted, and number two, now we have unconnected components, so this is no longer a tree. This is always going to be a graph. So logically in this case the answer once again has to be the same one, that we need to remove the edge between this 2 and 3, and by doing so we are still going to have a tree like structure, where this one node is parent of three different nodes, that is 2 3 and 4, and this is what we need to do. So once again we need to remove this 2 to 3. Now let's understand that what I'm suggesting we use to solve this problem, and for that I'm suggesting to use a very popular data structure that is called disjointed set union. Now, first let's understand that what does this disjointed set union data structure is. So this data structure actually only has two properties, but these two properties are very important and very awesome properties. So first let's understand that what are the two properties. Basically disjointed set union allows us to create a groups of set, and that's it. So it can show us that if we have like bunch of different objects or values, it can show us that that particular object belongs to which group. And if we provide two different objects, it can say that whether those two objects are part of the same group or not. So let me explain it to you, then it would make more sense to you. Let's say, so I mentioned that this disjointed set union works with two methods. First method is a find method, where if you provide in some value, then it can say that this value belongs to which group. Okay, on top of it, second one method is a merge method. So for the merge method, basically if you provide two distinct data structure, like two distinct objects that belongs to separate groups, then it merges into one common group. So let's see how it works. Let's say that currently I have these three nodes that are part of this one particular group. Okay, and let's say that I have these two nodes that are part of this second separate group. Typically in a disjointed union set, all the nodes are typically represented by some node that is currently present already inside that particular group. So let's say we randomly select that this one is the leader or the representative of this entire group. So we will call this as a group 1. Okay, that every single node that is currently present is being represented by this value 1, so we can call this as group 1. Same way over here, the representative is this value number 4, so we can call this as group 4, where every single node is being represented by group 4. Now we know that we can do two methods. We have the find method and we have the merge method. So let's say that if I try to do a find method and if I try to find value number 3. So if I try to find value number 3, all I am going to get in the return is that this value number 3 is part of this group 1. So in the answer, I would only get value as group 1 and in the return. Why? Because all of these nodes are represented by their parent node or by their representative, and representative in this case becomes like the parent of all the nodes that are part of this particular group. Same way, if I try to do a find operation and if I want to find value number, let's say 5, then in this case the answer we are going to get back is going to be group 4, because this value number 5 is part of this group 4. Now let's say that we wanted to do a merge operation. So the moment we do merge operation between group 1 and group 4, then both of these are going to be merged into one single set, one common set. And how it is going to operate? Number one thing, this property is going to remain as it is. Now we have two options, which who is going to be the representative from 1 to 4, either 1 or 4. We can pick whoever we like. So let's say that in this case we decide that representative is going to be 1 of this common jointed group. So how this group is going to look like, that 1 is the representative. It already had values 2 and 3, so it is going to continue to have values 2 and 3 that represents or who has parent value as 1. But same way, now we are also going to add one more node 4 whose parents or representative is now going to become value number 1. And for this value number 5, it is still going to have 4 as one of its parents. But now for this newly created group, if we try to find that any particular character, let's say if we want to find value number 3, then for value number 3 we are going to say that value number 3 is part of group 1. So in the answer we are going to return the value as group 1. Same way for value number 5, if we try to do that, in this case once again we are not, previously we were returning value number 4, but remember now value number 4 is also being represented by value number 1. So once again for value number 5, the same property is going to be inherited to value number 5 as well. And now for value number 5, we are also going to say that this is part of group 5. So this is the whole concept of a disjointed set union. But the thing is, why the hell am I explaining you this concept? What purpose this serves us? Now let me show you that how we can use this method to actually solve our problem and very effectively find or detect that whether there exists a cycle inside any particular graph or not, or cycle does not exist. And remember, whenever you have to find a cycle in an undirected graph, then this is a very popular method in order to do this one. So not only we are learning about the redundant connection LeetCode problem, we are also learning a new method, a new algorithm, a new data structure with our existing tree and graph data structure. And that's why this is a beautiful problem. Okay. So coming back to the solution. Now remember the problem statement that we needed to find that amongst these three nodes, let's say that if there exists a cycle, like amongst these four nodes, we don't know where the cycle exists. If there exists a cycle, we will need to remove the node that is causing the cycle, or sorry, remove the edge that is causing the cycle. And once we find that, we need to return that as part of the answer. So let's say that currently we are given these four nodes, okay, and we are being told that these are the edges we are currently given. So what we can do is, currently we can create four separate groups, and these groups are not connected with each other. So if we create four separate groups, how it is going to look like? We will have a group 1, we will have a group 2, we will have a group 3, and we will have a group 4. Currently these four groups are not connected with each other. So we can actually have a disjointed union set that is currently present, that represents that for every single node who is the representative or who is the parent of that particular node. So if we want to define that, currently we can have a parent array, let's say, and for every single node we will try to define that who is currently the parent of that particular node. So since this one is being represented by its own, so the parent is going to be 1. Same way the parent for this one is going to be 2. Same way the parent for this one is going to be 3, and so on and so forth. So currently all of these 4 nodes are unique on their own. They don't share any parents so far. Now what we are going to do is we currently have 4 edges that we need to deal with, and let's mark these 4 edges. So the first edge is 1 to 4. Same way second edge is 1 to 2. The third edge is 1 to 3, and fourth edge is 2 to 3. Okay, so logically, if this is the case, now we currently have parent for each 4 separate sets. We are going to start iterating over the edges. For every single edge, we are going to check that what are the current parent groups we have. And if we identify that they contain separate groups for both the vertices of this edges, then we are going to do a merge operation. Okay, let's start doing that, and then you will understood. So currently we are dealing with edge 1 to 4. Now for this edge 1 to 4, we will have to check that which are the vertices involved. So number 1 vertices is value number 1, number 2 vertices is value number 4. So for both of these, we will check we will do a find operation that who is the parent of those particular sets. For 1, the parent is already 1. For 4, the parent is currently 4. So both are separate sets. There is no commonality. So if there is no commonality, we will do the merge operation over here. So if we do the merge operation, what will happen is we are essentially establishing a link between this node 1 and node 4. So by doing the merge operation, now we will have to select that who is going to be the representative. So let's say that we are going to choose the smaller value as the representative. So I choose representative to be 1. Now, if I choose the representative to be 1, which means now even for this 4, the parent is going to be 1 because 4 is being represented by 1. And for the value number 1, the parent is going to be itself. So we will have to make some adjustments to our parent array. So this value number 1 is going to stay as it is, that it is currently the parent of its own. But for this value number 4, the parent is going to change, and now this is also going to be represented by value number 1. Okay. We completed this operation, and now we have made the updation on the parent block, and we also are done with this 1 to 4 edge. So now let's take care of 1 to 2 edge. Once again, repeating the same operation, we have two nodes 1 and 2, and for both of them, the 1 has parent as 1 and 2 has parent as 2. We can see over here. But now since both are separate, so we will have to do the merge operation. If we merge these two cells, once again we are establishing a link between this 1 and 2. Establishing a link between 1 and 2 now, which means we are also updating the parent of this 2 to be value number 1. Okay, and now the next edge we currently have is once again edge 1 2 3. So once again for 1 2 3, it currently has 1 and 3 as separate nodes. If we take a look at the parents, it is going to be 1 and 3. If we do the merge operation, because they are separate links, so if we do the merge operation, we are going to have our parents array that is going to look like all 4 values are being represented by 1, because we are also establishing this link as well. Now this is our parents array, all 4 values contain 1, but we still have one more link that we haven't tested, and that is this link 2 to 3. So let's do that. For this 2 to 3, we see we currently have vertices 2 and 3 as part, but now when we check for the parents, we can see that the parent is going to be common, that is going to be 1 and 1 for both 2 and 3. So this is going to be common. The moment we identified common parents amongst any two vertices, we can clearly say that if we were to create an edge between these two nodes, that edge is already part or is going to be part of the common nodes that are already connected in a common set. So creating this new edge is only going to lead to creation of cycle. And the moment we identify any two nodes that share a common parent, basically we can just return that edge as the answer. And this is the whole solution basically. So you understood how beautiful the solution was. We first of all understood that how a disjointed union set works. Then we understood that what is the difference between tree and a graph. Then we understood that how we can use disjointed union set and its property to find or update the parent values or create new links between any two vertices. And then we find the edge that is causing all sorts of trouble and return that as part of the answer. So this is a beautiful solution and a beautiful approach. So now let's quickly see the coding solution for this one. Okay, now the coding solution for this one is not so complicated. So let's try to understand what is being asked us to solve. First of all, we need to check that for any particular given node, we will have to define that what are all the different parents. So first, we are going to initialize a new array called parents, and notice that we are setting the value as edge length plus 1. Now we are starting to iterate parent from 1, not from 0, because initially each node is its own parent and we are being told that the current nodes we have are 1 to n, not 0 to n. So that's why we are starting from 1 and we are marking all the values as their own parent, which means all the nodes are currently individual sets of their own. Then we are going to iterate through every single edge in order to find the redundant one. The moment we identify a new edge, we are going to break both the values in part of two nodes, node 1 and node 2. For both the nodes, we are going to be finding the parents of those nodes, node 1 and node 2. And for that, we are going to be calling our find method that we have defined. Next, we need to check that if at any given moment we identify that the roots are same for both node 1 and node 2, we need to return that edge as the answer, because that edge is causing all the trouble and creating the cycle. If that is not the case, then we need to update the root of that particular second, like the parent of second root, to become the value of the first root. And this is what we are doing, is the union or the merge function amongst our two values. So let's quickly try to see the helper function we have created, that where we can actually use to find that who is the parent of that particular node. Basically, we are simply checking that if the node is not the node we currently have, if that is not equal to the parent node, we are simply going to keep traversing up in order to find that which is the parent node, and we are going to be updating the value of the parent node. That's it. It's very simple, and we are returning that value. So basically we should be able to calculate everything. Now this is just a return statement that is ideally just returning the value 0. Basically this should never happen, because we are being told that for every single input we do have a graph that contains a cycle and we need to return proper edge. So we should be able to find a scenario like this. Now let's quickly try to run this code and see if our solution is working as expected or not. Seems like our solution is working beautifully. Let's submit this code. And our code beats 100% of all the other solutions, which is awesome. In terms of memory usage, it is exceptionally well. So in both aspects, this is doing wonders, and this is a really good solution. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do course schedule lead code problem, and this is one of the most versatile problem that has been asked at bunch of different companies, like huge number of companies. We can see the companies like Amazon, Microsoft, Facebook, Google, TikTok, Snapchat, Robinhood, Twilio, Uber, eBay, Tesla. All the companies have asked this question, and this question is very practical, real life application. So that's why a lot of companies like to ask this question. So this is a LeetCode medium problem, and we are given a number of courses, and we are also given an array of prerequisites where any single entity in array is defined like this, where we are given two values, suppose a and b, separated by a comma, which means that we must complete course b first in order for us to complete course a. So suppose we are given an entity in the prerequisites like this 1 and 0, which indicates that this course 1 actually has a prerequisite called course 0. So we can define it like this, that course 1 has a prerequisite on course 0, and in terms of the practical manners, we first complete this course 0 in order for us to complete this course 1. And based on the information given, we need to check that whether we can finish all the courses or not. And if we can finish all the courses, depending on whatever the prerequisites we are given, we need to return true, otherwise we need to return false. Okay, now that we understand the problem statement, let's take a custom example to understand the problem. Suppose we are given the list of prerequisites like this, and we are given the number of courses as 4, which means that we need to complete the 0, 1, 2 and 3. These 4 courses we need to complete, and this is the list of prerequisites we are given. Now we can consider this as actually graph problem. We can consider these as graph nodes, and the prerequisite information, we can treat them as graph edges. So over here we can say, let's plot it on a graph and let's see that how it would look. So over here, 1 has a dependence on 0, so I mentioned this. 0 has a dependence on 3, so let's also mention this. And 2 has a dependence on 0, so 2 has a dependence on 0. Okay, so this is how we can plot this on a graph, and we need to see that whether we can complete all of these forces or 4 courses or not. So the most intuitive solution is to check from the beginning. We check at this course number 0, that can this course number 0 be completed or not. Now in order for us to complete this course number 0, we see that this course 0 actually has a edge pointing towards course number 3, which means that course 3 is a prerequisite for course 0. So we need to complete this course 3 before we can complete course 0. Now we are at this course 3 again. We check the same thing, that whether we can complete the course 3 or not. Now course 3 does not have any prerequisite, which means it can be completed on its own. So we say that okay, course 3 can be completed. Now again we backtrack to 0. At 0 we check that does 0 have any other prerequisites that we need to take care of. No, 0 only has one prerequisite on course 3 which we can complete, which means that we are able to complete course 0 as well. So we can mark this and the square box indicate that we are able to complete that course. So we are good. So we already know that 0 can be completed, 3 can be completed. Now we check for this course number 1. So at course number 1, we check that what are the prerequisites for course number 1. Well, course number 1 has a prerequisite on course number 0. So since we already know that course 0 can be completed, which means we can also conclude that course 1 can also be completed, which we can mention over here. And we can check for this course number 2. So course number 2 also has a prerequisite on course 0, which is already done, which means we are able to complete course number 2 as well. So in this case, for all the 4 courses, we are actually able to complete them, and we can return true in this case, that yes, based on the given number of courses and prerequisites, we are able to complete all the courses. Now we need to check that what could be the scenario if we cannot complete the course. So suppose we are given an additional edge like this in the same example. Suppose we are given this additional edge. Now let's see that how the dynamic would change. Let me clean this up a bit. Okay, now we have this additional edge 3, 2, which means that in order for us to complete this course number 3, we would need to complete course number 2 as well. Now let's see that can we complete. So initially we would check that can we complete this course 0. So in order for us to complete course 0, we would need to complete course 3. Okay. Now in order for us to complete course 3, we would need to complete course 2. Okay. And again, in order for us to complete this course 2, we would have to complete this course 0. So notice that we are constantly stuck inside a loop. It's the same scenario where you need experience to gain a job and you need a job to gain experience. It's somewhat similar kind of example, that we are stuck inside the loop, which means that no matter what happens, we are not able to complete any of these 3 courses without completing the other one, because there is an interdependence between each other. And essentially in this case, we would have to return false, that we cannot complete all the courses. But the thing is, why did we had to return this false? Well, the reason is quite simple. Basically, in terms of graph manner, if we speak, what was the difference from this graph compared to this previous graph? Only this edge. And when we added this edge, what essentially we did was we introduced a loop inside our graph amongst these 3 values, 0, 2 and 3. So we can conclude one thing, that at any given moment, if we've identified that there exists a loop inside our graph, we would be able to immediately return false. If there does not exist a loop and we are able to, from every single element, we are able to complete all these prerequisites, in that scenario we need to return true. So now we have these two information. Let's see that how can we use them and how can we solve this. So suppose we are given an example like this, and these are all the prerequisites that we are given, and we need to complete the total six number of courses in order for us to conclude that this graph can be scheduled or not. So essentially we are going to apply the same logic. We are going to first of all take these inputs, we are going to convert them in a graph like this. Inside the graph, for every single course, we are going to see that whether we can justify these prerequisites or not, and at any moment if we identify that there exists a loop, we will immediately terminate and return false. If there does not exist a loop, we would keep going, and eventually we would return true. So that is the idea. And in order for us to achieve that, first of all, what we are going to need is, we are going to need some sort of graph data structure, because initially the only two values we are given is number of courses and the set of prerequisites. So first of all, we would create a data structure like hash map, and inside our hash map we are going to store two values. We are going to store, as a key we are going to store the number of courses, and as a value we are going to store the number of prerequisites that every single course has. So initially we would have, so this is the number of courses and these are the prerequisites that we have. And we would try to see that can we complete all the courses or not. So first of all, we are at this course 0. So in order for us to complete this course 0, we need to see that what are the prerequisites for course 0. So for course 0, the prerequisite says course 2. Now for this course 2, what is the prerequisite? The prerequisite is actually course 3. Okay, and now for this course 3, the prerequisite is actually course 4. So here, and for this particular course 4, the prerequisite is actually course 5. So here, now we are at this course 5, we check that can we complete this course 5, and yes, we are able to complete the course 5 because there exists an empty list. So which means we can conclude that course 5 can be completed over here because there is an empty list. So again we backtrack, we go back to course 4. At this course 4, we know that course 5 can be completed. Since course 5 can be completed, we can also have an empty list over here, because it defines that at any moment, if we are at this course 4, that course 4 can always be completed because its prerequisites are already met. So we can have an empty list over here. Now again we go back. If we go back, we are at this course 3. So in order for us to complete this course 3, we would need to set up an empty list over here because course 4 can be completed. That is done. Now again we come back to this course 2. At this course 2, again we will create an empty list, and now we are at this course 0. So at this course 0, we only have dependence on course number 2, so we can also have an empty list over here, basically defining that course 0 can be completed. Okay, so that is one observation that has been done well. Now, and see that we were only trying to calculate that can we complete this course 4, but we already concluded that we can complete all these courses as well, and we have already established them inside our hash map. So at any moment, we only need to identify the remaining courses and not all of these courses that we have solved already, which means we are efficiently improving our solution. Second, we come at course 1. Now this course 1 actually has 3 dependencies, course 2, course 4 and course 5. So let's take care of each of them one by one. First of all, we will check that from course 1 can we complete course 2. So we check for this course 2 and we check that these prerequisites are already met because there exists an empty list, which means that we can eliminate course 2 from over here from the list of prerequisites because we know it can be completed. Again, we check the same thing for this course 4. Over here, this course 4, we again have the empty list, so we can also eliminate the course 4 over here as well. And again, we can repeat the same process for this course 5, that course 5 can also be completed because there exists an empty list, which means even at this position course 1, we can create an empty list over here. And now if we look at all the courses, the only prerequisites we have are just empty lists. And once we achieve that, basically we can conclude that we have already reached our solution and we can return true in this case. So this solution works perfectly fine. But the thing is, we missed the key point over here. Like, because this was a true scenario, we did not identify any issues. But the thing is, if there was a loop, we were not actually checking that whether we are encountering any loop or not. So let's see that if we want to encounter any loop at any iteration, what would be the additional steps we need to take. So let's modify our example a bit. Suppose we have an additional prerequisite like this 5 3, that in order for us to complete this course 5, we will need to complete course 3. So we will have an edge like this, and let's modify our prerequisites table. Okay, now in this example we know that there exists a loop between this 3 4 and 5, so we need to take care of it. And in order to take care of it, I'm suggesting that we create an additional hash set at the beginning of checking for any single course. So we create a hash set, and in our hash we just name it as visited or something. And over here we will keep track at any location are we repeating the same element. So let me show you what I mean by that. So initially, suppose that we are at this course 0 and then we start our program. So we want to check that whether we can complete course 0 or not. So first of all, we will check that whether we have already visited this course 0 in this current iteration. So we check in this visited node that have we visited course 0, and because it's a hash set, it's a constant time operation, so we are not adding any additional strain on the time complexity. So we haven't visited this node 0. We would add an entry over here first. Now we will check over here that what are the prerequisites for this course 0. So the prerequisite is course 2. So again we would check our visited node first. So course 2 is not part of it, so we would add an entry over here, and again we would continue over here. So now we need to check this course 3. Again we would add it entry to the visited node. We check over here, we need to check course 4 we haven't visited, so we would add an entry over here. Then we would check the force prerequisite 5 we haven't visited, so which means we would add an entry over here. And now at this 5 we would check the prerequisite for 5. So for the prerequisite for 5 is actually 3, so we are again at this position 3. So first of all we will check that whether we have visited this 3 or not, and this time we would know that yes, we have already visited this node 3, which means that we are in a loop. So this is what this hash set confirms, and the moment we find out, we can immediately return false over here. We don't even need to check any additional items in this given graph, and we would be able to terminate our case immediately. Which means, and in case if this edge was not existent, this entry for this value number 5, we wouldn't have to check anything, and we would have been able to complete all our code, and we would have been able to return true, but which is not the case this time, because there exists an additional prerequisite as specified over here. So this would be our final solution. And now let's calculate the time and space complexity for this one. So for time complexity, we can actually complete this whole thing in big O of v plus e time, because at any moment the maximum traversal we will have to do is from one node to all the single nodes, and throughout all the single edges. So this would be the time complexity. And space complexity, because we are creating an additional data structure like this hash map and also this hash set, but the thing is hash set is going to be smaller, so we are only concerned with this hash map. For general time complexity, it would be space complexity, it would be big O of v plus e as well. Okay, first of all we will create a hash map, and we are going to store integer and list inside it. We will name it course graph. Okay, now we will have to build our graph. So essentially we are going to iterate over every single prerequisite in the given prerequisites, and first of all we will check that whether this prerequisite is already added in our graph or not. So if it is added already, we only need to append the new prerequisite, and if it does not exist, we will need to create a new one. We'll have to create a new entry in our course graph. So we will create a new list and add the list, and then we will add the entry of the course and the list to our graph. Okay, so after this loop ends, we should have our graph structure ready. So now we will create a hash set that will take care of integer values, and we'll name it visited. And now we will have to run a loop for all the courses that we are given. And now we will have to create a method to check that whether there exists a cycle inside the loop or not. And let's name our method that course schedule, which indicates that whether we can schedule a course or not. In this course schedule method, we are going to provide the current course, the visited node, and the graph that we had created. And if this responds back to false at any given moment, we would know that we cannot create the course schedule, so we will return false immediately. And if this loop ends and we don't return false, which means that everything was successful, and we can return true. Okay, now we will have to create this course schedule method. So let's create a boolean method. Now let's test our terminating cases. So if our set contains the current course, which means that we have detected a cycle, so we can terminate immediately, so we can return false. Also we check that if for the current course, if we already have an entry in the graph where it has an empty array list, we can return true. If that is not the case, we will have to iterate over all the prerequisites for any particular course. So first of all, we will add the current course that we are iterating over in our visited hash set. Then we will iterate over every single prerequisite for that particular course. We would call our recursive function. So and we will provide the current prerequisite we are at. We will provide the visited hash set, and we will provide the graph. And if at any point this returns false, we can return false immediately. However, if this loop executes, we know that for that particular course we are actually able to complete the course, and we can schedule it. So first of all, we will remove it from the visited node, and then now since we know that this particular course can be completed, we would update the entry for that course in our course graph. So we would set the prerequisite to null, which means that in future at any point, if we identified this particular course, we know that we are able to complete it, and we can just move forward quickly. And at the end, we can simply return true in this case. So I guess this would be our course schedule function where the main logic happens. And let's try to run the code. Okay, seems like our code is working. Let's try to submit the code. Okay, our solution works, and it works pretty efficiently. So I would be putting this solution in the comments. You can check it out from there. And this was a really long video. It took me a lot of time to make it. So I hope you like it, and let me know in the comments on what are your thoughts about this problem. See you next time. So today we are going to do course schedule 2 lead code problem, and if we see some of the popular companies who have already asked this question, there are companies like Amazon, Google, Microsoft, TikTok, Apple, Plantier, ByteDance, Roblox, Uber, Facebook, Robinhood, Snapchat, Bloomberg, DoorDash, Lyft, and Goldman Sachs. So this has been a very popular question at many different companies. I'm going to pay my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and also very well like problem on LeetCode. In this case, we are given two items. First item is number of courses. Now the number of courses, it says that suppose we are given number of courses to be 3, which means that we are given the courses 0, 1 and 2. Suppose we are given the number of courses to be 5. In this case, the courses are 0, 1, 2, 3 and 4. So this is what the number of courses define. Second item we are given, which is more important, is the array of prerequisites. Now, what does an array of prerequisites define? Well, there can be a structure that looks like this, A, B. What this means is that course B is a prerequisite for course A. We all know that we need to complete like the prerequisite course in order to go and do the more advanced level courses. So in this case, if we complete course B, then we are eligible to complete course A. But say for example, for some reason we are not able to complete course B, we are guaranteed that we would never be able to take part in or be eligible to complete course A. Now, after having these two items, number of courses and prerequisites, basically what we need to do is we need to return an ordering of courses such that we are able to finish all the courses. And what does finishing all the courses means? That we are abiding by the list set of or the all the prerequisites that we are given amongst all the courses. And definitely there could be many different answers to that. We can complete the courses in many different ways, so we need to return any of the valid answer. And for some reason, if we are not able to complete all the courses, we need to return an empty array. So let's try to understand this with few examples. So in the first example, we are only dealing with two courses. So the two courses are going to be 0 and 1. Now for these two courses, we are only given one prerequisite, and this prerequisite says that course 0 has to be done in order to be eligible to complete course 1. So if we complete the courses in the ordering of 0 and 1, then this is going to be a legitimate answer, where we complete the course 0 because it has no prerequisites, and since we have already completed course 0, we are eligible to complete course 1, and this is going to be a valid answer, so we can return this as the answer. If we take the second example, this is a little bit more complicated. Now we are dealing with 4 courses, which means courses are 0, 1, 2 and 3. Now in this case, if we see, there are a bunch of different prerequisites, so let's go every single one of them and try to find some answer. So first one, it says that course 0 has to be done before we can do course 1. Okay, that is good. Second one says that course 1 needs to be completed before we are eligible to do course 2. So we have already completed course 1 over here. So let's try to do course 2 after that. Then it says that course 2 has to be done before we are eligible to do course 3. So over here we are already done with course 2. So let's complete course 3 after that. So this is one of the valid orderings. And in this case, if we return 0, 1, 2 and 3 as the answer, this is going to be a perfectly valid answer. And in this manner, we are keeping track of all the prerequisites and we are also completing all the courses. Let's take one final example. So if we see in this final example, this is a little bit different example. So over here, we are given 3 courses. So courses are going to be 0, 1 and 2. Now we are given some prerequisites. So let's try to go through each one of them. So first one is 0 to 1. Okay, we need to complete course 0 in order to complete course 1. That's good. Now second one, it says that we need to complete course 1 in order to complete course 2. So 1 we have completed over here. Let's create it for 2. But now this prerequisites, it's a little bit tricky, and the tricky part is that we need to complete course 2 in order to complete course 0, which is the tricky part, because now if we see, there is no way for us to complete like all 3 courses, because every single time we are going to be bounded by some other course. Because definitely in order to complete course 1, we need to complete course 0. In order to complete course 0, we need to complete course 2. In order to complete course 2, we need to again complete course 1. But we cannot complete course 1 because 0 hasn't been done. So this is going to be keep running in the round and round, and this is a huge problem. So in this case, we are simply going to return an empty array because we cannot find an ordering that satisfy all the properties. So based on my drawings and all the logic I'm trying to show you, it becomes pretty trivial that how we are going to solve this problem. The way we are going to solve this problem is using graph theory. And for the graph, we need two items. We need nodes and we need edges. So as the nodes, we are actually going to use the number of courses, that all the courses are going to represent a node in itself. And for the edges, we are going to take all the values that are present inside the prerequisite table, and based on that we are actually going to create an edge, and that is going to give us very interesting results. Now in this case, say for an example, just consider this example and let's try to draw a graph in this case. So first one, okay, we are given 4 courses, so we are going to draw 4 nodes. So first prerequisite is that we need to complete course 0 in order to complete course 1, which means 0 is actually a prerequisite for course 1. So we can have an edge between 0 and 1, where 0 is a prerequisite and 1 is the node that needs the prerequisite of 0. So notice in this case, I'm only drawing one directional edge. Why? Because for 1, 0 is a prerequisite, so that's why there is an edge between 0 to 1. But the thing is, for 0 there is no edge coming back from 1, because so far we haven't find that there is a prerequisite in this case. So because it is not the case, we are simply going to keep progressing. Now next one is that we need to complete course 2 in order to complete course 1, right? So basically from 1 to 2 there is also going to be an edge, because course 1 is a prerequisite of course 2, and course 1 has to be done before we can proceed to course 2. So that is why there is an edge from 1 to 2. Same way, we must do course 2 before we can proceed to course 3. So we must do course 2 in order to proceed to course 3, and this is also a prerequisite. And this is a graph that is being made based on the number of courses and the array of prerequisites that we are given. Now our aim is to find any legitimate offering. So in order to find any legitimate offering, the logic is going to be quite simple. What we are going to do is we are going to pick any single node and we are going to do a depth first search. Now in the depth first search, we will have to keep track of like 2-3 items. First thing we will have to keep track of is that there are no cycles. If we find cycle, basically we have entered a scenario where we are not able to complete all the prerequisites. Say for example, in this case, if we are given an additional node that looks like this, or sorry, an additional edge that looks like this. So in this case, we have actually detected a cycle, and because we have detected a cycle, there is no way for us to complete all the courses. So definitely in this case, we will have to return an empty array. But lucky for us, in this case, we are not given a prerequisite that looks like this, right? So we found no cycles. Second thing we need to do is we can pick any single node, and from that node, if we start iterating over all of its neighbors in the DFS manner, and then keep a track of all the elements that we have visited, by doing that we won't be able to find any cycles, and also we will try to order them in a manner that we match all the dependencies, and in the end we simply need to return the ordering. So this is going to be a perfect logic to solve this problem, that we are taking consideration of everything. Now let's see that we know the core logic, that how we are going to use it. Let's see how we are going to implement it. So in this case, we have total 7 courses that we need to take care of. And for all of these 7 courses, I also have a prerequisite array. Now, based on these two things, we know that for any single graph problem, we need a way to represent the entire problem in a graph manner. So how we can do it is we have 2 ways. We have adjacency list and adjacency matrix, right? So in this case, I think we are good with going with adjacency list rather than adjacency matrix, because the graph is not going to be too sparse, and so let's try to stick with adjacency list. Now based on this given array, we would be able to create our adjacency list. Now how we are going to create our adjacency list? Well, basically for adjacency list, we are going to create a hash map. Now inside this hash map, we will have to take care of 2 values. First one is like the key, and second one is its value. So as a key, we are going to take all the courses that are present, and as the value, we are going to take that which courses, like for that particular node, for home it is the prerequisite. Again, I'm repeating myself. So as the node, we are going to take all the courses. So basically the nodes are going to be 0, 1, 2, 3, 4, 5, 6, 7 over here. And as its value, we are going to see that for what are all the courses it is a prerequisite for. So let's try to draw our graph and also fill up our prerequisite table. Okay, so based on the given prerequisites, we have been able to draw our graph. Now, if we see on the graph, our graph is only for our explanation. Basically, all we will have to do is we will have to create our prerequisite adjacency list that I mentioned. Now, in the hash map, these are all the nodes or the number of courses as mentioned. And now let's try to keep on mentioning their prerequisites. So first we will see that for what are the courses, 0 is a prerequisite. So from the graph, we can actually take a look at this prerequisite array as well. But the thing is, I feel it would be better if we just do it from the graph. It would be easier to visualize. So in this case, basically course 1 and course 2, these are the two neighbors, or these are the two edges that derive from course 0, which means unless completing course 0, we cannot complete course 2 or course 1, because for both the courses 0 is a prerequisite. Same goes, okay, let's see for course 1. Course 1 is actually a prerequisite for course number 6. Okay, that's cool. For course 2, okay, course 2 is a prerequisite for course number 4. And 6 actually has no prerequisites. Okay, now we have done half of the work. We have created our graph. Now the question is how we are going to traverse the graph, how we are going to make sure that we are finding cycles, and how we are going to keep track of all the answers, that what should be the correct ordering. So these are the three tasks we will have to do. So the traversing part is pretty easy to solve. We are simply going to use the DFS and we will keep on iterating. The question is how we are going to detect cycles, whether they exist or not. In order to do it, basically from any single node, if we are going to do a DFS, we will have to keep track of that at any given position. We are not coming back to that particular node that from where we started. So we will have to find a way to keep track of all the visited nodes. So one of the best way to keep track of visited node is using hash set. So we are going to use couple of hash sets. There is also another trick where we can give the nodes some numbers and or some colors where we can treat them as such that whether they have been visited or not. But for explanation purposes, let's just keep track of hash set. When we go to the coding, we are going to use it differently. Now we also need to keep track of the ordering. The idea we are going to use over here is that we are actually going to use a stack. Initially the stack is going to be empty, and from whatever the node we started visiting, we will keep on visiting until we reach to a point where it does not have any prerequisites or all the prerequisites has been met. Once we get to that point, we would add that course into our stack. Eventually our stack is going to be full. And remember, the idea of a stack is that in the stack we keep on adding all the values. When we pop off all the values in the reverse manner, then we added. So basically we are adding the first value inside that contains basically all the prerequisites, and then we will keep on adding values on top of it. So the top value inside our stack is going to be a value that contains no prerequisites, and then we will keep on popping one value at a time, and in the end we should be able to get our answer. So after this long explanation, let's see all of these things in action. Okay, so now we have our structure ready. I have created an adjacency list over here. Now for this adjacency list, first of all, we are going to do DFS. So I'm going to keep track of that what element we are DFSing over. We are, for any single DFS that we are doing, we will also have to keep track of the current visited nodes that we are going through, because during the DFS we do not want to find any cycles. So if any element appears in the currently visited elements during the same DFS, we would know that we have encountered a cycle, right? Suppose we do not encounter a cycle and we reach to an element, say for example like 6, that does not have any prerequisites, then we can simply conclude that that node is a good node to be added to the stack. So we will simply add it to the stack. Once adding to the stack, we will also add it to the node of visited nodes. What this would do is, this would allow us not to do redundant work or not to do duplicate work. So let's see the whole calculation in action. Okay, so first we are going to start DFSing over the first element. So we are going to start with element number 0. If we start with element number 0, what are the neighbors or what are the values for element number 0? Okay, so first value is value number 1, right? So currently we are visiting, okay, initially we started our visit with element number 0, then first element we are visiting is currently 1. Now we are going DFS, which means we are going in depth. So even for node number 1 we are going in depth. So node number 1 has is a prerequisite for course number 6. So which means if we want to get to course number 6 we will have to go through 1. So now we will go to course number 6. So currently we are visiting course number 6. Now course number 6 does not have any is not prerequisite for any of the courses, which means this is wonderful. So now what we can do is we can conclude course number 6 to be done. So we will take the course number 6 value from here and we can actually add it to our stack. So if we add the value number 6 to our stack, okay, now we have added a value number 6, which means course number 6 we have already put the ordering for that. If we put the ordering for that, which means we have already visited that course. So we are going to add an entry in our visited hash set. Now let's go back. Now if we go back, okay, we still have one more element 1 that we haven't processed, right? So if we check for element 1, does it has any other prerequisites or is it a prerequisite for anything else apart from 6? No. So which means this is done. So for 1 we do not have any more courses where 1 could be a prerequisite, which means 1 can also be added to stack. So we will add entry number 1 to the stack as well, and also at the same time we would define 1 has also been visited. Now we go back to course number 0. So for course number 0 currently we have taken care of this course number 1, but we haven't taken care of this course number 2. So we will keep on iterating. So currently now we would visit course number 2. For course number 2, do we have any ways to go to next course? Yes, we need to go to course 4. We will have to go through course 2. So we can go to course 4. Now for course number 4, is it a prerequisite for anything else? Yes, it is a prerequisite for course number 5. So in order to go to course number 5, we have to go through course number 4. Now for course number 5, okay, course number 5 can go to course number 6, but the thing is 6 has already been visited, so we can ignore this case. If we ignore this case, course number 5 is no longer prerequisite for any other courses, which means now course number 5 is actually ready to be added to our stack and also visited hash set. So let's do that. We will remove course number 5 from here. We will add that 5 has been visited and we will add an entry 5 over here. Awesome. Now we have course number 4. So for course number 4, okay, apart from 5 it did not add anything else, so which means course number 4 is now also eligible to be added to the stack. So we will visit course number 4 and we will visit course number 4 to our stack. Now for course number 2, let's see if there are any more entries. No, there are no more entries. Awesome. So now we will put course number 2 over here as well. So 2 added and also 2 added, 2 removed from the current stack, and now we are back to the course number 0. For course number 0, okay, we already took care of course number 1. Now we also took care of course number 2, which means 0 is now also eligible to be added. So awesome. Let's do that. So we add 0 over here and we add 0 over here. That's great. Now if we go back, this has been jumbled up. So let me clean this up a bit. Now in this case, okay, now we took care of course number 0, right? Now for node number 1, we will check our visited hash set. So in the visited hash set, yes, we have already visited course number 1, so we don't need to do anything. Course number 2 has already been visited. Awesome. Course number 3 hasn't been visited. So now for our current DFS, we will start visiting course number 3. Okay, so for course number 3, it has many different prerequisites. So course number 3, okay, course number 3 is a prerequisite for course number 1. So currently we are visiting course number 3. Let's see, course number 1, okay, 1 has already been visited, so we do not need to visit this one. 4 has also been visited, we do not need to visit this one. 5 has been visited and 6 has been visited, which means all of the courses which could lead us to these courses have been visited, which means course number 3 is no longer prerequisite for any other courses. So it is a good candidate to be added to our stack and our visited hash set. So we can add it to our stack and we can also add it to our visited hash set, right? Awesome. Now if we see our stack is already full, so do we need to worry about adding these more courses or checking for them? No. But if we want, we can do it. It would only be constant time because all of them, they have already been visited, so we don't care. Now since we have our stack ready, let's try to pop out all the values sequentially. If we pop out all the values sequentially, this is going to lead us to our answer. Why? Because, okay, first we have to complete course number 3, then 0, then 2, 4, 5, 1 and 6. If we complete courses in this manner, we would be able to meet our prerequisite. So let's see that whether our answer that we received is this a valid answer or not? Let's compare it with the graph that we created. Okay, so now we have both the values side by side. Let's see if we start iterating. So if we first complete course number 3, then we would be able to finish a lot of different courses. So we won't have any prerequisites for course number, all of them have some other prerequisites, but if we do course number 3, there is no harm, so that is good. If we do course number 0, that is also good, right? Now can we do course number 2? Yes, course number 2 only has prerequisite on 0, which we have already completed, so we can do course number 2. Can we do course number 4? Yes, course number 4 can also be done because it had prerequisites on course number 2 and also course number 3. Both of them have been done. Awesome. Now for course number 5. Okay, 5 can also be done because it had prerequisites on course number 3 and course number 4. Both have been completed. Course number 1. Course number 1 only had prerequisites on course 0 and course number 3. Both have been completed, so we can do that. And also for course number 6, it had actually prerequisites on course number 1, 3 and 5. All 3 of them have been completed before. So this is a legitimate valid ordering that we can use. And this is a great way to solve this problem. See time and space complexity. In this case, the time complexity is actually going to be big O of V plus E, where V is the number of vertices and E is the number of edges. And if we see space complexity is also going to be big O of V plus E. And this is a great example. And also the way to find this ordering is also topological sort. So congratulations to you. You also learned a new algorithm. So since this video is already too long, the code solution for this problem, I'm just going to explain it and then paste this code in the comments so you can check it out from there. Okay, so first of all, we are actually doing things a little bit differently than what I explained. Basically, we are creating 3 different like white, gray and black values. So this is going to be assigned to every single node. White is going to represent that the node hasn't been visited or it hasn't been touched so far. Gray means that during the current DFS, this has already been visited. And black means the code that is already going down into the tag or that we have created, which means from where we can fetch it and use it for the answer. Now let's go to our main method first. First, we have this find order method where as an input we are given number of courses and we are also given prerequisites. Now first thing we need to do is that based on the prerequisite, we are actually going to create the adjacency list. This is what we are going to create as I explained in the explanation. Now after this adjacency list, we are going to assign every single value to the white color for the first time. Why white color? Because it hasn't been added to any list or it hasn't been visited. And then we are going to go over every single values of this adjacency list and call our DFS function. Now what does this DFS function is going to do? It is going to recursively call all of the values or all of the neighbors of that particular node until we reach to the end. Now let's see what happens inside the DFS function. We receive a node as an input. Now we have a boolean value is possible. That is going to check that whether we have been able to find any cycle or not. And how we are going to be able to find a cycle? By using this gray color. So if a node that is already assigned a gray color and somehow in the DFS we find it to be gray again, which means we came back to the same node which we have already traversed during our current DFS. So there is a cycle present. So this is a good way to detect that. And for that we just created a different method that if the given color is gray, we simply get the DFS method. We simply assign the values is possible to be false. Okay, now in this case, first we assign the value to gray for any particular node that we are visiting. Then we start visiting all of its neighbors. Now for every single neighbor, we are only visiting the node that where the color is white. If the color is black, we are going to ignore that. If the color is gray, we are going to assign the value is possible to false, which means that this is not possible to do it and we can simply return an empty array in that case. If not, basically recursively we are going to call our DFS function for every single neighbor, and for every single neighbor we are going to assign the value to gray, and we are going to keep on doing it until we reach to a point where it does not have any more neighbors left. So at that time we are going to put the node and assign it to color black, and also we are going to assign it to a topological order list that we have created. recursively, if we keep on doing it, basically our topological order list is going to be basically our stack where we would have all the values filled up. And once that is done, from our main method, we will check that, okay, if this is possible, if that is true, which means if this is still possible, then we will simply iterate over all the number of courses, and we are going to create a new array called order. For this order, we are going to take all the values in the reverse from the topological order, and we are simply going to return the order list that we just created, and this is the whole solution. So I would be posting this in the comments, so I hope you understood it. And if we try to run the code, this runs perfectly fine. If we try to submit the code runs decently efficiently. And yeah, so let me know in the comments what do you think about this. So the lead code problem we are going to solve now is called walls and gates. We can see that this UI looks slightly bit different than our typical lead code problems, and that is because this is actually a very popular lead code premium problem. So that's why I took this screenshot from a website called leadcode.ca. So whoever is operating that, thank you so much. Now let's understand the problem statement. We are given an m cross n 2D grid that is initialized with three possible values. First possible value is -1. So -1 defines that there is a wall or an obstacle that we cannot cross over. Next value is 0. 0 defines that there is a gate. And third value is an INF. So INF is a very large number basically. And if we are given this very large number, that defines that the given room is empty. So basically we are given three distinct values. One value defines that on that particular cell position, there could be a wall, or it could be a gate, or it could be an empty room. So for the rest of this problem, let's just try to use only these three values, so it would make sense for us to understand. Okay, now we need to fill each empty room, so each cell that contains the value e, with the distance to its nearest gate. So this is the gate that we are given. We need to calculate the distance from every single empty room to its subsequent nearest gate, and if it is impossible to reach a gate, then it should be filled with an infinite value, or which means like an empty room. So let's try to understand this with an example. Basically we are going to be given a grid like this that contains three different values, infinity, -1 and 0, but the thing is I have presented them slightly nicely over here. So let's try to understand and figure out that what does this problem statement is actually asking us to solve. So we can see that there are a bunch of different empty rooms that are currently given to us, and we are only given two different gates that these empty rooms can try to reach to. Plus for some empty rooms we actually have walls that are coming in between, so we will have to ignore those walls and try to figure out that what is the best way to reach to those particular gates. So let's just create an empty like empty m cross n grid, and we will try to fill out these values. So we can see that for this very first position, this one is an empty room. So what are the closest gate to this empty room? One closest gate is located over here. If we calculate the distance, this is actually 3 cells away. So in this case, one option is that we can fill value 3 over here, or if we have to calculate the distance between second gate, it looks like this is very close. This feels like that this is only 2 steps away, but that is not the real case. Why? Because there is a wall in between, so we cannot cross the wall. So if we have to reach to this particular gate, we will have to go down this path and then this path and then this path. So that actually makes the total distance as 4. But the thing is we need to calculate the shortest distance. So over here, shortest distance to the gate is going to be value number 3. Same way, shortest distance over here is actually going to be this gate, that is this value number 2. Shortest distance over here is once again this gate, and that is this value number 1. Now this value is already gate, so we can define it as 0, or let me just mark it as gate for our understanding. Now at this particular position, the closest gate is actually this one, and this is only 2 steps away, so we can actually mark value 2 over here. Same way, this is only 1 step away through this gate. Same way, this is also 1 step away through this gate. Same way, this is 2 and this is 3, and this one is actually 4 steps away from the gate, and that path is actually going to be this one. So this is going to be 4. For all the other ones, the walls are always going to remain the walls, so we can simply mark the walls as it is, and the gate is going to be as gate, and this is what we need to return as part of the answer. Now for some reason, let's try to understand that suppose this value is also a wall. Let's say that over here, let's say that this value is also a wall, okay, just for the understanding purpose. So then now at this position we have no way to reach to a gate because both adjacent doors contains a wall. So in this case we are still going to make put this as an infinite value or mark it as an empty cell. So just for our understandings okay, so let's break down the problem in subtask and we will try to calculate the result. Number one thing we need to check is that distance of any particular cell from the gate. This is the number one thing. Second condition we have is that if there is a wall we cannot cross, so we cannot go to the wall, we should not consider. If there is an empty room, we will try to find that how many steps it take from empty room to reach to the gate or from gate to reach to the empty room. So now what the approach I'm suggesting is that if we try to calculate at every single gate that or sorry every single empty room that where is the closest gate, and if we try to find this one, this problem can get like slightly more expensive. Why? Because remember that at this gate location we will have to do like either a BFS operation or a DFS operation, and we need to keep on iterating over of every single possible neighbors in order to calculate that where does the nearest gate lies, and it could take potentially big O of like m cross n times for every single grid in order to find both the gates in the worst case scenario. So this problem can become like m cross n multiplied by m cross n. That is going to be very expensive problem. So rather than finding out the from like distance from empty room and searching for the gates, it would make much more sense that from any particular gate we can start iterating over and branching out in like different traversal fashion and try to find the empty rooms. And for each traversal that we make, we simply have to do one iteration because we know that it is one step further from the gate in order to reach to that particular empty room. So what the approach I'm suggesting is that first of all we simply iterate over the given input array and try or sorry given input matrix and try to mark all the positions that contains gate. We identified that this contains gate. Now from this gate we start traversing in all the possible directions until we exhaust every single possibility of finding an empty room for the from any particular gate. That is option, that is number one thing. Second thing is that we also take care or take into the consideration that if I have to reach to any particular empty room, how many hops did I had to take in order to reach to that empty room. Also it could be possible that some other gate can also reach to same particular empty room. Then we will try to put the value that contains like the lower value compared to the current value we have as part of the empty room. So let me explain the solution, then it would make sense. Now the question is, let's say that we identify that these two are the gate positions. We know where we want to iterate from. But the question is how are we going to iterate? Are we going to use depth first search or breadth first search? So logic is quite straightforward, since in this case we will have to calculate how many hops it take to reach to any particular location. We don't want to do the backtrack and keep on going in just one direction. We actually wants to branch out in each of the directions. So logically it would make more sense to use breadth first search in order to calculate our result. So if we have to use breadth first search, we will actually have to use a queue in order to generate the result. So idea is we are going to initialize a queue. In the queue we are going to mark all the positions that contains the current gate values. Then from this particular gate value we will keep on iterating over until the next element, and all of its neighbors that we are able to reach that are currently empty rooms, we would mark them to the gate as well, and we would try to update the value of those empty rooms by 1 plus. And the moment we do the next iteration we will add one more value. The moment we do the next iteration we will do one more value. So let's say that we start our iteration from this value. So currently this one is a gate. Okay, these are all the walls that we cannot use or we cannot go over. So let's try to start populating our array using this gate value and see that how is the result we get. During the first iteration we are going to go down this path. So we know that for both of them, the distance is going to be 1, 1. And currently, remember, the distance is infinite. So we are always trying to put the smaller distance on the place of the gate. Next is from here we cannot go anywhere because this is a wall. We already visited this node, and so there are no other ways to go. But from here we still have two ways to go down. So let's mark the values for both of them. So this is going to be 2, this is going to be 2. Once again, from this 2 we have one more way to go, so this is going to be 3, and from 3 we have one more way to go, this is going to be 4. That's it, we exhausted all the possibilities down this path. But over here we still have more paths that we haven't traversed over. So this is going to be 3, then this is going to be 4, this is also going to be 4, then this is going to be 5. So, or sorry, no, this has to be a gate value, so we are not going to do anything. So now we exhausted all the possibilities at this gate. Once again we are going to repeat the same process from this gate and try to fill in the lower value. So if we branch out, this value actually becomes 1 because this value is, and 1 is less than 4, so we are going to put 1 over here. Then this value becomes 2 because 2 is less than the current value we have, so this becomes 2. Then this value becomes 3 because this value is actually smaller than this one, so we can mark this as 3. Now from this 2, if we have to go this way, this becomes 3, but we already have a 2 which is already a smaller value, so it makes no sense for us to go down this path. From this 3 we cannot go anywhere else, so that's it. Now this state actually contains every single possible like distance of empty room to the gate that we have been able to identify, and all we had to do was to use a breadth first search starting at the gate and keeping track of all the graph related principles. So basically keeping track of all the visited nodes and updating the value from the current position, or every single new BFS we make, we simply have to add value by 1, and then we need to branch out in all 4 directions where the given gate is the given cell value is not a gate and it's not a wall, which means any place that is an empty room, we need to calculate that what is the distance from a gate. And if we do this for all the gates, eventually we would left with what is desired from us that we can return. So if we have to understand the time and space complexity in this case, the time complexity is going to be big O of m multiplied by n, but we will have to do this by the number of gates that are present. And if we see space complexity, well, we will have to use a queue in order to do that, and q depends on the number of elements, so it is also going to be big O of m multiplied by n. And this is what we need to return. This is a pretty good time and space complexity, and congratulations, you just learned an awesome LeetCode problem. That is a premium problem, and you didn't have to pay for the LeetCode premium. So anyways, now let's quickly see the coding solution. So this is going to be the solution, and I cannot run this in LeetCode because this is a premium problem, but I would still paste the solution in our GitHub repository so you can check it out from there. So we have our infinite marked as a very large number. Then we are creating a static position called direction to iterate over all 4 directions. Basically this will help us during our breadth first search calls. Now this one is the main method, the walls and gate method, where we are given the rooms as part of the input. We first check for an edge case, that if the given rooms are null, we can return. If that is not the case, we define the values of m and n. Then we also initialize a new queue which we are going to use to do a breadth first search. Then we are going to find all the gates that are currently present inside our given array by using 2 for loops, and we are checking for the value that is equal to 0. After that, we are simply going to do a BFS for every single gate where we are checking that for this particular gate position, what are all the 4 directions that we can explore into. For each of the 4 directions, we are going to check that number 1, we are not going out of bounds, and number 2, if the given value of room that we are reaching to or the cell is actually infinite, then we are simply going to update the value of the distance, and in the end we can simply add that value to our queue as well to keep on updating the distance. So basically we are going to be storing like the smallest distance possible from every single gate, and this is what we need to return in the end. So this solution would work as expected. And now let's I won't be able to run it, but you will be able to find the solution at my GitHub repository, so feel free to check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, Pacific Atlantic water flow. And as you can see that this problem hasn't been asked in too many companies. But the thing is, the companies where this problem has been asked are really one of the most important companies in the world. Google, Amazon, Uber, Microsoft, Facebook, Apple, ByteDance, which is a parent company of TikTok, Bloomberg. So you can understand the scale that why this problem is important and what kind of companies ask this problem. And the thing is, main intention for understanding this problem is to not to understand the actual problem, but rather the approach behind the solution, because that can become a base foundation for too many other problems. There is a lot of information in this problem statement, but if we try to comprehend this using the picture, it's really simple to understand. So I'm just going to go over that. Essentially, we are given a grid like this, and we are told that this is actually an island or somewhere in the ocean. But the thing is, it is at the cross junction between Pacific Ocean and Atlantic Ocean. And the way it represents is that this top and this left edges, they are actually Pacific Oceans, and this bottom and this right edges, they are Atlantic Ocean. So this, and the second information we are given is that all of these coordinates inside the given island represents the height of that particular area. And why the height is important? Because we are told that on this particular island, on this particular grid, there happens to be a lot of rain, which means that rain falls, and we know the property of water that it gets transferred from higher height to lower height. We are also told that that rain at any particular cell can can go to four directions. It can go to top, right, bottom, or left, which means it cannot go diagonal in any scenario. And the condition that if it can traverse from one cell to another cell is that if the height at any particular given cell, if it's greater than or equal to the cell we are trying to reach, then the water can travel to that cell. Which means, suppose we take this cell for an example, the height for this cell is 4, which means if the rain falls on this cell, we can conclude that the rainwater will go to cell 3. It will also go to cell 1 and cell 2, but it would not go to this cell 5 because the height at cell 5 is greater than cell 4, which means that this is cell 4 and this is cell 5, so water can't travel like this. Now, the interesting part for this question is that we need to understand that what are the cells in the given grid that can travel, where if the rainwater falls, it can travel to both Atlantic Ocean and also Pacific Ocean. So let me clean this up a bit. Suppose we consider this cell number 5, and if rainwater falls in the cell number 5, let's see that can it reach Atlantic and Pacific. Like, we know it can reach, but in this cell adjacent to the cell number 5, the height is 3, which means water can go over here. From this 3, the water can go to this 1, and because this is at the edge of Atlantic, of course water can go to Atlantic Ocean from here. Now from this cell number 5, we know that water can also go on this side because the height is 4, and from this 4 the water can go because the height is 2, which is less than 4. And from this is at the edge, which means that at any point, whatever the height over here is, like 1, 2, whatever value, all of that can go to Pacific Ocean. So we can conclude that water from this cell number 5 can reach to both Atlantic and Pacific Ocean. Let's take another example. Suppose we take an example of this value number 4. So we know that from this cell we cannot go over here, we cannot go to 5, but we can go to 2, and from 2 we can go to Atlantic. So that concludes one option. Now let's try to see that can we go to Pacific Ocean. So first, if we try to go on top, okay, we can go over here because this is 3, but from 3 we cannot go to the top because this is 4, so we can't go Pacific in this direction. If we try to go over here, we can reach to this 1, we cannot go to this 7, which means that from this 4 we can go to Atlantic Ocean, but we cannot go to Pacific Ocean, so we wouldn't include this in our intersections. For every single cell, we are going to check that whether it can reach to both Pacific and Atlantic Ocean. If it can reach, we will just maintain a list or some sort that will take care of all the cells that we are able to reach to both the oceans, and we would keep on adding them in this list. So first we'll start with this first element. We know that it can reach to Pacific Ocean, but it won't be able to reach Atlantic Ocean because height over on both these cases are greater. So we wouldn't include this. We would go to next one. So over this, this again can reach to Pacific, but it cannot reach to Atlantic because if it will traverse in these two directions, but it won't be able to go any further over here and over here. Same happens for this one, and basically this solution would work. We would find our answer. Eventually our list would be filled out. Suppose we are at this location 5. So we know that this is at the exact intersection of both the oceans, and it can clearly go to the rainwater can clearly go to Pacific and both Atlantic. So we would add this particular location in our list, and eventually the list will be filled out. But the thing is, the issue with this approach is that in terms of time complexity, we are actually doing a lot of repetitive work, because for every single cell we are checking all the possibilities, and we might end up doing, in the worst case scenario, big O of. So suppose this is M and these are N cells, so we can say that the time complexity would be big O of M multiplied by N squared, because for every single cell we will have to iterate over all the other cells, and this is not a very good time complexity. There exists a better approach. So in order to solve this problem, we are actually going to use a different approach, and the approach we are using is actually, if mountain cannot come to Muhammad, Muhammad will have to come to mountain. And what I'm trying to say is, suppose that rather than checking at any particular cell that whether it can reach both Atlantic and Pacific Ocean, we create two separate grids. So suppose we create a grid and another grid, so two separate matrix of Boolean values that has the same size of whatever the input size we are given. And at any particular location, we just name that okay, this matrix consists the data of all the cells that can actually reach the Pacific Ocean, and this cells contains this matrix contains all the data of all the cells that can actually reach to the Atlantic Ocean. And once we have these two matrices defined, the moment we find that okay, so over here we know that this particular element 3, this can reach to Pacific Ocean. So over here, suppose this value corresponds to this 3, so we will set the value as true over here. And same goes on this side, that suppose we find out that this particular element at position 4 can reach to Atlantic Ocean via this way. So whatever the corresponding value we have over here, we will set that value as true, and eventually we will have the entire matrices filled out. And once we have those, all we need to do is just intersect both of them and find the common elements between both of these matrix, and that would be our final list of matrix that contains all the cells that can reach to both Pacific and Atlantic Ocean, and this would be our solution. Well, this solution actually works pretty fine, it's pretty efficient, and all we need to do is we need to figure out that how we are going to generate these two matrix and what are all the different logic we are going to take. Let's take the most basic approach. I'll be showing you an example that suppose we want to reach to Pacific Ocean, how can we fill out that matrix. Now, what is the most basic thing we know about Pacific Ocean? Well, we know that for this particular island, all the cells that are present in this row and all the cells that are present in this column, they are actually at the edge of the island. Also, they are at the very adjacent to Pacific Ocean, which means all the water in these positions can actually reach to Pacific Ocean in all the cases. So in our matrix, whatever matrix we have, we can basically define all the elements these positions as true, because we know that they can reach to Pacific Ocean. Now previously at any particular location, we were actually trying to go outwards to see if water can reach to adjacent cell or not. But rather than going outwards, why don't we come inwards from the cells we already know that can reach to Pacific Ocean? So over here, these cells we already know that they can reach to Pacific Ocean. So if we check that whatever the cells that are adjacent to these cells from this particular cell that can reach to Pacific Ocean, can we reach to these adjacent cells or not? And the moment we find that okay, we can reach to some adjacent cells that we haven't already visited, so we can set that as true. Suppose the value over here is 3 and we know that this is able to reach to Pacific Ocean, and suppose the value adjacent to this one is actually 6. So we know that since the height difference, there is a height difference, and over here we need to check the reverse height difference. Previously in this approach we were actually checking that whether the height we are currently at and the height the adjacent cell is actually the height is lesser than whatever the current height we have. Over here we are coming inwards, so we will check that whatever the next cell is that we haven't checked, whether its height is greater than whatever the height we currently are at. So in this case this is 3, this is 6, which means that okay, from this cell we can come to this cell, and over here we know that we are coming to this cell from this particular cell that is already able to reach to Pacific Ocean. So over here we can directly mark this one as true, and we won't have to do lot of calculation over here because we already know that this cell is true and we are reaching to this cell via this cell, and this would be a very good solution. And this is how we can actually fill out this entire matrix or like all the remaining portion in big O of m cross n times in just single traversal, because we are not, for any particular cell we are not going to check the whole thing, we are only going to check the cell that is exactly adjacent to it. Suppose we are at this particular cell and we know that this cell can reach to Pacific Ocean, we have already set this value as true. Okay, now we do calculations like this, and suppose before we come over here from this route we have already calculated this and we know that this is already true, that this can already reach Pacific Ocean, and we are at this position and we are checking this again. So first we will already find that whether the value for this particular element has been calculated already or not. If it has been calculated, we don't need to do repetitive work and we can just simply skip over it. That way we can also make some runtime adjustments that would be more efficient on our case. Okay, now we need to find a way to somehow create the matrix that stores the information of all the cells that can reach to Pacific Ocean and also to Atlantic Ocean. In order to do that, at first I thought that we are going to use dynamic programming over here, and the reason I thought is because first of all we are defining a set of all the cases that can reach to Pacific Ocean, so this becomes our base case. Once we have our base case defined, we are essentially going in all the directions to see that if we can reach to next cells, and suppose in this case we are able to reach to this cell from over here due to the height difference, so we will mark this as true, and again from over here we will again do the same thing, and we will, so basically at any point we are using whatever the calculation we have calculated before to generate the next results. So that's a very clear indication that we need to use dynamic programming over here. But it turns out that I was not able to solve it efficiently. I was still missing out in a lot of test cases. So apparently dynamic programming is not the way to go, but I still urge that if anyone can solve it using dynamic programming, I would be more than happy to understand your approach. So second thing I tried to do is okay, in order to solve this we need to iterate over the entire matrix, and in order to iterate over the entire 2D matrix we have basically two methods. We can use either breadth first search or we can use depth first search to iterate over all of the elements and do some calculation. Now I'm new to graph theory and I need to first of all perfect myself on depth first search before I move towards solving the problems using breadth first search. So I chose the approach of taking depth first search, but it can also be solved using breadth first search without any issues. And we know that in order for us to complete this program using depth first search, we need to use recursion over here, and of course we can use recursion because notice that at every single position, so over here first of all we define that this can reach to Pacific Ocean. Now we move on all the directions and over here we find the height difference, so again we know that this can reach to Pacific Ocean because this can reach to this cell, so we mark this as true. And then again we repeat the same process that we have just did, and again we would mark this as true, and again we would repeat the same process. So essentially we are doing the same sort of work but for different inputs, and that's a very clear indication that we need to use depth first search using recursion. And let's move on towards coding now. First of all, we are going to check the condition that if the given input is actually an empty matrix, then we just need to return null. Okay, if that's not the case, let's create two parameters to store the value of row and column. Now we'll create two Boolean matrix to see if to store the value of cells that can reach to Pacific and Atlantic Ocean, and we are going to name that Pacific reachable and Atlantic reachable. And we are going to create both of them to the size of whatever the initial heights matrix we are given. Now we will run a for loop on the for both the matrix to be filled out. In order to fill both the matrix, we are going to create a DFS method, and inside the DFS method we are going to provide the row and column location, and we are also going to provide Pacific and Atlantic matrix. So first we'll do it for Pacific matrix, and we are also going to provide the input heights that we are given. We are again going to call the same function for the Atlantic. We'll iterate using column as well. Now before we calculate the result, first let's create the method. Now inside the DFS method, we will have to iterate over for any particular cell. We will have to iterate over all four of its adjacent cells. So we'll just create a 2D array called directions, and we are going to use it to iterate over all the adjacent or neighboring cells. So we are at this DFS location, which means that we already know that this row and this column pair is already able to reach to subsequent whatever reachable matrix that we are trying to calculate. So which means that we will set that value as true. Now we will start iterating over the neighbors of whatever the current cell we are at, and we are going to create the new row and new column. Now we will have to check that if this new row and new column, are they out of bounds or not. If that's the case, we just ignore that and we continue. We also check that if we have if the new row and column cell if we have that value calculated before, we can also just ignore that case. Okay, if both the cases are not true, we will check that if the height difference of the previous cell and new cell is in our favor or not, which means if the heights for the new row and new column if that is greater than or equal to whatever the previous height was. If that is true, we will need to call the DFS function again with the new row and new column. And this would be our logic for this DFS method, because we are eliminating all the cases and we are also calling the recursive function based on the height difference. So after these four entries run, we should have both of our Pacific reachable and Atlantic reachable matrices filled out, and now it's just a matter of finding the common elements between them. So first of all, let's create a list of lists to store our result, and we'll just name it as result. Just going to iterate over the entire array row and column wise. and we are only going to check that if both the values are true in both the Atlantic and Pacific Ocean cells. So if both are true, we can add it to our list. So after this loop runs, we simply need to return whatever the result we found, and that should be our solution. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code. Okay, our solution also works. It is accepted by LeetCode, but the thing is it's not the most efficient solution. So let's see that if we can do some modifications. And one modification I can think of is rather than calling this DFS system right here and checking this condition all the time, what if we revert the condition, and if this condition is satisfied, we can just return it, and we can just continue before. So that's why loop breaks more times before. And if all of these conditions are not true, then only we will call our DFS function. Let's try to run the code. Okay, the code is working. Let's try to submit the code. Okay, we see some improvement in our code, and now it's a little bit faster than what our previous result was. So I'll be posting this code in the solution. You can check it out from there, from the comments, and let me know how do you like the video. Hello friends, the problem we are going to do today is one of the most versatile, most asked question in the history of LeetCode questions. Like if you just look at the sheer numbers of the amount this question has been asked and the range of companies this question has been asked, it's just mind-boggling. Whatever your dream company might be in the entire world, and if they do good technical interviews, they must have asked this question probably at least 2, 3, 5, 10 times to their candidates. If I only had 10 minutes to prepare for a technical interview, I'm going to choose this question at the top of my choice. Like just look at the companies over here, like Amazon, Microsoft, Bloomberg, Facebook, Google, LinkedIn, Oracle, Apple, ByteDance, which is basically TikTok, DoorDash, Yahoo, Paytm, Walmart, Tesla, Samsung. So I doubt that there are any companies left that didn't ask this question. And the question we are going to do today is number of islands, and I'm going to pay my utmost attention to this problem. Now in the input problem, we are given a grid of m cross n as a 2D binary matrix, and in this particular grid we are all the cells are filled with either values of 1 or value of 0, and whatever the value that represents as value of 1 actually represents land in the real life, and all the values that are marked as 0 is actually water. And we need to find that what are the total number of islands inside this particular grid. Now based on the definition, we know that suppose if we have some sort of body of land, something like this, and if it is entirely covered by body of water, we can say that this particular body of land is actually an island, and that is what we are trying to find in this given problem. Now we are also told one more thing, that at the edges of this particular grid, like all of these values, this is also water, which means that suppose we are given an input like this, where all of these values are zeros, and we only have just one single one over here. This we can also conclude as an island, because on these three sides of the island is already water, and on the outside is also water, because we are told that everything on the outside is also water. So just keep this in mind, that if we find some place at the edge of the grid, we still consider it to be surrounded by water if all the other side inside the grid is also water. And our aim is to find that what is the maximum number of islands that are present inside the given grid. Now this problem is actually pretty simple. Like if we just see over here, like in this particular input, if we try to find for this example one, that how many number of islands there exist, actually there only exists just one island, and that is this one. Because notice this, that these all ones are actually able to be connect with each other because they are adjacent to each other. If for any particular cell, suppose this is marked as 1 and this is a part of land, and any cell adjacent to this cell is also marked as 1, we can say that both of these are a common part of a land because there does not exist anything in between. They are right adjacent to each other, and this is what we are given over here. So in this example, we can only find one island. Now if we take the second example, we can see that there are actually more than one islands. So this is the first island that we can find. This one is by itself, and if we see all four sides of it, this is 0, this is 0, this is 0, and this is 0. So this is also an island, and these two ones, they are also an island. So in this example, we actually have three distinct islands. Okay, suppose we are given a custom example like this, and I have mentioned in my previous videos that it is really important to come up with your own custom examples, because it shows that you can think on your own and you can create test cases on your own. It's a really important skill for any computer engineer to have. Now suppose this is the grid that we are given, and this blue line indicates the body of water we have outside of our original grid. So this is just for understanding purposes. I'm just going to get rid of it now so it does not become an issue, and I can explain the problem better. So we know that there is water outside. Now the most basic approach is that we start traversing through the entire grid in some manner. Like there are bunch of different ways to traverse through the given grid, and we try to see that at any moment if we find one, which means that so far we have find a body of land. Now since we have found this one, we need to see that what are the different islands we can create, and we can create bunch of different islands if all the values are are connected with one. Like no matter how many number of values are connected with any single one, we would mark all of them as just one island, as long as they are connected with each other. And basically what we are doing is we are trying to find separate set of ones. Understand what I'm saying? I will repeat, we are trying to find separate set of ones. So in this example, if we just see that how many different sets we can find, like we can find this one set of 1, we can find this another set of ones, and we can find this third set of ones, and over here we only have one individual element, but still that is a set on its own. Like even if we only have just 1 acre of land, it's still a piece of land which we can consider as island. So that is what we are trying to find. And let me just revert back. Okay, so now we know that what we are trying to find. The most basic approach is we start traversing through the given input array, and we start traversing. Okay, suppose we traverse the first row, we don't find anything. Okay, now again we start traversing over here, we don't find anything. Now at this point we find that okay, there exists an element 1 over here. The moment we find that there exists an element 1 over here, we are going to call our function, and basically what that function is going to do is it is going to iterate over all the adjacent cells, and it is going to keep on iterating till we exhaust all the ones that are connected with this one. So till we exhaust all the sets that are associated with this particular one. So let me just go back a bit, and this is the approach we are going to take. That initially, currently we came to this particular item, we find that okay, there exists a 1 over here. Now because there exists a 1, we need to find all the ones that are connected with this one. So what we are going to do is we are going to mark this coordinate, and once we have this coordinate location, first of all we are going to increase the number of islands we have. Like initially the number of islands we have is 0. Now because we find at least a single one, which means that we have found at least one island, so we will update the number of islands we have. Now since we have already updated the number of islands, and we already have coordinates for this one, first of all we will mark this one as 0. So let's mark this one as 0. Okay, and now from this coordinate we will try to find all of its neighbors to see that there exist any adjacent ones. So over here we find that okay, this one is also 1 and this one is also 1, so we are going to repeat the same process. And remember, we are not going to update our islands in this case because we are still connected with whatever the previous value we had found before. So we are still in the same set of 1 that we were dealing with, so there is no point in updating that, but we have to exhaust all the ones that are connected with this original one we had found before. So we will check over here. Okay, this is 1, so because this is 1, we will we'll change its value to 0, because it now it becomes part of this original set we had. Now again we are from here we are going to repeat the same process. Okay, we don't find any ones from this point, so we are good. But remember, over here we didn't exhaust all the possibilities from our original coordinate, so we still have to do some work. So again we will come back, we will find 1 over here, which means we will have to turn it to 0, so we will convert this 1 to 0 as well. And now from this particular position we will try to repeat the same process. So we will check all of its neighbors, and all of its neighbors in this scenario are now 0, which means we are good. Like we have at least exhausted some possibility, and we have at least found one set of island. Okay, now we will again repeat with our process, and notice that I convert all these three values to zeros because we already found an island over here. And now we will repeat the same process. So again we will start traversing our matrix, and over here we encounter the 1 again, which means now we have encountered a new set of island. So we will update the value in our islands, we will update this to 2. Again we are going to repeat the same process. So first of all we will update this one to 0, and now this is 0. We still have to check its neighbors. We find an adjacent neighbor, again we flip it to 0 first, and again we go to the next element, again we flip it to 0, and now we won't find any more neighbors that are basically 1, which means that again we will start traversing. So we keep on traversing over and over and over, and we don't find any ones. But now we are at this point, again we find a 1, we update our island, so our number of island becomes 3, and now we need to find all the neighbors that are present in this particular island, and we set up all of those values to 0. So these values are set up to 0, and now we check that okay, no neighbor actually has a value of 1, which means we have exhausted all the possibilities of number of neighbors that could be a part of the island. And now again we repeat the same process, and now we find this 1, and this is the last element. So again we increase the number of islands that we have found to 4, and we set this up to 0. And now because we have exhausted all the possibility and we reach to the end of the grid, we can simply return whatever the value we find in the number of islands, and that would be our solution. Suppose we were given an input with all the zeros, like over here we wouldn't have found any island, and we can simply return 0 in that case as well. But this is like a very basic approach, and the approach we took in this scenario is actually depth first search to find the set of ones that are adjacent to each other. Like we could have used BFS as well, but I mentioned earlier, like I'm trying to learn graph theory, and first I'm going to master DFS, then I will start working on the BFS. So that's why I decided to choose the approach of depth first search in this scenario. Okay, and the time complexity in this case would be actually big O of m cross n time complexity, because that is in we have to iterate over entire grid that is given. And the space complexity would also be big O of m cross n in the worst case scenario. Suppose that we are given a grid where all the values are just ones, which means that for any single element we will have to iterate over all the entire grid, and that could be the worst time and space complexity. First, we'll create two parameters, row and column, to calculate the current row and column values for the given grid. Okay, and we'll also create a variable called island, and initially we will set it up to value 0, and we would update this every time we encounter 1 inside the given matrix. And inside the loop we will have a condition that if the current I and jth position inside the grid is actually equal to 1, then only we are going to call our DFS function. So first we'll do island, we'll increase the value of islands, and now we'll call our DFS function. In the DFS we are going to provide the ith position, the jth position, and we'll also provide the grid that we are working on. And once this loop ends, like, we should have all the set of separate ones, and we should have all the values of the total number of islands. So we can simply return the number of islands we have found. Okay, now we need to create the logic to implement this DFS function. So first we'll create a function. Inside the function we will need the values for the row and column again for the entire grid. So we'll just name them new row, and this would be grid's length, and we will also create a parameter called new column. This would be the first position's length. And this is basically the same as finding the row and column we found over here, but we need to use it, so I'm just giving different names. We'll also create a 2D array of called directions. This would make our lives easier and allow us to iterate over all the adjacent values of any current position, and we are going to initialize it with default values. We have this established. First we will put a condition that if the current row and column are they out of bounds or not. We will also put an additional condition that if the current value we are at inside the grid, if that is already 0 or not, because if that is already 0 we won't have to do anything. So if any of these conditions satisfy, we can simply break out of the DFS function, and this would be our terminating case. If this is not true, first of all we will update the current position we are at inside the grid, and will enter the value as 0, because remember we have already updated the islands. And now we will just run a for loop and iterate over all the 4 directions. So that will allow us to go over all the neighboring candidates of this row and column that we have. And now we are simply going to call DFS on row plus direction of 0 and column plus direction of 1, and we'll also provide the value of grid as well. And yeah, I guess this should be our logic, and we can try to run this code. Okay, looks like we messed something up. Oh, okay, seems like our solution is working. Let's try to submit the code. Seems like our solution is also working, but hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do longest consecutive sequence problem, And this problem has been asked in Google, Microsoft, Facebook, Apple, Goldman Sachs, Uber, Twitter, ByteDance. So it's a lot of companies and a lot of huge IT companies that have asked this problem. So I'm going to pay my most attention. I hope you also do it. And I just have one request for all of you guys. Like my YouTube channel, if you see, most of the people, they are not even subscribed, and it takes a lot of time and a lot of effort to make these videos. So I would really appreciate if you can just subscribe. Like basically we are given an unsorted array of integer nums, and we need to return the length of longest consecutive elements inside the sequence. Also, there could be possible that there might be duplicates in our given unsorted array, so we just need to take care of those as well. And let's try to understand this with an example. So the example we are given over here is, and over here, if we find that what is the longest consecutive sequence we can find, the longest consecutive sequence we can make is 1, 2, 3, 4 amongst these values. And we can ignore just this 100 and 200 because there does not exist any consecutive sequence from those values. So over here, since we found 4 elements, we can return the length of this as 4, and this would be our answer. Same way, if we take another example, over here we are given 9 elements, and all 9 elements are actually part of the longest consecutive sequence. So in this scenario, we are going to return 9. So in the brute force approach, we are not going to do anything clever. We are just going to take the most basic approach that we can and try to find the longest consecutive subsequence. So suppose at any moment we are given an input like this, we are given an empty list. We can say that there exists 0 longest common subsequence elements, and suppose we are given an element like this, suppose this is 100, we can say that there exists exactly 1 longest common subsequence element in this given input. So that is a given, right? That even if with a single element, we can at least define that there exists 1 single longest common subsequence element. Now over here in this example, since we know that there are at least more than 0 elements in this given input, and initially we are at this 100th position, which means that we can say that the current longest consecutive subsequence we can find is 1. And now if we want to find a subsequence in the remaining group that consists this 100, how can we do it? Like we can only do it in one scenario, that in this remaining portion, in this remaining elements, if there exists element 101, if this exists, we can say that 100 is also part of the or could be part of the longest consecutive subsequence. So this would be our basic approach, that at every single position we will try to find that whether the next elements could they be in the remaining input, and if they do, we will update our longest consecutive subsequence, and whatever the maximum value we find, we are going to return it as our answer. So we will also create another variable called current subsequence, and that would take care of what is the current subsequence that we are trying to find. Let's just name this current. Okay, and initially the current subsequence is also at also 1 over here at this 100th position. Now we'll try to see that whether this 101 exists in the remaining portion, and it does not exist, which means we will move forward. So we'll move forward with the element 4. Now for this element 4, we need to see that whether element 5 exists or not. So element 5 also does not exist, so we'll move on with just 200. For 200, we will see whether 201 exists. This also does not exist. For this one, we will try to see that whether 2 exists. So 2 exists in the remaining array. Now because 2 exists, the current subsequence we had was of value 1, we will update it to value 2. Now because this 2 exists, we can not break right now. We'll try to find more values. So we'll again try to see that whether 3 exists, and 3 also exists, which is over here. So again we will update this value to 3. Again, because 3 exists, we will try to see whether 4 exists. 4 also exists, and it is present over here. So we will update the current value of longest consecutive subsequence we have found to 4. Now we will try to see whether 5 exists. Now 5 does not exist, which means that 4 is the longest we have found so far, and then we will try to update the value of longest consecutive subsequence we have found to whatever the current value is, because previous value of this was 1 and now this new value is 4. But we are not done yet. We have only checked up until this 1. So now we will check for this 2. So again for this 2 we will, and by the way, we will re-evaluate this value back to 1 because now we are starting with the new element. So again for this 2, 3 exists, so we will update the value to 2, and 4 also exists, so we will update the value to 3. But we cannot update the longest common subsequence because 4 is greater than 3. And now we again check for this value number 3. So for value number 3, 4 also exists, which means that this value would become 2 for this value number 3, but we won't update, and in the end we are going to return this 4. So this is our brute force approach. Like, this solution works, we get the desired answer. The thing is, we get the desired answer at a very bad cost. Like, even if we just try to calculate the time complexity, in this case the time complexity would actually be big O of n cube. Why n cube? Because we will need to iterate over every single elements at least once to find the longest common subsequence. So that is n amount of work. Then suppose over here we are initially at this position 100. So we wanted to check that whether 101 exists. So in order to do this check, we will also have to iterate over the entire loop. So then in that case, we will have to do n more work. And at any given moment, suppose over here we identify that for this 1, 2 also exists, right? And once we identify that 2 exists, we will again check whether 3 exists. Again we will check whether 4 exists. Again we will check whether 5 exists. So even to do these checks, we will have to do n more work. So again we will do n work. So in total we are going to do n times n times n, so n cube work to solve this brute force approach, and this is a very disastrous solution. Now, one better approach we can think of is, suppose that with the given input, if we do some sort of modification, can we come up with better solution in faster time complexity? Like, of course we can. So remember that what we are needed over here is that we need to find the longest consecutive subsequence of this given input. And we are going to see with this custom example how can we modify the input and how can we come closer to solution. So suppose in this given example, rather than keeping the input just like this, if we do sort the given input, things become much easier for us. And let's see that what would be the sorted result. Okay, so now we have our sorted result. Now in the sorted result, we simply need to find that what is the longest common subsequence that exists, longest consecutive subsequence that exists. And it's pretty simple to find now, because all we need to do is that at any point we know that the definition of common subsequence is that, suppose we are currently at the value I, then I plus 1 would be a common subsequence, then I plus 2 would be a common subsequence, and this is the only condition we have to take care of. And the only other thing we need to worry about is having two duplicate values right next to each other. If at any point we encounter two duplicate values, we simply ignore one of those values and move forward. So in this example, we are only going to do two checks with the sorted input. First check we are going to do is, at first position we are going to check that whether this position is exactly same as whatever the previous position we had. If that is true, we would skip over because we don't need to do anything with that, because there are two same values. And if that is the case, so which is the case in this scenario, that both values are same, which means we would skip over. So we would go to the next element, and now we are at this next element. Again we are going to check that the value we are currently at and the value before that, if they are same or not. So in this case they are not same. If they are not the same, we are also going to check one more thing, that whether the current value of a of I, so suppose this 0 is actually a of I, and minus whatever the value of a of I minus 1. So a of I minus 1 in this case is minus 1. So if difference between these two values, if it becomes exactly 1, which means we can conclude that these two values are part of the longest common subsequence, and we could update their value. Again like brute force, we are going to use two variables. One variable to keep track of longest common subsequence we have found so far, and second one is to keep track of the current subsequence that we are working on. So let's see that how it would work. And both the values would be set up as 1 initially. Now initially we are at this 0 and 1 pair, and because they are sorted, we know that they are always going to be adjacent to each other. So this is the only condition we need to worry once we identify that the both values are not same. So in this case we can say that the current subsequence we have found is actually size 2. So we can update the value over here, that this is 2. Now again we check with this value. Now this value again it's 0, it's the same as this one, so we ignore it. We don't need to do anything. Now again we check with this value. So this value is actually 2. Now with this 2, if we put down this equation, so 2 minus 0, this is not equal to 1, which means that this 2 and 0 are not part of the common subsequence. If they are not part of the common subsequence, we check that now we can't update this current anymore. So we check between the current and longest common subsequence we have so far, and the current is actually greater, which means we will update the longest consecutive subsequence to 2 as well. And now current we will put it back to 1, because we will repeat our search again. Now we are at this position 3. So 3 and 2 are not same, and 3 minus 2 is actually 1, which is true, which means we update our current. So current would become 2. Now we are at this 4. Again 4 minus 3 is equal to 1. So again we update our current to 3. Again we are at this 5. So again we need to update our current. So current would be updated to 4, because all of these values 2, 3, 4, 5, they are in a common subsequence. Now we are at the 7. So 7 minus 5, they are not equal to 1, which means we can't update the current. So we will need to reset the value of the current. So before resetting the value of the current, we are also going to check that whether the longest common subsequence needs to update, and this needs to be updated to value 4, because this one was 4 before, because of these 4 values. And now we can set this value to 1 again at this position 7. And now we are at this position 200. So 200 and 7, they don't have any correlation, so we can't do anything about it. And in the end, at the end of the loop, we are simply going to return whatever the longest common subsequence or current subsequence, whatever the maximum value we have found between these two. And in this case, the maximum value we have found is actually 4. So this would be our solution. Now this solution works pretty efficiently, it's pretty neat, and if we see the time complexity, we can complete everything in just one single iteration. So we are only doing n work, but the thing is the time complexity in this case would be go of n log n, because initially remember that from this given input we will actually have to sort the array as well, and sorting takes n log n time. But overall, if we still compare it with whatever the brute force approach we had, brute force was actually big O of n cube. So this was really bad time complexity, and this is much more and much bigger improvement upon our scenario. Now in the optimal solution, we are actually going to try a couple of things. First thing we are going to do is we are going to create an additional data structure called hash set, and in the hash set we are going to enter all the values that we have found from this array. So suppose we create a hash set something like num set. Now in this hash set we are going to add all of these values. Now because we have our hash set ready, what we are going to do is when we are going to iterate over this hash set, and we are only going to start checking for the longest consecutive subsequence from the elements that could be at the start of the longest common subsequence. And what elements can be start of the longest common subsequence? Well, so if we take this example, we can actually see a couple of common subsequences or consecutive subsequence. One consecutive subsequence we can find is 99 and 100, which is at these two positions. And second consecutive subsequence we can find is actually 1, 2, 3 and 4. Now in what we were doing in the brute force is we were checking at every single position that what would be the longest common subsequence we can find. The thing is we can only find the longest common subsequence from the first element of the start of this consecutive subsequence. Same goes over here, that whatever the subsequence we can find at this value number 100, the subsequence that we can find at value number 99 would always be greater than whatever we can find over here, because this by itself is already a subsequence. So we are going to use this logic. Like over here, if we put this 3, 2, 3, 4, we will only find the consecutive subsequence of length 2. But this 2, 3, 4 would be of length 3, and this 1, 2, 3, 4 would actually be of length 4. So we can only find the maximum consecutive subsequence at the start of the any subsequence, not somewhere in the middle. And the only way to check that whether we are at the start of the subsequence or not is by just checking one very simple condition, that at any point we check that whether the exact value before that value, like one value before the value we currently are at, if that exists, which means that we are not at the start of the common subsequence. Let's take it by an example over here and let's see that what would be our approach. So first of all, we are going to be at this position 100. We are going to check that whether this 100 is a start of any consecutive subsequence or not. So we check that whether in this given num set does the value 99 exist. Now we know that 99 exists. So because 99 exists, 100 cannot be at the start of the common consecutive subsequence. So we are going to ignore this case. We don't have to do anything with this 100. We come up at 99. Now we come up at this 99. We check that whether there exists a value before 99. So 98, does it exist in this num set? 98 does not exist, which means that at 99 we can be at the start of any common consecutive subsequence. So we start a subsequence at 99, and now we will initiate our logic. And in our logic we are simply going to check that from this 99 how many consecutive numbers we can reach. So we are going to check that, okay, 99 by itself is a common subsequence of length 1, so we know that. Now from this 99 we are going to check that can we reach value number 100. So 100 we can reach, and because we are using a hash set, we can do all the operations in constant time, so we are not adding any strain in our time complexity. Now we can find the value 100, so we can reach 100, which means that the whatever the longest common subsequence that longest consecutive subsequence we found, we will increase its value to 2. Now again we will try to see that whether we can find 101. Like 101 does not exist, which means we would break out of over here, and the longest common subsequence we have found up until this point is actually of length 2. Again we are going to repeat the same process. So now we are at this position 4. We check that whether 3 exists in this set or not. So 3 exists, which means we ignore this 4. Now again we are at 200, so we check that whether 199 exists. So 199 does not exist, which means 200 can be start of the any consecutive subsequence. So we again check that whether 201 exists, but 201 does not exist in this given example, so we ignore this 200 as well, because the longest consecutive subsequence we find at this value number 200 is always going to be 1, and we already have a value that is greater than 1. Again we check at this position 1 that can 1 be start of any consecutive subsequence. So we check that whether the 1 minus 1, so we check whether 0 exists in this example or not. 0 does not exist, which means 1 can be start. So now we set our current subsequence to value number 1, and now we check that from this value 1 how many other values we can reach to. So first we check that can we reach the value number 2. Yes, we can reach value number 2 because 2 already exists. So we update whatever the current subsequence we can find to 2. Now from this 2 we check can we reach 3. Again we can reach 3, so we will update the current value to 3. Again we check that whether from this 3 can we reach 4, and yes, we can reach 4 as well. So again we will update the value of our 4, value of the current subsequence to 4, and from 4 we check whether we can reach 5. So 5 we can't reach, which means we are at least able to reach this 4. So we are able to see that the current the longest current subsequence we have found is 4, and previous value was 2. So we will update this, so this will become 4. And now again we are going to check the same thing for this value number 2, so that for value number 2 does 1 exist, and 1 exists, so we will ignore this. Again we check for 3, does 2 exist? 2 also exists, which means we are going to ignore this 3. And now since we have reached the end of this hash set, so we are going to reach whatever we found in the as the longest consecutive subsequence, and this would be our answer. Now if we calculate the time complexity would actually be big O of n in this case, because we are only iterating over the entire input just once through this hash set. So this is a very efficient time complexity. And if we see the space complexity is actually big O of n, because we will have to create this additional numerical set, and we are going to store n memory for that. And let's see the coding. I would be showing the hash set solution in this code, but I'm going to post both the codes in the comments so you can check it out from there. So first of all, we are going to check that whether we are given an empty list or not. If that's not the case, first of all, we are going to create a hash set. We are going to name it num set. Now we'll run a loop across the given input, and we are going to store all the values to our hash set. This is going to do two things. It's going to eliminate all the duplicates values, and it will only add unique entries in the hash set, because hash set has a property that does not allow us it to store duplicate values. Now we are going to create a parameter to store the longest subsequence, and we are going to initialize it with value 1. Now we are going to run a for loop across the given num set. So initially we are going to check that whether we are starting from the middle of any longest consecutive subsequence. If that's the case, we are going to ignore that number. So if this condition is true, we are going to continue and go to next element in the loop. If this is not the case, we are first of all going to mark the number we are at as current number, because this is the beginning of any longest consecutive subsequence. We are also going to create another parameter called current sub that is going to take care of the current maximum consecutive subsequence we can find, and we are going to initialize it to 1. And now we are going to put a condition that while our hash set contains the current number plus 1, while this condition is true, we are going to increase the number, and we are also going to increase our current subsequence. And after this loop ends, we need to check that whether we have found the longest common subsequence or not. So once this loop ends, we should have our answer in the longest sub variable, so we can simply return that. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit the code. And seems like our solution works pretty well, and it is faster than a lot of other solutions. I will also post the sorting algorithm solution as well, so you can check it out from the comments. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do alien dictionary lead code problem, and not only it is a very important problem, this problem can actually be asked in multiple ways. It can be asked directly as a graph question, or it can be asked as a follow-up question for the previous question that we solved, verifying an alien dictionary. Because both questions are very similar, and if you want to check that where the solution for this problem is, you can check it out from over here. Also, another reason why this problem is really important is if you just take a list of companies that have asked this problem: Airbnb, Facebook, Google, Amazon, Bloomberg, Microsoft, Uber, they have all asked this question in last 6 months. Also, IT giants like Pinterest, Apple, Twitter, eBay, they all have asked this question in last 6 months to 1 year. And ByteDance, Snapchat, and Flipkart, so they have asked this question not fairly recently, but still it's important. And I will be paying my utmost attention, because my aim is to clear any FAANG interview, and I hope you also enjoy the video. This is a LeetCode hard problem, and it justifies this hard tag. So let's understand the problem statement. Essentially, we have identified a new alien language that uses English alphabet. However, the order of those letters is unknown to us. Now we are given a list of strings inside this words, and we are told that they are from this alien languages dictionary. And in that string, The important property these words have is that they are sorted lexicographically. And we need to return a string of unique letters that are present in these words, and we need to return them in lexicographically increasing order. Now also there could be possible that there might be multiple solutions. So if there are multiple solutions, we only need to return any one of them. And there could be some cases where this given string of words is invalid, and if it is invalid, we need to return an empty string. So in order to understand this problem, first of all, we will have to identify that what does this lexicographically increasing order means. The second thing we will have to understand is that what are the cases where this particular input is going to be resulting in falsified information, and what does this string of unique letters with lexicographically increasing order means, because this unique word is actually really important, and I'll come to that later. So suppose if we just talk about what is lexicographically sorted means, if we talk about English language, if we talk about the words A, B, C, D, all the way up to Z, this is plain English language that we use on a day-to-day basis. Now in the English, suppose we are given any four letters. Suppose we are given letters like Q, A, E, B, R, C, and Q, E. Suppose we are given letters like this, right? And if we want to sort these four in plain English language, how we are going to sort them? Like, of course, the answer is simple. We are only going to check that what is their position in this given order, and based on that particular order, we will sort them. So if we sort them, the sorted result would look something like EA, QA, QE, and RC, something like this, right? And the reason we are able to generate this is because we know that the position of E comes before Q, and in this case there are two entries QA and QE. So which means, like, if we will have to identify that what is the second letter, and second letter A comes before E, and then this R actually comes before Q. So we are able to determine a sequence like this. Now in this given problem, we don't need to generate a sequence like this. Basically we are told that we are not given this information. We don't know that what is the order of words are, and we are directly given this particular sequence that is already sorted in that particular language. So suppose this was to be alien language, and if we want to identify that what should be the answer we need to return in this case, the few things we can determine from this input is that, okay, over here we are checking first, at any point we are checking any two adjacent words. In those two adjacent words, we go letter by letter, and we try to see that what is the first differing letter that comes to the existence, and based on the differing letter, whatever the word is presented first should come first in that order rather than second letter. So if we compare these two words E, A and Q, A, we can see that the first differing word comes as E, and over here it is Q. So which means we can determine that E will always come before Q in this particular alien language. Now don't forget this, that this is plain English. Just imagine this as an existing scenario. So we know one scenario, okay, that E should come before Q, right? Now over here again, if we compare next two words, the next two words are QA and QE. Okay, so in QA and QE, notice that the first letter is Q, so it is common, which means we cannot identify much information from that. But the second letter is A and E, which means we can determine that at any given scenario, A will always come before E. So we can notify that, we can also create a scenario like that, that A will always come before E. And over here I am denoting this relation by an arrow, which indicates that at any given moment E should always come before Q, because it is on the beginning end of the arrow, and the where it is pointing to should comes later. And again we will compare these two words QE and RC. So if we compare these two words, we can identify that, okay, Q should come before R. So we can also denote that relationship, that Q will become will be before R, right? And over here now we have these three relations. So based on these three relations, we can actually establish something over here, that we can establish that A will always come before E, and E will always come before Q, and Q will always come before R. So one of the sequence that we can return over here is that A, E, Q, R. Okay, so this is one of the sequence that we have to maintain at any given cost, because we are given these conditions based on the words that were given. But the thing is, will this be our answer? And actually this will not be our answer. And the reason this will not be our answer is because over here we are given this particular line that we need to return a string of unique letters from this words in the new alien language, that is lexicographically increasing order. But the thing is, over here if we look the original input, in the original input we actually have one more unique character that we are missing, and that particular unique character is, so we already took care of E, we took care of A, we took care of Q, A, Q, E, R, all of this we took care of, but C, the letter C, we did not take care of it. And the thing is, over here based on whatever the input that we were given originally, we cannot determine the position of C. But the thing is, we know that C is also a unique character, and the only thing we know about the positioning is that for these four characters we can define some positioning like this. For C we cannot determine any positioning, but the thing is it has to be part of the answer as well, and that is why we are told that there could be multiple solutions and we need to return any of them. So in this scenario, this could also be a solution where A, E, Q, R and C we are placed at the end, or this could also be a solution where A, we put C somewhere in the middle, and E, Q, R is also placed like that. The important thing is that we need to maintain this order. As long as we are maintaining this order, because this C is one of those unique letters where we cannot find the dependency for that, so we will need to take care of it as well. And this is a very important detail that lot of other videos have missed out, and that is why it took me a lot of time to make this video. I want to make sure that I go through it completely. Now let's take one more example from the given input, and we will again try to find that what should be the answer for that. So in the given input, we are given the following words. These are the words that we are given in the alien dictionary, right? And our aim is to find that what should be the answer in this case. Well, the first thing is that what we are going to need in order to generate the solution. In order to generate the solution, we are going to need two things. We are going to need list of all the unique characters that exist, and second thing we are going to need is what are the dependency on all between characters. And based on these two things, we will try to generate some sort of order or some sort of pair. And also remember that we will have to consider the scenarios where we could find invalid strings as well. So I'll be explaining that in this example. So over here, if we see the list of unique characters, the unique characters are W, R, T, F, E. Okay, these are all the unique characters that we can find in this particular input. Okay, now let's start making dependencies. Now in order to make dependencies at any given moment, we will have to compare two adjacent words, and we are going to find first differing character, and based on the differing character we are going to establish some dependency. So first of all, the first two words we are going to compare are WRT and WRF. Okay, in this case W is common, R is common, which means that first differing character is T and F, and we already know that these words are sorted. So because they are sorted, we can determine that T should come before F. Okay, we already know that. This is good. Now what are the next two words? Next two words, and we are done with this WRT. The next two words are WRF and ER. Okay, so WRF and ER. Now in this case, what is the first differing word? Well, the first differing word is first letter by itself, W and D, which means we can make another dependency that W should always come before E. Now we can ignore this. Again, we compare next two words. So ER and ETT. So over here, what is the first so EE is common. The first differing letter is R and T, which means that R should come before T. Next one is ETT and RFTT. So over here, the first differing character is E and R. So we can also mention that E should always come before R. Okay, now we have these four dependencies for these 5 unique characters. Now let's try to create a dependency tree from this given input. So if we see, we can clearly see that, okay, W is dependent on E, and E, so W comes before E, then E comes before R. Okay, then for R comes before T, and T comes before F. So this becomes all the dependencies, and if we notice all the unique characters, they are already part of these dependencies, so we are good. We don't need to do anything more over here. Now if we make that what should be the order of letters, the order of letters in this case would be W, E, R, T, F, and this would be the correct solution. Now notice that in order to generate the correct solution, what we had to do is we had to find all the unique characters, all the dependencies. Once we had all the dependencies, we actually had to iterate over all the dependencies, see that which dependencies are interconnected. Based on their interconnection, we actually had to generate this order. And in order to do that, we are actually using graph theory. And how we are using graph theory is basically all the unique characters in this case are actually nodes, and all of these dependencies are actually edges between those nodes, and those edges can be represented as in some form of adjacency list in some sort of hash map, and then we will need to iterate over all of the entire graph, and then at any moment we will have to go through the graph and find the solution, that what should be the order in which we are able to iterate over all the unique characters, which means that all the nodes inside the graph, and we need to generate this order of pairs. And if we are able to successfully generate this order of pair, we will return whatever we find, and if for somehow we find out that the input is invalid, we will have to take care of that scenario as well. So first let's take a couple of examples where we can find that the input could be invalid. Now based on the English language, we know that at any given moment, if there are two words present, W1 and W2, and we know that any single word, so suppose W1 is actually prefix of this W2, if that is the case, then W1 should always come before in the dictionary than W2. Let's take it by an example. Suppose we are given two words like bat and Batman. If we are given two words like this, so if we start comparing these two words and see that what should be their order, we check that, okay, B is common, A is common, T is common, right? Now over here, this actually ends. There is actually an empty list. There is nothing over here. While over here, there are still some values. So if that is the case, we can determine that this W1 is actually prefix of this W2, because these three characters are also present over here. And in that scenario, this W1 should always come before W2. At any given moment, we identify that this particular character is not present in correct manner, and suppose we are given an input like this, that Batman and bat. If we at any moment encounter this scenario, we can immediately return false, because, or we can immediately return an empty string, because this is a wrong ordering. So this is one of the failed scenarios where we cannot do anything, right? So this is very important to understand, and we will have to take care of this in our solution. The second thing that will not work is that at any given moment, suppose we are given list of words, suppose the words are like X, A, B, X. Suppose we are given list of words like this, and what this means is that the first letter X should always come before A. Okay, so based on these two, we can establish this dependency. Based on these two, we can also establish that A should always come before B. Okay, and over here the next thing is that B and X, which means that what this is saying that B should always come before X. So if you notice over here that we are actually stuck inside a cycle, that X needs to come before A needs to come before B, and B needs to come before X. So at any moment in our graph, whenever we are traversing over all these unique characters and dependencies, at any moment we encounter that okay, there exists a loop, and if we detect that there is a loop from any particular node, then we can return false immediately, or we can say that okay, this is an invalid case where the string actually doesn't exist and we will need to break out of the loop. Suppose we are given a custom example like this, words, and we are told that all of these words, they are lexicographically sorted in the alien dictionary, and now we need to return the order of words of all the unique characters that we can find. So what should be the approach? Well, in order to do that, we are going to need two things. First thing we are going to need is all the list of all the unique words or all the unique characters, and we are also going to need the entire dependency between any two letters, that which should come first and which should come later, right? So let's start working on it. So first of all, we have B and A. Okay, so we will just add list of unique letters B and A, and second word is by, which means that first differing characters A and Y. So we can establish a dependency like this, that A should come always before Y. Okay, now again moving forward with next two values. So over here the first differing character is B and A, which means that B should always come before A, and also I forgot to add one more unique character Y over here, right? Now this B should come before this A, so we will add that to our dependency list as well, that B should come before A, right? So this is one dependency, and over here we have the unique character D, so we will add the unique character D as well. Now we have this another word, these two words, and in these two words A is common, which means that D and L are differing characters. So first of all we will add the word L over here, and over here we have this D, right? So we know that D at any given location will come before L. Okay, so we'll just mention that. Now over here we have one more unique character T, so I'll also mention that. Now the next two words are these two words. Over here the A is common, L and I are different, and also we have one more unique character I. Now we know that there is a dependency between L to I, so we will also mention that L should come before I. Now the next two words are AI and AIR. Now notice over here that this AI is actually prefix of this AIR, right? Which means that this AI will always come before this word AIR, but we cannot determine anything regarding this R, because this R by itself, it has no other thing to compare its result with, which means that though we have a unique word, we don't know that what is the intention for that particular word is. And now let's see that in the dependency list that we have created, amongst these unique words, what are all the words that we are able to find a pair for. So one pair we were able to find is for this one, this BAY. Let me just draw everything in same color. So BAY, this is one pair, which means we know that at any given moment this BAY order has to be maintained, like B always has to come before A and Y. And same goes for this DLI, that D always has to come before L, and L always has to come before I. But in the list of unique characters, we are given this R and T as well, that are not represented by any dependency, which means we can say that this R and this T, they are unique characters by themselves, which does not have any sort of dependency, right? So if we want to see that what could be the potential different pairs we can make over here, well, there could be bunch of different results. Like there can be so many different permutations and combinations. Let me just give you a few of them. Like most simple one would be BAY DLI RT. So this is one combination where notice that we are just maintaining the entire order. Now second combination could be B D A, L, Y, I, R, T. Now notice over here that at any given moment we need to make sure that these two orders are met up. So B is always coming before A and A is always coming before Y. So that is satisfied. Over here D is always coming before L and L is also coming before I. So that is also satisfied. This RT, they don't have any dependency. So it doesn't matter. We could have some pair like this, that B, R, T, D, A, Y, L, I. This is also a valid pair because notice that this B, A and Y, this is maintained. This D, L and I, this is also maintained, and this position of R and T doesn't matter. So there can be a bunch of different options that we can choose from, and I'm just showing you that these are the different results we can have, right? Because we need to take care of unique characters as well. So don't forget the unique characters, they are really important. Now, what should be the approach in this case? Well, one approach is actually quite simple. Because we know that we have unique characters, we have the dependency, we can choose some data structure like hash map. We can iterate over at any point whenever we identify the dependency, we can iterate over the entire hash map. We can, from any point, we will try to see that whether it has any dependency or not. If it has dependency, we will go to that dependency, we will try to iterate over those values, and we will try to generate the order list, right? So let's see that how it can work. Suppose we create a hash set like suppose we create a hash map like this. Okay, suppose this is our hash map, and based on these dependencies we know something, that we know that okay, for in order for us to put down this B, we know that A has to come after B, which means A has dependency on B, right? We will mention it over here. Now for this A has to come before Y, so A has to come before Y. Now for this Y, we don't have any dependency, so we will just leave this value as blank. Now for this particular D has to come before L, right? So we will just mention L over here. Now this L has to come before I, so we will just mention I over here. For this I, we don't have any dependency, so we are good. And same goes for this T and R, that we don't have any dependency, so we are good. Now since we have this dependency tree, let's see that what would be the approach we can take over here. So in this scenario, suppose if we want to calculate that what would be one of those ordering pair, what we can do is we will start traversing through all of these values, all of these unique characters. And remember that this is hash map. So in hash map, we are treating these as key values, and these are actually values. So in the keys, we are mentioning all the unique characters. In the value, we are mentioning all the dependencies. Now over here, we will start iterating at this B. So first I'll just mark B as that we are iterating over it, right? Now from this B, we identify that okay, we need to have A before B. So again we go to A, because we will have to check all the dependencies, right? We cannot just put any letter randomly any place, right? Because this B has some dependency, so we will have to go over that. Now this A has actually dependency on Y, so again we will go to Y and we'll just mark A as being as part of being visiting. And over here we reach at this Y don't have any dependency, so we are at this Y. Now notice that we are actually traversing this graph in DFS manner, depth first search manner, right? And in depth first search, at this Y we identify that okay, this Y does not have any dependency, so we can just put Y to our order list. So we can just put Y to our order list. Now from this Y we will do a backtrack, we will again come back to A. Again we will do a backtrack, again we will come back to B, and then we would be done with this B, right? That okay, we are done with this. Now again we ignore all of these. Now we start with this second position. Now in the second position, first we determine that whether we have calculated this value already or not. So since A is already calculated over here, so we ignore that, so we can ignore the second case. Again we check that whether this Y we need to calculate it or not, but Y we have already calculated, so we can ignore this, right? So we will ignore this, and now we'll move on towards this D. Now do you see any problem with this one? Well, definitely we are seeing a problem with this one, and the problem is that over here the dependency is like this, that B has to come before A and A has to come before Y in order for us to generate the dependency order. But over here, when we started traversing, the actual dependencies we are getting is actually in reverse order. You see that y comes before a and a is coming before b. So one way we can do it is that we can start traversing like this one, that over here we again come to this d. For this d we find a dependency as l. For this l we find a dependency at I. For I we don't find anything, so we'll just put I over here. Then we backtrack, so again we put l over here, and then again we backtrack, and then we will put d over here, and then we come to this t, like this I, this l, and this has already been done, so we ignore that. We come to this t does not have any dependency, we put it there. I has already been processed, and we reach at over here at r. Now this order list we got is actually correct, but in reverse order, because the dependency should be like b a y, and this should be d l I, but over here it's d l I in reverse order, and same goes for b a y. So what we will have to do is when we calculate the answer, we will have to return the reverse of this answer, and that would actually satisfy these dependencies. So that is one way of doing it, right? And there is also another way of doing it, and the better way is that when we are actually creating this hash map, we can actually do something different. Previously in the hash map, what we are doing is that over here we had a key as all the unique characters, and as the value we had these dependencies exactly as they were mentioned, that for this particular b it is dependent on a, for this particular a it is dependent on y. But the thing is that is not true. The actual true thing is that actually this y, the position of y should be dependent on a, that y cannot be present unless there exists an a value before that. If we start, so if we, rather than storing the dependency on value that is taking care of the value that comes after it, if we start taking care in reverse order, so let me show you what I mean by that. So suppose if we have a hash map like this, and over here in the value we actually present at any given value what should be the previous value that has to be present in order for us to reach at that particular value. So what that would do is that if we want to calculate this b, we don't need to basically have any value, right? So over here we will leave this as blank, that for b we don't have any dependency. But for this particular a, we actually have dependency on b, that b has to be there in order for us to process this a. So we will put a dependency over here saying that okay, b needs to be there for us to calculate this value a. Same goes for y, that a needs to be there in order for us to calculate this value y. Again we reach at this d, and for the d we don't have any dependency, so we'll just leave it blank. But for this particular l, again we will have to have a d over here, so we'll put a d over here. For this t we don't have any dependency, so we can leave it blank. For this particular I, we actually have to have an l before that, so we'll put a dependency over here. And for this r we don't have any dependency, so we'll leave it blank, right? So this is the table this is the hash map that we work with. And over here now let's try to iterate over this hash map. Essentially our aim is to iterate over this entire hash map, identify that at any point if you are inside the DFS function you are not finding the repeated character, so that is item number 1. Second thing to make sure is that you go through all the characters and you start building up the order list. So over here we will get, we initially start at b, and at b we don't have any child, so we are good to put b over here. Now next and we can mark that b is already done. Now we are at this a, so for a we need to check that whether b is done or not. B we check over here, b is already done, so we are good, which means that we can put a over here. So we will put a over here. Again we will mark a as being done. Again we are at this y, we check that okay, y has dependency on a, so we check okay, a is already done, so we can put y over here as well. Now we are at this d, so d does not have any dependency, so we can just simply put d over here and we can just mark this as done. Again from l we check for d is already marked, so we put l over here. T does not have any dependence and we mark l, t does not have any dependency, so we mark t is done, we can put it over here. Now this I has dependency on l we have already marked that it is done, which means we can complete this I as well. And for this particular r, it does not have any dependency, so we can put it over here. Now if you notice this scenario, we are actually fulfilling both of these dependencies. And notice that this B comes before A and comes before Y, so we are good with this dependency. This D comes before L and I, so we are also good with the second dependency as well. And this T and R, they were actually separate values, so it doesn't matter wherever we put them, as long as they are there, it fulfills our purpose. And this is the actual solution that we need to take care of, that where initially we will iterate over all the words, we will create all the unique characters. Based on the unique characters, we will create the dependency list. Based on the dependency list, we can actually create a hash map that we are going to use to traverse as a graph. But thing is, rather than traversing the original hash map, we can actually create a reverse list of dependencies, and we can iterate over that just once using DFS or BFS, anything, but we are going to use DFS because I want to master DFS for myself. And that would be our solution. So it took me a lot of time to come up with this solution. It took me a lot of time to understand this problem. Okay, let's calculate time and space complexity for this problem. So the time complexity for this one is going to be big O of C, where C is actually total number of characters that are given in this original input words. Because notice that there are actually three parts of this problem. The first part is that we need to find all the unique characters. Like in order for us to generate all the unique characters, we will have to iterate over all the characters that are given in the original input words. So that is one part. Now second part is that we need to create a dependency, and in order to generate the dependency, again we will have to traverse all the words. And the third part is that we will have to so we are generating some sort of hash map, and inside the hash map we will have to iterate over all the values inside the present hash map. So at any given moment, the maximum work we are doing is iterating over the sum of all the characters that are given inside this words. So that is why that would be the time complexity. And if we want to calculate the space complexity, the space complexity would actually depend on the number of unique characters. So suppose that in English language, the number of unique characters maximum we can have is only 26, right? And we are also told that for this alien language, the maximum number of unique characters we can have is also going to be 26. So space complexity actually has a finite number, and there is only so much it can grow. So we can treat space complexity to be big O of 1 or constant space complexity for this one, even for us to creating this additional hash map. The second thing is that suppose if we want to calculate based on the number of unique characters, there is also one equation where the space complexity would actually be big O of U plus whatever the U square or N, whatever the minimum value of this is. And let me know in the comments if you want me to explain the space complexity in a scenario where the number of unique characters are actually not finite and not 26. Like in this case it's 26, so I will just leave it as it is, but let me know if you want me to explain that. First of all, we are going to create our hash map, and we are going to actually create it outside of this alien order method that is given, because we want to use that hash map to our DFS method as well. So, and as a key we are going to use unique characters, and as a value we are going to use the dependency. So it would be list of characters, and we are going to name it reversed list, because essentially we are just reversing the adjacency list. Also we will create another hash map to essentially store the value of any parameter that we are already currently visiting inside our DFS method. And we'll need to create an output of strings, so we can create a string builder variable. Now the first thing we need to do is find all the unique letters inside our given string of words. Now this is done, Now we will have to find all the edges, and we will have to add the reverse edges to our reverse list hash map. Now at any given moment we need to check that whether the word 2 is actually prefix of word 1 or not. If that is the case, we can return false immediately, and we have found a terminating case where the given string of words is not valid. Okay, if that's not the case, we will find the first differing character between two words and add it to our hash map. And notice that we are actually adding the value to the to the second word's differential character. And the moment we find the first differing character, we can actually break out of that particular word. Now we are going to iterate over the reverse list hash map that we have created, and we are going to run our DFS function. Okay, for all the keys present inside the reverse list hash map, we are going to run the DFS function, and we are also going to check that at any given moment have we receiving the result as false. So we are just going to create a boolean variable result, and now we are going to call the DFS function, and we are going to provide the character inside the reverse list. And at any moment, if we identify that the result is for this result character is actually fault, we will return empty list immediately. Okay, now all we need to do is that once this DFS step runs, we should have our output inside the result. So we will have to check that whether all the unique characters have been taken care of or not. So we are going to check that whether the length of output, if that is less than the size of our list, if that is the case, we can return false immediately, because we haven't taken care of all the unique values present. And if none of these cases happen, we will return whatever we find inside the output. Now the only thing we need to do is we will have to create the DFS method. Now first of all, we are going to check that whether the current character C we are checking, if we have already visited that or not. If we have already visited that, we are simply going to return false. If that's not the case, which means first we'll add the current character to our scene hash map, and we are going to mark the entry as false, so that way whenever if we encounter the repeated value, it will always return false. Otherwise by default the value would be true. Okay, now for every single character inside the current for the given character, we will iterate over inside the reverse adjacency list. And at any point if we encounter the result false, we will return false immediately. If that is not the case, we will remove the entry from the scene hash map. So we'll set the entry as true, and inside our output string we will append the value. And for that particular character we are going to return true. Okay, so I know this is a very long and too many lines of code. I'm going to put this in the comments. Let's try to run the code. Okay, seems like our solution is working. And also remember, I was talking to you that we will have to take care of all the unique characters. Here, let me show you an example. So suppose we only have two characters, H and P. If we are only given input like this, and we know that H comes before P, right? Which means that in the result we should be getting HP. So let's see that what, okay, so this is accepted, right? But now let's say that we have additional character HA and PB. Now over here we don't have any mechanism to measure this A and this B, so they become unique characters, right? And now let's try to run the code for this particular test case. So if we do that, you are going to see that A and B would be at weird locations. So over here, see, the important thing is in our output we are maintaining the order for this H and P, and that is what it matters. Like A and B over here in our output is actually behind this HP, while over here the A and B are actually at the beginning, and then there comes HP. So it doesn't matter as long as the order that is given in the input is maintained. And now let's try to submit this code. And oh wow, our solution is actually 99% faster than all the other solutions. And I used lot of help from the solutions tab from this LeetCode Premium, because it took me a lot of time to understand this problem. So I'll be posting this in the comments. You can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do a very important LeetCode graph problem, graph valid tree. Basically we are checking that whether the given graph is actually a tree or not. And this question has been asked in a bunch of different top tier companies, companies like LinkedIn, Google, Amazon, Bloomberg, Microsoft and Facebook. So these are my dream companies, so I'm paying my utmost attention. I hope you enjoy the video. Okay, so this is a LeetCode medium problem, and we are given n number of nodes. We are also given a list of edges, and we are told that these edges are actually undirected edges. Now we need to see that whether the given graph is actually a valid tree or not. If it is a valid tree, we'll return true. If it is not a valid tree, we'll return false. And we are also given an example to understand this problem. Like in this example, we are given these 5 nodes and we are given some list of edges. Based on this list of edges, they have shown that this could be a pictorial representation. And over here, they are saying that, yeah, this is a valid tree. So that's why they are returning true. Now the question is, in order to understand this, first of all, we will have to understand that what is the relationship between any graph and a tree. What is the difference between a graph and tree, and how can from the given input we can identify that, okay, this is a valid tree or not, right? That every single tree is also a graph, but that is not the case for every single graph, that it will always be a tree. Because if I put it in Venn diagram, essentially graph is actually a superset, and tree is just one of its subset. So this can be a tree, and this is a graph. There are a lot of cases, lot of real life cases to understand that as well. Like the person who got slapped by Will Smith is always going to be a human, but not every single human has been slapped by Will Smith. It is something, that kind of relationship, right? Now the thing is, what are the differences between a graph and a tree? That inside the tree, all the components are connected, or all the nodes are connected. There is no restriction for graph that all the nodes should be connected. And the second difference is, inside any tree, we will never encounter any loops. So we can just say no loops, while inside the graph there can be loops. Let's try to understand this with some examples. Is this a valid tree? Actually, yes, this is a valid tree, because notice over here that from one node, like every single nodes are connected with each other, and we do not find any single loops. But the thing is, say for example, in this case, if I had an additional edge, something like this, I can clearly see that there exists a loop between these 4 nodes. And because we have identified a loop, we can clearly say that this, though this is a graph, but this is not a tree. Now let's take another example. Now this is a valid tree. Like all the nodes, they satisfy these two properties, that they are connected and there are no loops. The same graph, if I had some components like this, some additional nodes, though they are not connected with all the nodes, they are connected with each other, or there are some isolated nodes, something like this. If this is the case, this will always be true that okay, this is a graph, we can put it in the category of graph, but this will not be a tree. And in this case, we will need to return false. Now, before we move on towards solution, I just have a simple request. If you see, a lot of people, they watch my content, but they are actually not subscribed to my channel. It takes me a lot of time and a lot of effort to make these kind of videos, and I would really appreciate if you can just show your support and subscribe the channel. Like, now this problem actually can be solved in so many different ways, and I'm going to show you a few different ways on how we can do things. Now the question is, what we need to find basically we need to find that whatever this given input is this a valid tree or not. In order to find that whether it's a valid tree or not, we need to check two things: whether all the nodes are connected and if there are any loops or not, right? So what I'm suggesting is that we break this problem in two parts. In the first part, we check that what could be the different ways we can see that whether these nodes they are connected or not. If they are all connected, we are good, and if they are not connected, we can return false immediately, that this is not a valid tree. And once that is done, we will find all the ways on which we can identify that whether there are any loops or not, right? So first, let's go with the first approach. Now our aim is to check that whether all the nodes are connected or not. What could be the different things we can do over here? In order to check that, essentially what we will need to do is we'll have to traverse over whatever this given input graph is. Now traversing over this given input graph based on the structure we are currently given in the input is going to be a little bit tricky, based using this number of nodes and edges. So the question is, like, first thing we need to do is we will need to convert this given input in either adjacency list or adjacency matrix. Either of them can be used and it will work perfectly fine, but in this case I will suggest to use adjacency list. We only use adjacency matrix when there are too many edges. We don't have any clear indication in this case that there would be too many edges, and we would try to use an adjacency list, right? So now we are trying to check that whether all the nodes are connected or not, and we have already created our adjacency list. Now what I'm suggesting is that through this adjacency list, we know that we would be able to iterate over this given input, and through this given input, what we do is we create a hash set. Inside the hash set, initially it would be empty. Whenever we are at any point iterating over any single node inside this given hash set, we will check that whether that particular node already exists in the hash set or not. If it does not exist, we will add a new entry inside the hash set. And at the end, once we have traversed all the values inside the given input through this adjacency list, what we are going to do is we are going to check that what is the total size of hash set and what is the total number of n given. If both are same, we can conclude that from any single point we are able to reach to all the other elements, and because we were able to reach to all the other elements, all the elements are connected, and we at least satisfy one condition. So let's see that how it would work. Suppose in our adjacency list, we start traversing through this position number 1, right? So initially we check that whether this value number 1 exists in the hash set or not. It does not exist, so we'll add an entry over here that okay, value number 1. Now through this value number 1, we can traverse in two directions. We can either traverse to the neighbor on the right or neighbor on the left. So let's say that we go to this node number 0, again we add 0. From this 0 we go to node number 2, again we come to 2. Now from this 2 we can't go any way forward, right? But the thing is, we still need to go back. We'll need to do backtrack. We'll go back to 1, again through 1 we will go back to 3. Now at this 3, this is not added, so we add it over here. From this 3 we will go to 4, so we will add 4 over here. From this 4, again we will do a backtrack and we would come back at 3, and then we will come to 5, and then we will add 5 over here. Now at the end of this hash set, we are able to iterate over all the elements inside the given input, right? And we check that what would be the size of this hash set. So size of this hash set would be 6. And what is the given n? So n is also 6, which means in this case we are at least able to conclude that this given hash set is actually satisfying our condition, and inside this given graph all the nodes are connected. So we are good. Now suppose in this case if we had another node, something like this, and this was not connected to any of them, basically this would not have been entered inside our hash set, and our n in this case would have actually been 7 rather than 6. So we can clearly see that if our size of our hash set is going to be lesser than whatever the number of n we have, if that was the case, we could have written false immediately, because we found that there exists some not connected component, and which was not the case in this case. So this is one of the very good approaches to identify that whether the graph is connected or not. Okay, now we have taken care of the first part, and now we need to take care of the second part, that we need to check that whether in the given graph does there exist a cycle or not. So first thing that comes to our mind is that why don't we use the visited hash set that we have already created. And in that visited hash set, what we are going to do is at any point in time we are going to start exploring from one of the node in the given input graph. From that node we are not going to stop exploring till we exhaust all the neighbors of this particular graph. And at every single time we are planning to come to next element, we would first check that whether that element exists in the visited hash set or not. If it exists, then we would consider that there exists a loop and we would break out of it. If it does not exist, we would add that entry over here. So first we will start traversing this value number 0. So it does not exist in visited, so we will add an entry over here. From this 0 we will start exploring its neighbor. So one of its neighbor is this value number 1. And remember that we are going in depth first search, so we will not stop until we exhaust all the possibility in one direction before going to the other neighbor. We could do it breadth first search way as well. It's up to us. Now from this one, again depth first search, we see its neighbor, that there is a neighbor 2, so we add an entry over here because it does not exist. Now remember that this is actually an undirected edge. So what does an undirected edge means? Undirected edge means that from 0 we have an edge to go towards 1, and from 1 we have an edge to go towards 0. Same goes from 1, that we have an edge to go towards 2, and from 2 we have an edge to go towards 1, and same goes from 2, that we can go to 0 and we can come back. Now over here from this position number 2, because we have an edge that goes to 0, we can consider that 0 is also a neighbor of 2. In this case, from this 2 we will try to go to this 0, and the moment we try to go to the 0, we will see that okay, it has already been visited, it is part of this hash set. So we would say that okay, there exists a cycle, and we are pretty happy with ourselves that hey, we have identified a cycle and now we are done with our case. But the thing is, this is actually a wrong approach, and the reason why it is a wrong approach, it is wrong approach because there exists this undirected edge. And let me show you by an example that what could be the problems if we keep using this visited hash set only, and how can we find false positives. So suppose we are given an example like this, that 0 calls 1 and 2, and that's it. This is the input we are given, right? And now we don't have any entry inside our hash map. Now the thing is, all the edges are undirected edges. Now because they are undirected edges, we can represent them in different manner. So let's represent them in slightly different manner. So from 0 we have an edge that goes towards 1, from 1 we have an edge that goes to 0. Same goes from 0 to 2 and 2 to 0. Now initially we start traversing from this 0. Now we have our algorithm that initially we are going to add the entry to visited hash set. So 0 does not exist, so we add the entry towards our visited hash set. Now from the 0 we need to check all of its neighbor before we move on to some other node. Now from this 0, first of all, let's say that we go down this path and we check its neighbor 2. Because there exists an edge like this, we are able to check its neighbor, right? So we are at this position number 2. Now at this position number 2, we don't have an entry in the visited hash set, so we enter an entry over here that this is 2. Now from this 2, again we will need to repeat the same process, that we will need to check for all the neighbors or all the edges that this 2 can point to. Now it does not have any edges that go further, but it has an edge that goes back to 0. Now the thing is, in this case, again we will use our same logic. So from this 2 we can still go to 0. So we will check that whether we have visited this element 0 or not, and over here we find that hey, we have already visited this element 0, which means by our logic that we were previously trying to impose, we could have said that okay, we have found a cycle that looks like 0 to 2 and 2 to back to 0, and we in this case say that hey, we have found a cycle and this is not a tree and we will need to return false and blah blah blah. The thing is, this is actually not the case, and why it's not the case is because of this correlation of having an undirected edge that is causing all this problem, which means that we cannot rely only on having a visited hash set. If we do that, then essentially we are not going to be able to find an answer, because in this case we know that from there does not exist an edge, and from this 2 we are coming back to 0 only because there exists an undirected edge from this 2 to 0, and that's why we can consider this 0 to be 2's neighbor. But in reality this 0 is actually parent of this child 1 and 2. So if that's the case, why are we still doing things like this? What could be a better approach we can use to find that what would be the solution to detect these cycles? There are a couple of different ways where you can tackle this problem. One way to tackle this problem is that initially, remember, the only reason we are causing this problem is because there exists an undirected edge, which means that there exist 2 directed edges from any 2 nodes. So what we can do is we can put a condition that from any point, if we travel from this 1 to is 0 or 2, if we are able to travel in one direction, we would get rid of the remaining edge. And let's see that how it would work. So what I'm proposing is that initially we are at this 0th position. So we check in our visited hash set, we don't have any entry. So we add an entry over here that okay, we are at the 0th position. Now from the 0, first let's say we travel to 1, which means that now we have traveled from 0 to 1 in this direction. So our aim is that we get rid of this reverse edge in our adjacency list. So if we get rid of that, now we are at this position number 1. At this position number 1, again we add an entry over here in our visited hash set. Now from this position number 1, what we have to do is we will have to check that what are all the neighbors that we can travel to, or all the children we can travel to. But this one does not have any neighbor or children, so which means we don't have to worry about anything. So over here we can say that okay, from this one we can't go anywhere, but thing is there still exists some nodes that we haven't traveled to, and we are using either BFS or DFS in any manner to traverse over entire graph, right? So which means that we will have to do a backtrack. So now from this one we do a backtrack. Now again we end up at this 0. But thing is, in this scenario, remember, we are not ending up at this 0 because from 1 there existed an edge like this where we consider 0 to be 1's neighbor. We are coming back to this 1 because we are using backtracking through any BFS or DFS algorithm. We can implement this recursively or iteratively, doesn't matter. In any scenario we will have to iterate over all the nodes that are present inside the given graph, and since we haven't traveled all the nodes, that's why we are coming back to the 0. So again this would be a new entry in the visited hash set. So again we come back at the 0, and this 0 we check that okay, we have already explored one of the neighbor of the 0, but we still have to explore another neighbor. So again we repeat the same process. From the 0 we explored another neighbor of 0, we come back at 2, and immediately we get rid of this this edge that was coming back to it, and then we add an entry over here that okay, we are at this position number 2. Now from this 2, again we don't have any more neighbors to go to, so now we have explored all the neighbors of 1, so we can mark 1 as being done. We have explored all the neighbors of 2, so we can mark 2 as being done, and now we come back at the 0 and we can mark 0 as being done because we have explored all the neighbors of 0 possible as well. And in any scenario we did not find any single loop because we did not find repeated value inside our visited hash set. So we can determine that there does not exist a cycle, and which means in this case we can return true because there are no cycles. So we can say that there is no loop for this one. And the only reason we are able to come up to this conclusion is because at every single position we were removing the edge where in one direction we have already traveled. So that is one way to take care of this problem, and this solution would work as expected as well, right? Now the thing is, there could be another solution where we can use the little bit different logic, little bit different data structure, and we can do things in better manner. And let's see that what would be that approach. So the second approach is that rather than using this visited hash set, we don't need to do anything with this visited hash set. Let it be used for the purpose of counting that whether all the elements are connected components or not. What I'm proposing is that we created another data structure, a hash map, and in that in this hash map, what we plan to do is we as a key we have parent, and as a child we as a value we have the value of its children. Now let's see that how can we use this combination to do things a little bit differently. Also over here, let's say that we are given a graph like this, that 0 1 2 3, something like this, right? So 0 is connected to 1, 1 is connected to 2, 2 is connected to 3, and now we have this 3 connected back to this 1 as well, which means that there exists a cycle over here. Now because these are undirected edges, which means that they are bi-directional edges as well. So from this 0 we can go to 1, from this 1 we can go back to 0, and blah 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 whatnot. So initially let's say that we are at the 0th position. From the 0th position we start exploring its neighbor or children or whatever you want to call. So the moment from the 0 we are able to reach to this 1, we would add an entry over here in this hash map, and the entry we are going to make is that 0 is actually a parent in this case, and one of the children that we could find for this 0 is actually node number 1. So node number 1 is the children of 0, and just stay with me that why we are using this approach. Now again from this node number 1 we need to explore its neighbors, right? So what are the neighbors of this node number 1? We can explore neighbors based on the number of edges that goes out from this node number 1. So from this node number 1 we actually have 2 edges that goes out. First edge is that from this node number 1 we can go to node number 2. Now we check in this hash map that does node number 1 exist, node number 1 does not exist as a key. So we add an entry over here. So we say that okay, parent is node number 1, and from this node number 1 we can actually travel to node number 2. So we are good with that. Now again from this node number 1 we still have possibility that we can go back to this node number 0. So again we check in this hash map, okay, that whether there exists an entry for this node number 0 that we are trying to reach. Remember this very importantly. We will check that whether this node number 0 that we are trying to reach from this node number 1, does that exist in the hash map or not. Okay, so 0 exists in this hash map. Again we check that from this 1 we are trying to reach to this 0, is this one of the children of this node 0 or not. In this case, yes, 1 is the children of node number 0. If that is the case, we can identify that this connection from 1 to 0 is actually not a cycle, it's just a trivial loop, and that is being caused because there exists an unidirectional edge on both the sides. So that's why we will ignore this case, we will ignore this connection. We are not removing the edge. Again, remember, we are not removing the edge, we are just ignoring this case because in the hash map we are able to find that okay, this 0 to 1 connection is actually just a trivial cycle, and we move on with our life. So from this 1, again, since we have reached to this 2, right, and 2 is not existing, and 2 is one of the children of 1. Now again we are at this position number 2. Now again from this position number 2, what are the different ways we can travel? We can either go back to 1 or we can go to 3. Let's say that we go to 3 first. So we check that whether 3 exists inside the hash map. 3 does not exist, which means we can create an entry that where 2 is a parent and 3 is a child. We are good with this so far. Now again from this 2, when we try to check that from 2 we are trying to go back to 1, is that a cycle? So first we check that whether this 1 exists in the hash map or not. So 1 exists in the hash map over here, and 2 is one of its children. So because 2 is one of its children, we are going to ignore this case, and we are going to ignore, and because we are ignoring this particular, we are just going to move on with our lives. Now we are at this position number 3. From this 3 we will check that okay, what are the different places we can travel back to. So from this 3 we see that okay, one edge that goes to 1, one edge that goes to 2. First of all, let's explore this edge from 3 to 2. So over here we will check that we are trying to reach to this node number 2. So 2 already exists and 3 is one of its children, which means we are going to ignore this edge, so we don't have to worry about anything. Now again from this 3 we check for this value number 1. So okay, from this 3 we try to see that whether we are able to reach to node number 1 or not. Node number 1 has already been visited inside the hash map, and that's why we are able to determine that there exists a loop inside over here, from where we are actually going back to one of the places that was actually not that is already been visited inside our hash map. And this hash map acts as both. It acts as a visited hash set that we were planning to use, and also it acts as a way for us to determining that whether we are detecting the correct cycles or we are detecting the trivial cycles between the unidirectional edges. And this would be a way on how we can check the cycles, which means that the combination of this, using this hash map to identify that whether cycle exists or not, and using this visited node and iterating over using BFS or DFS inside our graph, original graph, using these two data structures, we can actually get rid of both of our cases where we need to check that whether the graph is connected, and we need to check that whether the graph contains any cycles or not. And once, because we are able to do both of these things, at the end, if we are able to reach to end node, we will return true. If we are not able to reach to end node, we can return false. And this solution actually works perfectly fine. There are no issues with this solution. It is a very elegant solution. If you tell it in any interview, they are going to be very impressed with the depth and breadth of your thinking capabilities. What are the space and time complexity over here, and can we do something better? So let's first try to determine that. So space complexity, in this case, we know that we will have to use the hash map, and we will have to use the visited array as well. Inside the hash map, we are going to iterate over all the nodes plus all the edges, which means that over here the space complexity would be big O of v plus e, because we are iterating over all the vertices and all the edges. The time complexity in this case would also be big O of v plus e, because we will have to iterate over every single node and every single edge multiple times in order to come to this solution. But the thing is, we are not doing loop inside loop work, so which means we are not doing repetitive work at any given moment. Okay, after such a long explanation, let's see that there be a better approach. And yes, there is actually a very elegant, very beautiful solution, where actually we don't even have to go through all of these mess to detect that whether cycles exist or not. In order to do that, actually we need a higher knowledge of graph theory. What do I mean by that? Okay, at any given moment, suppose we are given a graph like this, that 0, 1, 2, 3, 4. Suppose we are given a graph like this, right? Now, if we want to identify that whether this is a tree or not, like in this case, we can clearly see that, yeah, this is a tree. There is a very legitimate scenario. There are no cycles. All the nodes are connected and blah, 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 whatnot. Everything is good with this, right? Can you notice an important property over here? The important property that I'm talking about is, if you count that what are the number of nodes and what are the number of edges, does there exist a correlation? Yes, actually there exists a correlation. And the correlation is that suppose we are given the number of nodes equal to n, and if we are given the edges that are n minus 1, and we determine that all nodes are connected. If we determine that all nodes are connected, because remember, in our solution, when we are trying to finding that whether the nodes are connected or not is much simpler. We simply need to use a hash set. We need to iterate over whatever the given input we have, and basically we can determine that, okay, whether the nodes are connected or not. But checking for the cycle is slightly more complicated. Actually, not slightly, much more complicated, because either we have two options and both options require us modifying a lot of things or managing a bunch of different data structures. Either we can choose to remove the edges like this, or we can choose to create a hash set like this. In both the cases, we are actually doing a lot of work. So what if we actually don't need to encounter that whether we need to find the cycles or not? If we only encounter that whether the given nodes are connected or not, if that is true, and at any given moment we identify that, okay, all the nodes are connected, and then we identify this property, that whether the number of nodes that are given and number of edges that are given, if there is the difference between them is only 1, if that is the case, then the given graph will always be a tree. Let's see in this scenario. In this scenario, we can identify that, okay, from this 0, all the nodes are connected, that this 1, 2, 3, and this 4, we are able to connect to all of them, right? What is the number of nodes? So number of nodes in this scenario is actually 5. This 1, 2, 3, 4, 5. Now let's see that what are the number of edges. So if we calculate the number of edges, the number of edges is, okay, this is one edge, this is second edge, this third edge, and this is fourth edge. There are only 4 edges that are possible. If we have any more edges, then for sure there would be a loop. Because remember, where would you add an edge in this scenario? You can add an edge over here. Okay, that creates a loop. Let's say that you don't add an edge over here. Suppose you add an edge over here. Again, it creates a loop. Well, you don't even add an edge over here. You add an edge like this. So again, this creates a loop like this. Eventually, as long as the difference between the number of nodes and number of edges is actually not exactly 1, and if the number of nodes are one number higher than whatever the number of total edges are given, if that is the case, and we determine that all the nodes are connected, then we can clearly say that, okay, everything is good with our life and we don't have to worry about anything. Why we need to check that whether all the nodes are connected or not? The only reason we need to check if all the nodes are connected or not is, suppose we are given a scenario like this, that we are given these three nodes. Suppose we are given these 4 nodes, right? And in these 4 nodes, so remember our equation is that number of nodes and edges. So if nodes are 4 and if edges are 3, so we can say that, okay, everything is good with our life. In this case, the number of node is 0, 1, 2, 3. Okay, so total 4 nodes, we are good. Number of edges 1, 2, 3. So this is also good. The thing is, over here you can see that there exists a cycle over here between these 3 edges. And why there exists a cycle? Because this particular node is not connected. So always at any case, we will have to check that whether all the nodes are connected or not. And once we identify that all the nodes are connected, we are good, and then we can just wrap up our solution. So using this solution, actually everything becomes so smooth that if we calculate the time and space complexity, the time complexity in this case is actually big O of n, because we only need to iterate over the given number of nodes, and where n defines the number of nodes. If we calculate the space complexity is also big O of n, because we only need to maintain a hash set to take care of all the number of connected edges. So once we find out that what are the number of connected, if all the elements are connected, we can immediately identify that whether this given graph is a tree or not. So let's move on towards coding now. First of all, we are going to check that whether the given number of edges, if its length is 1 less than the number of nodes or not. If that is not the case, we can return false immediately. So, and if that doesn't happen, we will have to make an adjacency list. So we will create an adjacency list, so it becomes easier for us to iterate over the given input array. So for all the given n, we are going to treat them as vertices, and all the values that are provided in the edges, we are going to treat them as edges basically. Notice over here that for every single edge, we are actually adding 2 entries inside our adjacency list, and that is because the given edges are actually undirected. So that's why we will have to add an edge for both the nodes. So if there is an edge between 0 to 1, so we will have to create 2 edges, and those 2 edges would be 0 to 1, and from node 1 to 0. So that is what we are doing by this second for loop. Okay, now we will start iterating over the given graph inside the adjacency list. And I want to learn that how to iterate over the graph using stacks. So I'm going to do it using stacks, and I will be doing iterative depth first search. So first I'll initialize a stack of integer values and just name it as stack. And we will also have to create a hash set of integers called visited. Inside our stack we will add the first entry, so we will add the node 0, and inside our hash map visited we'll mark the first node as visited. We'll pop the first node that is inside our stack, and then we will start iterating over its neighbors, and we'll see that if that neighbor has already been visited, then we will simply ignore that case. If that is not the case, we will start iterating, we'll start adding those neighbors to our stack as well, and we will also add that neighbor to our visited hash map as well. It would be neighbor, not node. Okay, and after this loop ends, we only need to check that what is the size of our hash set. So if, or else we will return false. And let's try to run the code. Okay, seems like our solution is working. Let's try to submit this code. So the question is number of provinces. This is a LeetCode 547 problem, and this problem has been popular amongst top tier companies. So companies such as Amazon, Bloomberg, Apple, Two Sigma, DoorDash, Goldman Sachs, Google, Uber, they have all asked this problem. So that's why I hope that you pay enough attention to this one. If we see the problem statement defines that there are n cities that we are given, and we are told that some of these cities are connected, some of these cities are not connected. Now if say city A is connected with city B, and city B is directly connected with city C, then city A is indirectly connected with city C. So A is connected with B is connected with C. Suppose this is the relationship, then we can define that A is also connected with C. This is what this problem is, the statement is referring to. Now going back, we are given the definition that what a province is. A province is a group of directly or indirectly connected cities and no other cities outside of this group. So suppose we are given cities like A, B, C, D, something like this, and we are given that A is connected with B, B is connected with C, and we can also refer that indirectly A is connected with C as well. Currently this D is not connected with anyone. In this case, we can define that this A, B, C makes a province, and this D by itself, currently since it is not connected, it is not making a province. But suppose we identify that another city E that exists that is connected with city D, then we can define this to be the second province as well. Okay, so now we know that what the problem statement has given us. We are given n cities, and we are given the connection between those cities, and we are also given the definition of what a province is. Now we are given an n cross n matrix, and wherever there is a connection between any two entities, that particular value has been marked as 1. That defines that the ith city and jth city is connected. And if the value is not 1, if the value is 0, which means that those values are not connected. Now based on this given input, we need to define the total number of provinces. This problem is very similar to one of the previous problems we solved, and that is the number of connected components. And how? Let me just quickly show it to you. What we are given is that we are told that we are given matrix, and inside the matrix, using the values 0 and 1, we are going to define that whether any two values are connected or not. Okay, so suppose the values are a, b, c, d, and here a, b, c, d. Okay, all the values are by default going to be connected with each other, so I'm going to mark it as 1. Suppose, let's just take the same example. So these are all the items we are given. This is true. Based on all of these items, what we are given is that this is actually not a matrix, but actually this is an adjacency matrix, and adjacency matrix is one more way to represent a graph. Since this is one more way to represent a graph, we can, rather than considering these as cities and these are connection between them, let's just try to think of these as nodes and edges, where nodes are the cities and edges are the connection between them. And now this becomes a very simple problem that we can solve using BFS quite easily. And the whole problem statement now becomes is that we need to identify that how many number of connected component exist inside any given graph, and those connected components, we need to return them as the answer. So I have already solved this one in past, but I'm going to quickly show you the solution again. And simply we are going to use breadth first search. For breadth first search, we all know we need two items. First one we need is a queue, and we need some way to keep track of all the visited nodes so far. So let's just do that. I'm going to initialize our queue, and also I'm going to initialize our hash set that is going to keep track of the visited hash set. Okay, so this one is for visited and this one is queue. Now we can start at any given node. So suppose this is the input we are given. Currently nodes are 1, 2, 3. These three cities are connected, and city 4 and 5 is connected. We are also going to mark one more variable called provinces, and initially the value of the provinces is going to be 0. Okay, so currently this is the variable that is going to keep track of the number of provinces we have been able to find so far. Currently the value is 0. Now let's just pick any arbitrary value. So we start with node 1. So let's just run a BFS starting with node number 1. So first we are going to, since 1 has not been visited, we are going to mark as visited because we are visiting it. We are going to add 1 inside our queue. Now the moment we find a value inside a queue, we are going to iterate through its neighbors. Currently 1 has two neighbors, value 2 and value 3. Both value 2 and value 3 are not visited, so we are going to mark them to the number of visited nodes, and we are going to mark 2 and 3 here. Now we iterated over all the neighbors of 1, so we are going to dequeue 1 out, and we are going to remove it from the queue. Now currently we only have values 2 and 3. For value 2, the number of node is 1 and 3 as its neighbor. Both 1 and 3 have been visited, so since they are visited, we are not going to revisit them, and we are going to pop 2 out as well, that stating that we visited all the nodes of 2. And at the same time we are going to pop 3 out as well, since the neighbors of 3, 1 and 2 are already been visited. Also, I forgot one key important thing, and that is that the moment initially when we started iterating through 1 and we found that 1 has a neighbor 2, immediately we needed to add the number of provinces to 1 because we found at least one province. So we would have found one province, and in order to finding that province, we already visited all 3 nodes. So we are going to mark these 3 nodes as visited. Now, since in the input we are already given n is equal to 5, we initially started with n is equal to value number 1 because it was not visited. Now we will start with n is equal to 2, but that has also been visited, so we will simply skip over. N is equal to 3 has also been visited, so we will simply skip over. Last value is n is equal to 4. N is equal to 4 has not been visited, so marking 4 to our visited list, adding 4 to our queue, and now 4 has a neighbor 5. So again, the moment we find a neighbor, we are going to increase the number of provinces to 2. We are going to add 5 to our visited list. We are going to add 5 to our queue, and then we are going to pop 4 out because we visited all the neighbors of 4. But we haven't visited all the neighbors of 5. Currently for 5, since 5 has already been visited, we do not care, but 5's neighbor 4 has also been visited, which means 5, we also visited all the neighbors of 5. So now we get rid of 5. Now initially for this n is equal to 5, we had gone through 1 to 4. For the 5th value, 5 is also present inside the number of visited list. So we can define that 5 has also been visited, and because of that we went through all the nodes or all the cities that we were given, and the number of provinces that we were able to make was 2, and which we are going to return as the answer. If we see solution for the time and space solution for this one, basically the time complexity is going to be big O of V plus E, where V is the number of vertices or number of cities in this case, and E is the number of edges or the connection between the cities that we are given. Pretty simple, and this is pretty standard. Space complexity also going to be big O of V, because the space complexity is based on the visited hash set and the queue that we have to generate, which can hold maximum up to 5 cities for this example. So it is directly related to the number of vertices that is present inside our given example. Awesome. So see how knowing BFS made our life so much easier. Let's move on to the coding explanation for this problem. Let's see the coding solution for the number of provinces problem. This is a really unique problem, and the solution is actually quite simple. First of all, in the main method, we are given the 2 by 2 matrix that defines that what are the number of connected components. Based on that, we would be able to easily identify that what is the total number of edges or total number of nodes present. And once having that, we are going to initialize our visited Boolean array, and initially the number of provinces is going to be 0. Now we are going to run our for loop, where we are going to call the BFS method. Inside the BFS method, first of all, we are going to check that whether the current node has been visited or not. If the node has not been visited, we are going to call BFS method to visit all the connected components or all the cities that are connected with each other that form a province. And we are going to increase the number of provinces. So we are going to do provinces plus plus, that was initially set it up as 0. Now let's see that what is going to happen inside our BFS helper method. The answer is quite simple. In the BFS, we are going to initialize our queue, and we are going to have a visited array that to keep track of all the nodes that we have visited so far. For any single input that we are given, we are going to keep on iterating all the neighbors of that particular node that it is currently connected to, and we are going to mark all of them visited. So even when we encounter the same city that has already been processed, we do not reprocess it again, because it has already been marked visited. And after this entire process ends, currently in this loop, this provinces variable should have all the answers populated. We can simply add them over here and return provinces as the answer. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs 99.26% faster. So this is pretty fast solution. And don't worry about this. I'm going to paste the solution inside my GitHub, and the link is in the description, so you can check it out from there. So today we are going to do find the celebrity LeetCode problem, and if we see some of the popular companies, the problem has been asked at companies like Amazon, LinkedIn, Pinterest, Microsoft, Facebook, Apple, Snapchat, Google, Uber, and Goldman Sachs. So basically all the popular companies have asked this question. So I'm going to pay my utmost attention. I hope you also enjoy the video. This has to be one of the most interesting problems I have been able to find so far. If you look at this, LeetCode categorized this as a medium problem. If you try to understand the problem statement and try to think about it, you will feel like this is actually a hard problem. And once you put like some more thought into it, you are actually going to feel that this is actually an easy problem. So in my opinion, this is actually an all-in-one problem. Let's understand the problem statement to go further deep. It says that suppose we are at a party with n people, and the names of these people are the numbers. So basically numbers from 0 to n minus 1. So say for an example, we are in a party with 4 people. Basically the people are going to be 0, 1, 2 and 3. So these are going to be the 4 people. Now we are told that in this party there may exist. So this is an important part, that there may exist, which means there might be a celebrity or there might not be a celebrity. Okay. Now we are first of all given that what the definition of a celebrity is. The definition of a celebrity is that that every single person in that party knows who the celebrity is. And the second condition is that celebrity does not know any single person in that party, which is how typical celebrities are. So now, given these two definitions, first of all, we are told that we need to check that whether there exists a celebrity or not, and if there exists a celebrity, basically we need to find that who that celebrity is. The question is how we are going to find who that celebrity is. Well, definitely over here the relationship is based on either people knowing who the celebrity is, or the fact that celebrity knows no one, that everyone knows celebrity and celebrity knows no one, right? Now at our advantage we are given a methodology where we can check between any two entities whether they know each other or not. We have a method boolean knows a to b, which defines that whether a knows b or not. If a knows b, if this gives answer true, which means a knows b. If this gives answer false, which means a does not know b. And why we are using that? Because the only relationship we have to identify whether a person is a celebrity or not is by the amount of people know them or the amount of people they know. And in this case we either need to find the celebrity or we need to return -1 if no celebrity exists. So I know this is a little bit complicated to understand, but let's try to see some examples for this problem. Okay, so in the problem we are actually going to have an input that looks like this, where in this input we are given a list that contains some values that defines the relationship between any two values, that whether they know each other or not. Now the thing is, this input is kind of messy, so I'm not actually going to show you examples based on this exact input. I'm actually going to show you in the base of something that is easier to visualize. So this is the same input I took from here, but I have actually converted it into a 2D matrix. And basically as an input we are given a graph, or we are basically given an adjacency matrix. Okay, so for this adjacency matrix, we based on this adjacency matrix we are given two entities. We are given a person and we are given whether that person knows each other or not. This diagonal line is always going to be 1 because that defines that whether person 0 knows person 0 or not, whether person 1 knows person 1 or not, things like that. And that is always going to be 1, so we can simply ignore this one. This serves no purpose. The important thing in this case is this defines that whether person 0 knows person 1 or not. So this answer is 1, which means that person 0 knows person 1. Let's try to find who the celebrity is in this problem, right? So in this case we are given basically 3%. So we can actually create a graph that looks like this of 3%, and we are going to name them as 0, 1 and 2, right? Now the thing is, relationship between them is actually going to be the relationship defined by an edge, where a edge would represent that whether one entity knows the other entity or not, or one node knows the other node or not. And this is going to be a directed edge. Why? Because it could be possible that 0 knows 1 but 1 does not know 0. So we cannot just simply have an undirected edge, we must have a directed edge in this case. So let's try to do that as well. So if we draw it from this graph, okay, 0 0, this does not matter, these three values, so we'll just ignore them. Let's just start 0 with 1. So 0 knows 1, right? So which means 0 knows 1. Yeah, we mark it. Now does 0 know 2? No, 0 does not know 2, so there is not going to be any edge. Now whether 1 knows 0? No, 1 does not know 0, and 1 also does not know 2, so 1 does not know anyone. Now in this case whether 2 knows 0? Yeah, so 2 knows 0, that is good. And whether 2 knows 1? Yeah, 2 also knows 1, so that is also good. And 2 knows 2? Yeah, that is true, so we can ignore that. In this case, if we see the two definitions of a celebrity, that everyone knows who the celebrity is and celebrity knows no one at the party. So definitely in this case we can say that, hey, if we check out the input for this value number 1, it knows itself. But the thing is, that is not the point. The point is whether it knows anyone else at the party or not. So 1 does not know anyone at the party, that is true. And also 0 knows 1 and 2 also knows 1, which means every single one who is every person other than 1 knows who the 1 is, and 1 does not know anyone, which means 1 perfectly fits on our category of celebrity, and in this case 1 is going to be celebrity. So we will simply return 1 as the answer, and this is what we need to return. Okay, let's see one more example. In this case again 0, 1 and 2. Let's draw 3 lines. Now ignore these 3 cases, and 0 knows 1, no, 0 knows 2, yes, so 0 knows 2. Okay, Does 1 know 2? Yeah, 1 also knows 2. That's good. Now whether 2, okay, 2 knows 0. So in this case 2 knows 0 and 2 knows 1. No. So in this case, can we find any celebrity? Actually, we cannot find any celebrity. Why? Because in this case, okay, 0 and 1, both of them know 2. So that is good. 2 qualifies for one of the property of being a celebrity. The thing is, second property of being a celebrity is that it has to know no one at the party. But in this case, 2 actually knows who the 0 is. So because 2 know one person, 2 does not qualify for the second entity of our answer. So in this case, we cannot find any celebrity. So because there is no celebrity present, we are simply going to return -1 is the answer. And this is what we need to return. Okay, so first approach is a brute force approach. In the brute force approach, what we are going to do is we are simply going to check that whether all the person that are given, can any single one of them is a celebrity. So for one by one, we are going to check for every single person whether they are celebrity or not. So in this case, what we are going to do is first we will take consider person 0. Okay, so for the person 0, we will try to see whether 0 is a celebrity or not. How can 0 be a celebrity if everyone else knows who the 0 is and 0 knows no one? So in this case, we can see that 0 knows someone, so 0 is not a celebrity. Now we will have to check whether 1 is a celebrity or not. So in this case, okay, 1 still knows someone, so 1 cannot be a celebrity. But and in this case, we'll try to see whether 2 is a celebrity or not. So 2 knows no one, and let's see that if everyone knows 2 or not. So this one knows 2, but this one does not know 2. So 2 is also not a celebrity. So in this case, we will return a -1. And this logic leads us to the correct answer. Some maybe if you make some modifications or tweaks, it can be an acceptable solution as well. The thing is, this is still not the most optimal way to solve this problem. So basically, we would end up solving this problem in big O of n square time. So which is not too bad for some of the problem, but it is really bad for this problem because this can be done very efficiently with other methods. So let's try to see what that other methods could be. So in this scenario, if we see, okay, 0 knows 1 and 2. So 0 knows 1 and 2, right? Same way, 1 does not know anyone and 2 knows 1 and 1 and 0. So 2 knows 0 and 2 knows 1. So basically answer is going to be 1. That is a given fact. The thing is, what is one smart trick we can use? The smart trick is the knows function. The knows function that we are given in the input, that is there for a reason. And what knows function does is that if we provide any two values, say for example, if we provide the values of 0 and 1, it is quickly going to tell us that whether 0 knows 1 or not. So in this case, okay, 0 knows 1, that is a true fact. Now the thing is, if we know for sure that 0 knows 1, what is one thing we can say for guarantee? We can say for guarantee or for certainty that 0 cannot be a celebrity. Why we can say that? Because remember the definition of a celebrity. The definition of a celebrity is that everyone knows the celebrity and celebrity knows no one. Which means in this case, if we try to find or if we try to see this knows function between 0 and 1 and the answer is true. If the answer is true, definitely we can say that 0 cannot be a celebrity. Which means we are eliminating 0. Now, what could be the second possibility? Second possibility could be, say for an example, if we try to use the knows function for values 1 and 2. If we try to use the function 1 and 2 knows, the answer is going to be false. Why the answer is going to be false? Because 1 does not know 2. If 1 does not know 2, what is also one more thing we can say for certainty? Well, we can say for certainty that in this case 2 cannot be celebrity. Why 2 cannot be celebrity? Because we found at least one element that does not know 2. And in order for 2 to be celebrity, celebrity has to be known by everybody else in the party. So because we find one entry over here who does not know 2, we can say for sure that 2 is not a celebrity. Which means depending on the result of this knows function, if the value is true, we can eliminate one value, that is the first value in the knows function. If the value is false, we can eliminate the second value inside this given input, which means with every single knows call, we are getting rid of one element. So in this case, after just making two calls, we were able to get rid of 0 and 2, which means if there exists a celebrity, it has to be 1. So now all we need to do is that since this is the last item or last value pending, Do we need to check that whether everyone knows one or not? No. Why? Because since we know for sure that these two are not the celebrities, right? So all we will have to worry about is that whether one knows no one. If one knows no one, which means one has to be the celebrity. If one knows at least one person, which means there are no celebrities inside this input, and we can simply return -1. And this is the whole logic behind this problem. Let me try to explain very quickly with a big example. So now we have bunch of different values over here. Basically, we are simply going to use the knows function, and we are going to go through every single value and try to see whether it knows the next value or not. So first we'll try to see that whether the 0 knows 1 or not. So, and we can ignore all of these values because diagonals doesn't matter. We do not care if they know their own self or not. So in this case, okay, 0 to 1. 0 does not know 1, which means we can say for sure that 1 cannot be celebrity. If 1 cannot be celebrity, we can simply skip over to the second value. Now in this case, we will check that whether 0 knows 2. So in this case, 0 to 2, 0 knows 2. So because 0 knows 2, we can say for sure that 0 cannot be a celebrity. So we ignore this. Now we are at this value number 2. So we'll try to see whether 2 knows 3 or not. So 2 to 3, if we check, okay, 2 knows 3. So if 2 knows 3, definitely 2 cannot be a celebrity. So we will ignore that. Now we are at this value number 3. So we'll check for 3 to 4. So 3 to 4, if we check, yeah, 3 knows 4. So in this case, 3 cannot be a celebrity because 3 knows 4 because of this value. Now we are at this 4 position number 4, 4 to 5. So if we see 4 to 5, so 4 to 5, this value is actually 0, which means 4 does not know 5. So because 4 does not know 5, 5 cannot be a celebrity. So in this case, we have actually got rid of all of these elements and only fourth value is pending. So now we know that if there exists a celebrity, it has to be 4, otherwise there are no celebrities. So now we are simply going to check that whether 4 knows anyone or not, and for that we simply have to do one check at this fourth row to see whether apart from 4 by itself, does it know anyone else, and it knows no one. So definitely 4 is the only candidate left and 4 knows no one. So in this case, 4 is definitely our celebrity, and this we can simply return as the answer. And this is the whole logic behind our answer. Say for an example, in this case, by chance, if 4 knew this value number 1, if this was answer 1, then simply we can say that, okay, 4 is also not a celebrity, and we can simply return -1 in this case. But thing is, because this value is actually 0, so in this case, answer is actually going to be 4, and we are solving this problem most efficiently. If we see time complexity in this case, the time complexity is actually going to be big O of n. And if we see space complexity, well, apart from using a couple of variables, we are not using any additional space. So space is actually going to be constant. First, I identify a few things. So I created a new global integer to use the number of people, and I have assigned it to the value of n. And basically in the problem, we need to resolve this find celebrity problem. And also for this problem, I have created is celebrity a helper method. So that is going to define that whether any single candidate that we have been able to identify from this find celebrity method, if that is a celebrity or not. And now first let's start implementing this find celebrity method, and then we will implement our is celebrity method. So first of all, we are going to initialize a variable called celebrity candidate. Now we are going to run our for loop, and for every single value we are going to check, or we are going to call our knows function. And for the knows function, we are basically providing the value of the celebrity candidate and the value of current I. Now depending on the answer we get back, we are going to update the value to the I. So what this is going to do is, this is simply going to eliminate every single value for us except one last remaining candidate, and that we are going to consider as the celebrity candidate. And once we get out of the loop, all we will have to do is we will have to call our is celebrity method. If this value is actually true, if this value is a celebrity, we are going to return this. And if that is not the case, we can simply return -1. Now in this method, we will first of all run a for loop. Inside the for loop, first we will have to check that if the given value of I is equal to j, which means we have found a diagonal value. So in this case, we simply ignore that. And if that is not the case, we are going to check that whether J satisfy all the properties of being a celebrity or not. If any of these is true, we can simply return false. And if that is not the case, and if we get out of the loop, we can simply return true. And I think this has to be the whole logic behind this input. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions, and it is also really efficient in terms of time complexity. So this was a great problem to solve and to understand a lot of different concepts. I would be posting this solution in the comments so you can check it out from there. Thank you. The problem is called number of connected components in an undirected graph. And if we see some of the popular companies who have already asked this question, there are companies like TikTok, Amazon, Google, Facebook, LinkedIn, Microsoft, DoorDash, and Twitter. So this problem has been really popular amongst topmost companies. And let's see that what the problem statement is trying to convey. Basically, this is a LeetCode medium problem and also very well-liked problem. It says that we have a graph of n nodes that we are already given, and we are basically given the edges that defines that there is a connection existing between those two nodes for any given graph. Now based on that, we need to indicate that how many number of connected components are present inside the graph. So let's try to understand this with an example. In this case, currently we have 5 nodes. So basically we are given an n is equal to 5 as the number that defines that there are 5 nodes. We are also given these edges. So we would have given 3 entries, and the first entry is going to be 1 to 2, second entry is going to be 1 to 3, and third entry is going to be 4 to 5. Now based on these two items, we need to define that how many number of connected components that exist, which in this case we can see that this is the first connected component because these 3 nodes are connected with each other, and same way this is the second connected components. So in this example, for this given input, we can define that there exist 2 connected components and we need to return 2 as the answer. So this is the whole ask of the problem. Let's try to understand this with one more example. Suppose in this case, currently we are given n is equal to 7 and we are given all of these different edges. Now in this example, we can clearly see that there exist 4 different connected components, and those 4 components are these, that this is the first one, this is the second one, this is the third one, and though this 7 is not connected with any other node, still this is a connected component in itself because it's connected with itself. So in this case, in total, since we have 4 connected components, we need to return 4 as the answer. Now let's see that what is going to be the strategy to solve this problem. Suppose we take the same example as the input and we will try to see that what should be the answer. Now again, remember, we are given 2 things. First, we are given n is equal to 7, so that we know for sure there exist 7 nodes, and we are given all of these 5 edges. Now based on these number of nodes and edges, we can clearly do one simple thing, and that is to treat this as a graph problem, because that what it is. Basically we know that a graph is comprised of 2 items. First one is a node and second one is an edge, and which we are just told in plain English that these are the 2 entities we are given. So we are going to treat this one as a graph. Now the aim is to find connected components, which means from any single edge or any single node, we will need to define that how many other nodes that particular node is connected with. And if we keep on repeating the same process, and the moment we find the connected nodes, we can eliminate all of those nodes. So and repeat the process for all the 7 nodes that are given, we would be able to find the number of connected components quite easily. And the technique we are going to use over here is the one of the most popular technique in the entire coding industry, and that is called breadth first search. And how we are going to use BFS? Well, we already know that in order to use BFS, we will have to use Q, and we will also have to use number of visited nodes that we have already visited. So using these 2 items, we are going to make our lives so much easier, and let me just walk you through the solution. First thing we are going to do is we are going to we can start from any node, because this is a graph. There is no particular definition that we need to start from here or we need to start from here. Say for simplicity, we start from this node number 0. So we are going to have our Q, Now inside our queue, currently we don't have any elements, and we also have our visited hash set. We can also use visited array. I'm just giving you example of visited hash set. Either way, we are going to have a mechanism to keep track of all the numbers or all the nodes that we have visited so far. So this is our visited hash set, and this one is our queue. Okay. Now first we start with node number 0. Now for node number 0, we are going to mark this one as 0. So we are going to enqueue with 0. Now we are also going to mark 0 as visited. Okay, and we are also going to have one more number that is called the number of connected components. So let me just mark this one as counter. Okay, and currently the initial counter value is going to be 0, but since we found one node, we know for sure that there exists at least one connected component, because it could be connected to itself. So in that case, we are going to increase the number by 1. Okay, now for this particular 0, we are going to run BFS, and by running BFS, what we would be able to do is that we would be able to go through all the neighbors that this 0 is connected with, and then mark all of them in the visited hash set. So even in the future, for this n is equal to 7, if we come back to the same node, if that node has already been visited, we will just simply skip over it. So let's just do that. Now for this 0, it has two neighbors. First neighbor is neighbor 2 and neighbor 1. Currently both are not visited, so let's just add entry 0, 1 and 2 over here, and then we will mark 1 and 2 inside our queue, because we need to do something with that. Currently the count is still going to be 1 because all the nodes are connected. Now we pop 0 out and we do the same process with 1. Currently for the value number 1, 1 is also visited. So since 1 is already been visited, we do not need to do anything with 1, and we can simply pop that one out. Again, 2 is also visited, so we do not need to do anything, and we can pop it out. Now after iterating or after doing the BFS starting with the node 0, we have simply eliminated node 2, node 1 and node 0 by itself, and so far the count has been 1, and we have all of these 3 nodes in our visited hash set. But we know that there are still 7 nodes that we have to take care of. So we are going to iteratively go over every single one of them. Initially we started with 0, so we got rid of it. Let's just start with 1. Again for 1, since 1 has already been visited, we do not need to increase the counter and move on to the next value. Again 2 has also been visited, so we do not need to increase the counter and move on to the next value. So all of this entire connected component has been taken care of. Moving on to the next value, starting at position number 3. Since 3 has not been visited, adding 3 over here, adding 3 in the queue as well, going through all the neighbors of 3. Currently 3 only has one neighbor, and that is value number 5. 5 is not being visited, and also since we find a new element 3, I forgot to add the increment the count. So now the number of connected components we have found so far is going to be 2. I forgot that, but this is important. Now going back, the currently 3 is connected with 5. 5 has not been visited, marking 5 as visited, at the same time adding 5 inside our queue to visit further neighbors of 5. Now 3 does not have any more neighbors, which means we can get 3 out or dequeue 3, and then we are going to have value number 5 remaining. 5 has one neighbor, that is 3, but since 3 has already been visited, we cannot do anything with that. So we are also going to get rid of 5, and 5 has also been taken out. This means that currently we do not have any elements inside our BFS function. Now moving on, currently we went through 0, 1, 2 and 3. Now we need to go through value number 4, because there are 7 elements inside our given input. For even again repeating the same process for value number 4, currently 4 has not been visited, so we will mark value number 4 as visited. At the same time, we are going to put 4 inside our queue. We are going to go through the neighbor of 4 current, and we are also going to increase the count. I always forget to increase the count, which is the most popular thing which is the most important thing asked in this problem. But anyways, now going back for value number 6, it has not been visited, so we are going to add value number 6 over here. At the same time, add value number 6 over here. Now we iterated over all the neighbors of 4, so we are going to dequeue 4. After dequeuing, currently there is only element number 6 staying in. 6 currently has one neighbor, that is value number 4, but since 4 has already been visited, we do not need to add it to our queue, and then eventually we would pop out 6 as well. Now what we have done is that currently, in order to find these 3 connected components, we already visited nodes 0, 1, 2, 3, 4, 5 and 6, and all of these nodes are visited. Now in the end we are going to be at the position number 7. Since for position number 7 this node has not been visited, which means we need to increase the counter. So currently the counter is going to be of value number 4. Now we are going to add 7 to our list of visited nodes, and also we are going to mark 7 inside our queue. Since 7 does not have any neighbors, which means we can pop 7 out immediately, and now our queue is empty. We have already iterated over all the number of 7 nodes that were given as the input, and we are basically done with the problem. So in the end, whatever the value that has been stored inside this count variable is the answer we need to return. So simply at the end we can return that there are 4 connected components in this problem, and this is the complete solution. Now if you see how beautifully we were able to come up with the solution, and in this case if you see time and space complexity, the time complexity is going to be big O of V plus E, where V defines the vertices or nodes, and the E defines edges, because that is the time complexity to run the BFS function and go over the entire given input array. So this time complexity is pretty good. If we see space complexity, now space complexity is also going to be big O of V, because we are using the additional data structure of queue and also a hash set or array. There are two ways to do it. I typically like to use hash set, but you can also use an array as well. Both would work equally fine. In either case, this is a very good time and space complexity. And remember, one of the most important concept is, inside the graph theory, the breadth first search allowed us to solve this problem smoothly in a beautiful manner. Here is the coding solution for number of connected components in an undirected graph, where first of all we are given in the input the value n, and we are also given a 2 by 2 array called edges. So first thing we are going to do is create an adjacency list and to create a graph like structure. So this is going to allow us to iterate over graph in a much easier fashion, which this process is doing, where we are running across every single edge and every single node and plotting them on the graph. After that, we are going to have our boolean array called visited, and we are also going to have a value called count that initially we are going to set it up as 0. We are going to run our for loop starting from value 0 to the total number of n that is given in the input. And then inside the for loop, first thing we are going to check is that the current ith position, if that is not visited, then we are going to call our BFS function, and at the same time we are going to note it as the new connected component found, and we are going to increment the number of count. Now let's see that what is going to happen in our helper method BFS, where we are taking a graph as the input. We are also taking the number of nodes that have been visited so far, and we are also using the starting pointer from which we are entering inside this given graph. So first of all, we are going to initialize our cube. We are also going to have a visited array that we are going to mark as true for the current node that we are visited. And while there are no entries inside the queue, first of all, we are going to pop the last added element inside the queue, visit every single neighbor of that node, and for all the neighbors that has not been visited, we are going to mark them as visited, and we are going to add it to our existing queue. And by doing this operation, we would be simply running through every single connected component. So suppose here I give you like 0 as the input, then through this BFS method, 0, 1 and 2, all three nodes would be marked visited because they all are connected. And this is what this operation is doing. And in the end, after this for loop ends in our main method, we simply need to return the count that we have found that would allow us to find the number of connected components. Let's try to run this code. And our solution works perfectly fine. Let's submit the code. And our code runs decently efficiently. And don't worry about that you are not being able to see the code. I'm going to put this code inside the GitHub, so you would be able to find it quite easily from there. So the LeetCode problem we are going to solve now is called surrounded regions. We can see that this one is a LeetCode medium problem and also very well like problem. Now the statement is quite straightforward, that we are given an m cross n matrix named board that contains bunch of different x's and bunch of different zeros. Now we need to capture all the regions that are 4 directionally surrounded by X. And if a region is captured, then we need to flip all the zeros into that particular region into the axis that is a surrounded region. So let's try to understand what they are trying to ask. We are given in this example an m cross n board where we can see that there are bunch of different x values and bunch of different zero values. Now in this case, what is the definition of any particular zero region to be surrounded? A region is surrounded if in all 4 directions it is connected by some sort of x in each one of them. If that is the case, we can determine that this particular region is surrounded. Now notice one important thing. We are not concerned with its immediate neighbor, but even if the neighbor of the neighbor is still a value x, then we can determine that that particular value is still surrounded by x's. So the moment we identify a surrounded region, all we need to do is convert all the zeros into x's, which means we can see that this node is surrounded by 4 x's in these 4 directions. Same way with this particular 0, it is surrounded by these 4 x's, and same way for this particular 0, it is surrounded by these 4 x's. So logically all of these would be converted into the x's, which we can see over here. But for this particular region, it is only surrounded by x in 3 different directions, not 4. So we are not going to flip this 0 into x, we are going to leave it as it is, and then we need to return this state of the m cross n grid as part of the answer. So let's try to see that what is the simplest logic we can use to solve this problem. Now let me give you one example of bunch of different zero potential values in all of these different grids. Let's say for this particular grid, if we have any single value 0, then that value has to be not surrounded region. Why? Because currently this particular value is located over here. Even if in all the other directions we have access, then also we would never be able to get a 4 directional pattern where this region becomes a surrounded region. So in the answer, we are always going to have a scenario where this 0 is going to remain 0. Same way for this 3 by 3 grid, let's say that if we have any particular 0 present over here, and let's say that all the other values are currently x's, then we can very easily determine that this 0 is actually surrounded by x's in all 4 directions. So in the answer, when we try to create, basically this 0 has to be flipped into x. That is true. But let's say instead of doing that, instead of this being 0 in this middle portion, let's say if we have 0 located at any of these edges, any of these, okay, I'm not saying all of them are zeros. Let's say any one of this is a 0, and let's say that all the other values are x's. So I'm currently marking these by a bunch of different x's. This region would never be surrounded. That's a given fact. Why it would never be surrounded? Because there is always going to be 1 or 2 directions where it is located on the edge, which means there can never be an x planted over here. So if the node is in the middle, then it has the possibility of being a surrounded region. But if we identify 0 at any particular edge, then that 0 is always going to be a not surrounded region. So it does not needs to be changed. That is what I'm trying to explain. Now let's try to see one more example in this case. Let's say if we have any particular these 4 zeros placed like this and all the other values are x's. In this case, all of these zeros has to be converted into the x's because all of this becomes a surrounded region. But for some example, if we have any particular 0 located over here, we already established that this does not needs to be changed. That is number one thing. Second thing is that not only this does not needs to be changed, let's say that if there are any particular other zeros connected with this value, then also they are also going to be not surrounded regions. Once again, I repeat, if there are any particular zeros that are connected with this edge, then we can determine that this is also going to be not a surrounded region, and we are going to exploit this property to its fullest. Because remember, in this case, particular this 0 is actually always going to have one more 0 located over here, which means it can never be 4 directionally challenged by another 0. and this is what we are going to use to solve this problem. What we are simply going to do is that we are going to treat this as a graph problem. Not only a graph problem, we are also going to treat it as a graph traversal problem, where we need to do the depth first search. At any given moment we identify a value that is currently 0. The thing is, we are not just going to blindly start looking for zeros in all of these particular grids. That it makes no sense. If there is any particular 0 in the middle, there it might be possible that there might be excess in all 4 directions that could prevent it from becoming a not surrounded region. What we are going to do is we will try to only traverse into the edges of this particular matrix, and for each of the edges we will try to find that if there exists any particular 0, then we are going to start doing the DFS, and all the values that we identified through this iteration, we are just going to mark those numbers that they are always going to be 4 directionally not surrounded regions, and all the other regions or all the other values we can simply mark them by X. So let's try to understand this with an example that I'm trying to show you. Let's say that in this case we are currently given that these two nodes are currently zeros, and let's say that this is connected with this 0, and let's say that this one is not connected with anyone else, and then we have this 0 connected like this, and all the other values are currently X values. So logically the algorithm I'm proposing is that we start iterating over this m cross n grid in first of all the edges. So let's say that these 4 are the edges, and then we once again identify this edge and this edge, and then this edge and this edge. So we found a one edge that contains a value 0. The moment we identify one edge that contains the value 0, first of all we are going to mark this one as a special 0. So let's say that I'm keeping track of all the zeros that I have been able to identify so far, and let's say that this one is a special character that contains a 0 at the edge. Then we are going to do the DFS operation in all 4 directions to find all the connected zeros. But we can see that this one does not have any connected zeros. So we are just going to say that this is the only 0 we find, and then continue with our iteration. Once again we are at this position, this is also X. Once again we identified one more 0. So the moment we identify one more 0, we are going to mark it as a special character, and then we are going to start doing the DFS operation in all 4 directions. This one is an X, so we don't do anything. This one is an X, so we don't do anything. But this one is not an X, so this one is also a 0, and a 0 that has been found by reaching a 0 that was present in the edge. So once again we are also going to mark this as a special character, and then now from now on we cannot move ahead anywhere forward, so we cannot do anything. On top of it, for our DFS operation we will have to keep track of all the visited nodes, so we are also going to mark all the visited nodes as well. So it's just simply for our convenience, and that's it. So once again we don't find any more access, so then we simply say that we iterated all the edges. We did the DFS on whenever we found a 0 at the edge, and we marked those nodes, and apart from these nodes everything else should be converted into the X's, which means this node has to be converted into an X, and that's it. This is the state of m cross n that we need to return of all the zeros that are not surrounded, and all the surrounded regions are being converted into the X's. So that's it. This is the whole solution. If we try to understand the time and space complexity, in this case time complexity is going to be big O of m cross n, because we will have to iterate over every single nodes, and this is an example of adjacency matrix kind of representation for the graph. Space complexity, well, this is debatable. If you have to create a new snapshot, then you might have to use m cross n space. If you can modify this current existing node just by changing this character from something else from 0, maybe something like a hash or something, then also we can use the same pattern or same logic. So it's up to you how you want to approach that, or how your interviewer wants to do that. It can be a common space complexity, or if you are not allowed to change the input, then it is going to be big O of n cross n space complexity. So now let's try to see the coding solution for this one. So the coding solution is quite straightforward. We need to solve the given board, and first we are going to check for the edge case, that if the given board is equal to null, we can simply return. If that is not the case, we are going to define our m and our n. Then we are going to start iterating over the boundary, and start marking all the zeros that we find on the boundary as like a temporary character or a temporary variable. So let's say that we run two loops. We have this if condition that if the given node is equal to 0 or m cross m minus 1 and j is equal to 0 or n minus 1, which means we are checking for the edge nodes. On top of it, we are also checking that if the given board position marks the value as 0. If that is the case, then we are going to call our DFS method. In the DFS method, we are checking that all the surrounded regions that we need to find. So this is our DFS method, where we are first of all checking that if the given node is equal to null, or we exhausted all the possibilities, we can simply return. If that is not the case, we are going to mark that particular value as a temporary character t, stating that this has been visited, and we are going to run the DFS operation in all four directions repetitively, which means we are only going to be left with temporary values that are currently visited by us after this DFS operation, that are connected with the zeros that are located at the edge. Then once that is done, we simply need to check and capture all the surrounded regions. So for that, we can simply iterate over the given input array and check that if the given input board position is equal to 0, which means it is not t, then we are going to simply mark it as x. If that is not the case, and if that value is t, which means it is not a surrounded region, so we are going to mark it as 0. And that's it. This is the whole solution. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code is exceptionally faster compared to all the other solutions, which is great to see. And once again, you can find the solution on my GitHub repository. Link is in the description. Thank you. Today we are going to do a very interesting LeetCode problem called word ladder that has a real life application, because this is a game by itself as well. And if we see some of the popular companies who have already asked this question, there are companies like Amazon, Bloomberg, LinkedIn, Microsoft, Google, Uber, Apple, Facebook, Lyft, ByteDance, and Goldman Sachs. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode hard problem and also a very well-liked problem, which is a rare combination to be seen. Now in this problem, we are given two words, a begin word and an end word, and we are also given the list of words called dictionary or word list. Now our aim is to reach or go from the begin word to the end word by a transformation sequence. The question is, how does this transformation sequence works? Well, the transformation sequence works is that suppose we are currently at word 1, we can only jump to word 2 if the difference between the characters is only 1. So say for an example, if we are given a word like cat and we are given the second word like caught, we can go from cat to caught because there is only difference of a single character a. The c and t are common across both the words. So this is a valid transformation sequence. The idea is that from the begin word, we need to keep on doing the transformation sequence amongst many different words, and our aim is to reach to the end word somehow. And if we are able to do it, we need to see that what is the minimum number of ways we can do it, and these words, they has to be present inside the word list that we are given. So we cannot just create words out of fly. This is the purpose of this word list set that we are given, a bunch of different words. And if somehow we are not able to reach to this end character using the transformation sequence, we need to return 0. And if we can, we need to return the minimum number of hops needed to reach to there. So let's try to understand this with a couple of examples. If we see this first example here, the begin word that we are given is called hit and the end word is cog. And these are the different words that we are given. So one of the ways we can solve this problem is by creating a word sequence that looks like this. In this case, we are starting from the first word and we are reaching to the end word. And these are all the different hops that we are making using the transformation sequence. So this is a valid example. But if we see in this case, we are actually taking 6 different hops to reach to the end word. Can we do something better? And the answer is yes. There exists a better solution for this problem. So let me quickly show you the better one. Again, even for this example, we are able to reach from this beginning word to the end word But in this case, we are doing the whole journey by only 5 different hops. So in this case, we need to return 5 as the answer because we are only taking 5 steps to reach from the first word to the end word. And this is going to be our word ladder. If we take a look at the second example, in the second example, the word we are given is hit, and again end word is cog, so that is true. But the thing is, in this case, we need to return 0. Why we need to return 0? Well, because this cog is actually not at all present inside this word list that we are given. So since the end word is not present, we cannot reach to the end word. So basically we need to return 0. So I hope this explanation makes sense and you are able to understand the problem statement. Now let's see that what is going to be the approach we will take. Okay, so before we come up with the optimal solution, first let's see that what kind of pattern we can see in this problem. Basically, we are given a beginning word and an end word, and we are told that there are some series of words that we need to go to in order to reach to this end word, and we need to return the minimum sequence possible, right? The thing is, in this problem, we are not only guaranteed to given all the words that would be used between this beginning and end word, and it could be possible that we are given some different words that are not being used, or they can be used, but the thing is that leads to like a longer answer, and we do not need to like go through all of them, and we only need to find the shortest path. Now if you see this kind of structure, what does this reminds you of? Well, you are absolutely correct. This is actually a very similar structure to a graph, where you can see the words that are given, they can be treated as different nodes, and the relationship between these nodes can be treated as edges. So we have our vertices and edges, and we have a way to define edges. Now how does a vertices connects to an edge? A vertices connects to an edge through the mechanism that the number of characters of word 1 and word 5, in this case, they only have one differing character, and that's it. That is the only way we can define a relationship between them. Once we have a structure like this ready, now let's see what is our aim. Our aim is to find a path from the beginning word to the end word, and if we want to find the path, what we can do is we can simply iterate over the given input and see that what are the different paths we can take, and try to find the most optimized path or the shortest path that leads us to the correct answer. So in this case, we can actually find two different paths that leads us to the answer. First one is the one that I indicated in blue, and second one is the one that I indicate in this purple color. Now in both the cases, this path is actually the shortest path that leads us to the answer, and we need to in the end we need to return the distance between the words amongst these paths. So in this case, the answer is going to be 5. But you get the idea that basically we can, if we are able to generate this graph structure, then all we need to do is we need to do the breadth first search traversal. And the question is, why breadth first search? Because we are trying to find the shortest path, and if we do depth first search, it could be possible that in practice it might take us longer. So breadth first search would be a better candidate in this case. So if we are able to create a graph structure, and if we do the breadth first search, we can actually find the shortest path. Okay, so now we are going to use the same example that we have been given as the input. Now, first of all, we need to find that the beginning word that we are given is the word hit, right? And say for example, we devise some mechanism to easily traverse through these words to make sure that whether these words exist or not, right? Now the question is, from the hit, we are treating this hit as one of the nodes, right? Now we need to find that what are all the different edges this hit is able to connect to. The idea we can do is that we can see all the possible words that this hit can have with just one differing character. The logic is we can start with the first character and keep all the characters from A to Z, and then keep the remaining two constant. So what we will do is we will try to check for the words such as AIT, then BIT, all the way up to ZIT. Right, these are all the different words we can make. Then same way we can keep the H and T common, and then do A, B, C all the way up to Z, and we can keep on repeating the same process. So basically at every single word, what are the different possible words we can have? Well, say for an example, if the length of this is equal to M, then basically we can have M multiplied by 26 differing characters and or differing word possibilities. Now amongst these 26 word possibilities, all we need to do is we only need to find the words that exist inside this word list. And since this is a dictionary, basically we can access pretty fast and check that whether any word exists or not. We can do it in constant time, so this is not going to be an extra overhead. So by using this logic, we are actually able to generate all the graph pairs for our given input. So first value is going to be hit, and now let me just quickly draw the graph structure. Okay, so we can actually make a structure that looks like this, and this is a pretty decent representation of the input that we are given. Now this is going to be our start node, and this is going to be our end node, or the beginning word or and the ending word. Now basically we need to iterate over the given graph, and we are also going to keep track of all the nodes that we have visited so far. That is to not end up inside any like unexpected loop or infinite loop. Now all we need to do is, from starting point, we already mentioned that we are going to run a BFS, and we are also going to have a variable called min that is going to keep track of what is the minimum path we have found so far. So if we just see the input, one of the path we can take is that we start from hit, and then we can go down this path, and eventually we would be able to reach to the end word. So in this case, if we see, and definitely we are going to keep track of all the visited nodes, and everything is going to be taken care of. If we see this path, basically it is going to take us 6 words, and currently this is the minimum value we have because we haven't identified any other path, right? So 6 is the correct answer. Now what is, let's see that if there is any second option that we are missing. So yes, there is another option that we are missing, and the option is that if we start from this hit, we can go down this path, and through this path the number of words we encounter is actually 5. So because we are encountering 5 words, basically we need to update the minimum number of answer we can get. Let's see if there is any another path that we can take that we are missing. And yes, there is also still one more path that we haven't taken, and the path that looks like this. And in this path also we are encountering 5 words. So again the answer is going to remain 5, and we have explored all the possibilities. So in this case we can simply return 5 as the answer, because that is what we need to create. And you see, once we have this graph kind of a structure ready, things becomes much easier to comprehend, and we can simply return the answer pretty fast, pretty efficiently. So this is the whole logic behind this problem. Now in this problem, currently we are only going in just one single direction, but in practice there can be like a bi-directional BFS, where we start iterating from here and we also start iterating from here, and we can do like BFS from this direction, BFS from this direction, to reach somewhere in the middle and to find the answer. And we can do things slightly faster in that cases, but I don't think anyone is going to expect you to do this in any of your interview, so don't even bother. If we see time complexity, in this case the time complexity is actually going to be big O of m. So m is the number of length of any character, and I mentioned that length is going to remain constant amongst all the word list characters, so we don't have to worry about that. So number of m square. Now why m square? M square is taken in order for us to generate this graph like structure. So it takes big O of m square time, and for every single character there can be one possibility that we need to iterate, because we know the starting and ending point. So basically it's going to be m square times n in terms of the number of time complexity, where n is the total number of words given. And if we see space complexity, well, basically we are anyway storing this graph like structure, and that is going to give us like big O of m square space. So we also need to take care of that. So in my opinion, this was a tough problem, but once you know the logic, you can solve it easily. And this this goes to show you that if you know the logic about different data structures, things becomes much easy, because this word ladder game is actually a real life game that people use and people play. So yeah, this is not just a random out of the blue question. Now let's move on to the coding. So since this word ladder problem was already becoming such a big video, so that's why I'm just going to explain you the code rather than typing all of it, and I will go through the explanation. So first of all, we are going to initialize a variable to note down the word length because that is pretty important. And we are also going to initialize our hash map that contains the information of all the combinations inside the dictionary that could be possible. Now what we are going to do is, for every single word that is present inside this given word list, we are basically going to iterate over all of its characters, and we will try to see that for all the differing characters, what are all the transformations possible, and whenever if a transformation is possible, we will basically add it to our all combination dictionary. Because this is a hash map, inside the key we are going to store the value that is being present and inside the word list, and as its subsequent value we are going to have a list of all the possible combinations that any particular word can have. So this is going to give us our dictionary, and this is going to take basically m square time to do it, or l square time to do it. Now, in order to iterate over the breadth first search, we are going to have our queue where we will keep on adding, or we will begin with the first word, and we will not rest until we have iterated over all the neighbors of this first word, and we will keep on repeating the same process iteratively. So we are not doing recursion. We can do recursion, but we are doing it iteratively. And also, as mentioned, that because we do not want to get inside a position where we end up in any infinite loop, we are basically going to initialize a hash map, and now we are going to basically put the first word or the begin word that we are given as the input, and then we will start iterating over our given queue in the BFS fashion. So first of all, we are going to create a pair, or so first of all we are going to remove the node in that is existent inside the priority queue, and then we will try to get its word value. Then we will see that what level it is, and basically we will iterate over all of the different possible words that can be present, and we will keep on repeating the same process for all the adjacent words. And every time we go to the new level, we are basically going to increase the size of the level. So this is going to return us that how many different paths that we have taken so far. And somehow if we get out of the loop, then basically we need to return 0. So this is the whole logic behind the whole problem. And this condition refers to if we have reached to the end word, and this condition refers to in the scenario where we have not reached to the end word, we are somewhere in the middle. So basically we are going to add a new entry inside our queue, and we are going to increase the current level we are at. So I think this solution makes sense. I would be posting this code in the comments, so you would be able to check out the code. Don't worry about it. Let me try to run this code, and our solution works as expected. Let's submit this code. And our code runs decently efficiently in terms of space complexity and time complexity. Both are really good. And this is the BFS solution from the LeetCode. So once again, we are going to do a very awesome LeetCode problem. This one is a Reconstruct Itinerary. We can see that this one is a LeetCode hard problem. Also, constructing an itinerary is actually a very popular real life use case that we see in like aviation industry all the time. So this is an important problem. Let's pay our utmost attention. Now we are given a list of airline tickets where any particular position we are given like a tuple value inside the array that defines that where what is the departure and arrival for locations based on that particular unit. Now we need to reconstruct the itinerary in in like a particular order and return that reconstructed itinerary. Now let's see that what are the constraints around reconstructing the itinerary. Number one thing is all the tickets belong to a man who departs from JFK, which means JFK is the starting position for our entire itinerary. Then next thing is that if there are multiple valid itineraries that we are able to construct, then we should return the itinerary that has the smallest lexicographical order. So what does lexicographical or lexical order means? It means that we need to sort them in like A to Z manner, basically. Which means if we, let's say, if we have two tickets, first one is from JFK to LGA, and second one is another ticket from JFK to LGB. Then we must return LGA first before returning LGB, because remember that we are sorting lexicographically. So this one has character A and this one has character B. So A comes before B, which means this has a smaller lexical order. So we need to put this in priority. Now we are also told that we may assume that all the tickets are valid, and we must use all the ticket once and only once. So let's try to understand this problem and try to see that what could be the potential solutions. Number one thing is, this is the type of input we are given. Now we can see that there are a bunch of different tickets we are given. In this case, we are given a ticket that is from Munich to London Heathrow. We are given a ticket from JFK to Munich, then San Francisco to San Jose, and London Heathrow to San Francisco. So these are the 5 tickets we are currently given. I have just plotted all the 5 airports over here, and now let's see that what is the solutions we can make. So let's just take a simple approach, and let me just keep on marking all of these nodes, or like all the flight connections. So we know that we have a connection between Munich and London Heathrow, so let me mark this one. Then we have a connection from JFK to Munich, so let me also mark this one. Then we have a San Francisco to San Jose, so marking this one. And then we have London Heathrow to San Francisco, so let's mark this one. So this is a valid order. We can see that every single ticket we currently have, that are 4 tickets we have, we used all of these 4 tickets over here. After using all of these 4 tickets, we need to reconstruct itinerary starting from JFK. So we can see that if we start our journey from JFK, the direction is going to be JFK to Munich, then Munich to London Heathrow, Heathrow to San Francisco, and San Francisco to San Jose. This is the reconstructed itinerary that we need to return in this order. Let's take one more slightly complicated scenario. So we have like bunch of different tickets in this case, and we only have 3 airports to deal with. So first ticket is JFK to San Francisco. So let's just mark this one. So JFK to San Francisco, this is one option. Second option is JFK to Atlanta. So let's mark this one. Then San Francisco to Atlanta, okay. Then Atlanta to JFK, okay. And then Atlanta to San Francisco, okay. So currently these are all the different options we have. Now let's see that what is the optimal option we need to choose. We know that we need to start our journey from JFK. Now notice at JFK we have 2 different tickets going outwards. First ticket is going to the San Francisco, and second ticket is going to the Atlanta. So question is, which ticket should we choose? Now here comes the lexicographical ordering that we need to pick from, and we can see that Atlanta is lexicographically smaller than San Francisco. So we are going to pick ATL first. So in our path, this is going to be the first path we are going to take. All the markings that I'm marking with red is like the correct marking, okay. So we took care of one ticket. Then from Atlanta, once again we have 2 options. We can either go to JFK or we can either go to San Francisco. So once again it makes sense to pick the smaller amount, and that is once again going back to JFK. So let us go back to the JFK. Now at JFK we only have one option, that is go to San Francisco. So we go to San Francisco, and then from San Francisco now we only have one option, that is to go to Atlanta. So we go to Atlanta, and now from Atlanta we still have one more edge that is remaining, and that is to go back to the San Francisco. So we will once again go back to the San Francisco. So this is the sequence we are going to follow, where first we are going to go from JFK to Atlanta, then this is the second, this is the third, this is the fourth, and this is the fifth flight we are going to take. So this is what we need to return. Now I know understanding this question took way longer than expected, but don't worry, the solution is not that complicated. So let's just try to understand a simple logical scenario just for this particular input that we are given. What is the one thing that we did to solve this problem? Well, it is quite obvious what we did to solve this problem. We first of all mark that from every single airport, what are all the different possibilities we can take, and then we started iterating over our journey from JFK. On top of it, not only marking all the different possible journeys, we also mark that what under what order should we start picking and start moving in any particular direction. So what I'm suggesting in this case is that we are only given the tickets, we are only given these values from any particular two nodes. What I'm suggesting is that we actually treat this as a graph problem, and which is pretty obvious. Why are we treating it as a graph problem? Through this one, we are going to be marking every single airports we currently have as the nodes, and all the tickets that we currently have as the edges. Okay, we already got our nodes and edges. On top of it, what we need to do is we need to iterate over the given graph. Now, iteration of the graph is quite simple. We know that we have two methods. We have a breadth first search method and we have depth first search method. Now in this case, going in one particular direction makes more sense, because notice that over here we are going in like a depth first search fashion. Even in this example, we saw that we were doing bunch of different back and forth in order to complete all of our transaction, and that was also being done in depth first search fashion. So in this case, we are also going to be using DFS to iterate over all the nodes. Next thing is we need a starting pointer to iterate over. We already have a starting pointer, and that is starting from the JFK. So we know that we first of all need to treat it as a graph. We will need to do a DFS. We will need to start iterating over from JFK. Next thing is, when we are constructing a graph, we will have to set up ordering in which sequence are we going to go to any particular airport, and for that we will have to follow the lexicographical ordering. So for that, what I'm suggesting is that we actually use an adjacency list kind of a scenario where we store the adjacency list for our graph, and we do it in lexicographical ordering. So what I'm suggesting is that we initialize a hash map. As part of the hash map, we need two items, key and value. As part of the key, we mark the nodes or the airport. As part of its values, we mark that from that airport how many different tickets that we can traverse over. So, or how many different airports or destinations we have. Okay. Then once we have these two values, then we need to populate these arrays. So let's start populating this value for this given input. Okay. So currently let's go one by one in these throughout all of these tickets. So first one is we are starting from JFK. So one node is JFK. Okay. Now from the JFK, we need to have a ticket. The destination is San Francisco. So let me mark this as SF. Then we have one more ticket from JFK, and the destination is Atlanta. Now we know that JFK is already present. The thing is, we are trying to insert Atlanta over here. So one logical thing is that rather than just doing anything, let me just create a linked list over here where I'm storing Atlanta as well, that from JFK I have one more ticket that goes to Atlanta. Okay. Same way, we have a San Francisco and the destination is Atlanta. So let me also do that. And we have Atlanta and JFK. So Atlanta and JFK. Okay. And last one is Atlanta to San Francisco. So we are going to have one more destination, San Francisco from Atlanta. Now we have our key or our graph, our adjacency list being created, okay, inside our hash map. But the thing is, we need to sort this in lexicographical manner. So what we are going to do an intermediate step where we are simply going to update this given graph that we have created so far. And for this one, we are simply going to sort all the values or all the inputs we have in the destination in lexicographical manner. We know that this can be done in n log n time. So we are going to spend that extra time in order to complete that. So let me just start marking this one. So first entry is JFK. Okay. For JFK, we currently have two values. First one is San Francisco and second one is Atlanta, but this is not sorted correctly. So we are going to sort it. First one is going to be Atlanta and second one is going to be San Francisco, as this is going to be the sequence of linked list. For San Francisco, we only have Atlanta. So let's just mark this one. And the last one, even for the Atlanta, we have JFK and San Francisco that is already sorted in correct order. So let's just mark this one. So JFK and we have Atlanta. Okay. San Francisco. Okay. So let's just mark this one as well. And now we have everything we are looking for. Now all we need to do is just do the DFS operation from our adjacency list on the graph, and every time we iterate over one destination, we are going to remove that from the list. So next time when we are at the same airport, we simply pick the next lexicographical entry in sequence. So let's try to run the solution. So we start our journey from JFK. So we are initially at this JFK location. We saw that the first ticket we need to find, or first flight, is Atlanta. So let's just traverse to Atlanta, marked as A. Now we need to go to the Atlanta because we are currently presented in Atlanta. Also at the same time, we are going to remove Atlanta from here, and we are going to go to the Atlanta. Now Atlanta, the very first flight is JFK. So once again we are going to come back to JFK. So after coming back, we are going to remove JFK from here. So now at the JFK, the next flight in sequence is San Francisco. So let's just make another journey to San Francisco. And now we are going to remove San Francisco from here. Now at San Francisco, next flight is Atlanta. So let's just mark a journey to Atlanta, and we are going to remove Atlanta from here. And now from the Atlanta, let's just mark one journey to the San Francisco. So we are going to mark a journey to the San Francisco, and we are going to remove San Francisco over here. Now the moment we come to any particular position, let's say we came to San Francisco, now there are no more entries or no more destinations for us to visit, which means we can conclude that we have iterated over every single possible tickets that we currently have present, and we can simply say that we iterated over all the entries, and this is the path that we created. We can just keep track of the path in like a backtracking function, and because we are making recursive calls to use the DFS and solve this problem quite easily, quite beautifully, quite simply, and this is an awesome LeetCode problem. If we understand the time complexity in this case, that is going to be big O of vertices multiplied by edges plus big O of n log n in order to do the sorting, but this is already greater than n log n, so we don't need to factor that in. And if we talk about the space complexity, it is going to be big O of once again vertices multiplied by edges, because we are creating a new hash map that is going to be of length v. So actually this is only going to be big O of size v, but in the value section we are going to have all the edges that we currently have, so it's going to be v plus e. Okay, so this is still a good time and space complexity. Now let's quickly see the coding solution for this one. Okay, so the very first thing we are going to do is to create a map to store the list of destination for every single departure airport. So we are going to create a new hash map where as a key we are going to store the string that is going to store the name of the airport, and as part of its value we are going to be storing a linked list or list of strings. Now we are going to iterate over every single tickets that we currently have and keep on marking all the values inside our graph hash map that we have just created. After having a representation, now we are going to be sorting all the values that we have in the destination of the graph. So we are going to run a for loop and just do a sort operation. After sorting it out, we simply need to start our journey from the JFK terminal. So we are going to have a linked list that is going to be creating an itinerary that we need to return as part of the answer, and we are going to have a DFS operation that is going to start from the JFK airport, where we are going to pass in the graph that we have just created that contains all the sorted destinations, and the itinerary linked list where we are going to be storing all the values in sequence. Now let's see our DFS method. So first thing we are doing is that we are adding the current airport we are at the destination. After that, we are checking that while the given destination is not null and the list of destination is not empty, then we are going to remove that destination to avoid revisiting the same path. So we are simply going to removing that inside our array, and we are also going to be calling the next value that we need to iterate over and calling our DFS function once again. So that's it. This is the whole solution, where instead of passing in JFK, we are passing in the next airport that we have to iterate over, and we are also adding the airport to our itinerary as well, just so that we know that what airport we are beginning at, and we are generating the itinerary in the reverse order. So now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs beautifully compared to like almost 75% of all the other solutions, like 71%. It can still be improved in terms of space complexity. So Let me know in the comments if you want to see that. But anyways, you can still see or find the solution on our GitHub repository, so feel free to check it out from there. Thank you. So the lead code problem we are going to solve now is called minimum cost to connect all points. This is a very popular question in my opinion. Why? Because we are going to be dealing with something very important, that is called Prim's algorithm, to solve this problem. And this Prim's algorithm actually has a lot of different practical applications that you can use it in all sorts of different questions and different techniques. So let's understand the problem statement. We are given an array points that represents an integer coordinates of few points on a 2D plane, which means x and y type of graph. And we are told that any particular point value is defined as xi and yi, so the coordinates of that location. Now we are told that the cost of connecting 2 points x and y is the Manhattan distance. So let's say that if you typically has like 3 values, and if you are trying to, let's say, connect any two like this one, in this case the cost of this one is going to be the Pythagoras if we try to choose the diagonal. But the thing is, Manhattan distance is that instead of picking out the value of the straight diagonal between these 2 points, you first go to a common point and then go to right. So in this case you are actually doing the delta of x, and you are also doing the delta of y, so absolute values of x1 and x2 amongst these 2 points, and the sum of this is going to be the total distance you are going to cover. So this is called Manhattan distance, and this is what we are going to follow. So it's slightly better for us so that we don't have to spend so much time on calculating the Pythagoras or root values. Now we need to return the minimum cost to make all the points connected. Now let's try to understand this with an example. In this case, suppose these are the different points we are given. Now we need to make sure that number one, we connect all of these points in some fashion. And after connecting these points, we also need to make sure that the distance we are traveling by connecting them is the minimum distance we can. Now let's try to understand first of all that how does a Manhattan distance is going to work. So let's say you want to find out that what is going to be the distance between these 2 points, then logic is going to be quite straightforward. You are first going to do the difference between x pointers, so this y pointers, and you are going to add it to the difference between x pointers. So in this case the distance between these two nodes is going to be 4. Though it's not a diagonal, I'm just writing it diagonally so it becomes easier for us to understand. Now the thing is, the solution of this problem is something where we will have to deal with minimum spanning tree. Now minimum spanning tree is a very important concept in the graph theory, where you are given bunch of different points on any particular plane, and you are trying to connect all of these points in some fashion such that there are no cycles being formed, and you are trying to span the tree in like only the places where it is absolutely needed, nothing more than that. But the question is, the first thing that should come to your mind is that, hey, in this case we are only given points, we are not given the edges, which means these are simply just the nodes we are given. We know in order to solve any particular graph problem we need two items, we need a nodes, and we also need edges. But the thing is, good thing for us is we already know how to calculate edge between any 2 points. And the thing is, in this case there is possibility that from every single point you are able to connect to every other point in order to treat it like an edge. But the thing is, if I try to draw the whole solution by that matter, it's going to look very bad, because imagine how many number of different edges you can form amongst all of these points, and then it is only going to look so much more messy and complex if you have to understand all the different flows and data entries and data points and whatnot. So what we will try to do is we will understand that what is the most simplest logic we can use to solve this problem, and we will also understand that how we are going to be using the Prim's algorithm and the solution of basically Prim's algorithm plus the graph theory concept to solve this problem. So let's start working on the solution of the problem. I hope you must have understood that what the problem is asking us to solve. So now let's very quickly and very simply think one by one that what are all the different possibilities we have across all of these 5 different points? Well, number one possibility is that if we are at this point, we don't know that what are all the points that are currently present inside the remaining graph, which means we don't know that if we have to generate a minimum spanning tree that crosses or that goes through all every single nodes that are currently present, which node should this node 0 be connected to? So we don't know this question, number one thing, that what is the minimum cost to reach to any particular point from this node 0. And remember, we need to make sure that we don't form any cycles, because we simply need to connect all the points. And if there are cycles, basically our cost of connecting all the points would increase. So the shortest way to connect all the points is through like some sort of a straight line or a tree kind of structure where there are no cycles. So now at this 0, the number one thing we will have to do, if we have to find the shortest distance or the closest point, we will first have to calculate every single distance we can from all the remaining points to this 0th node. And the distance between these points would be treated as the edges, because we are basically connecting two different points, and amongst those edges we will have to find the edge with the smallest value. So these are actually weighted edges. And the other thing is, the connection in this case is going to be bidirectional. Why? Because whatever the distance from this 0 to this node is, same distance is going to be from this node to 0 as well. So we don't need to do any directed distance calculation in this matter. All we are concerned about is unidirectional transfer, and to understand that what is the minimum place to reach that place. Now comes another problem. Let's say that from the 0, it makes logical sense that this is going to be the smallest distance that we can calculate. And we also know that the distance amongst this one is going to be 2. So sorry, 2 plus 2. So total, let's say that this distance is 4, that we already know that this is going to be the smallest distance. But once again, when we come back to this place, now we still have 3 more nodes that we will have to iterate over. We are not going to iterate over node number 0. We are going to treat that this 0 has already been visited, but once again we will have to repeat the same operation. And from this position, we know that the shortest distance we should be able to find is going to be this value. So if we calculate this, I think this distance is going to be 3. Okay. And same way, from this 3, the shortest distance that we calculate for any particular node is going to be this one, and this distance is also going to be 4. But the thing is, now we still have one more node remaining, and we already found the results for these 4 different nodes. So question is, how do we know that which node is actually going to call to this particular node? So for that, we will actually have to find a way that while we are calculating the distance from 0th node to all the other nodes, and same way from this first node to all the other nodes, we will still have to keep track of all the nodes that are still remaining. Because the thing is, it could be possible that there are some nodes that are not down the path of the shortest nodes. But the thing is, we need to connect all the points, so we will still have to find a node that is still closest to this node, that it makes sense to make that connection. Now I know what I just said might sound confusing, but the thing is, try to understand this from an example point of view, that if you are if we only traversed, or if we only use the greedy approach where we are just iterating in the minimum fashion, then we are always going to be stuck with one node that is not following this beautiful path. And the thing is, if we try to find the path to that node, that remaining node from here, this might be much longer compared to this distance. So in order to do that, what logical solution I'm suggesting is that we first start at the 0th position. From the 0th position, we make the calculation that how much time it is going to take to travel to this first node, second node, third node, fourth node, all of these nodes. Same way, then we find that amongst these 4 nodes, which one has the smallest value to reach to there, so smallest edge, and we realize that the smallest edge is 1 in this case. Then from this 1, we know that we already calculated the distance for 0. 1 is a self node in its own, which means now from 1 we will have to keep track that how much time it takes to reach to node number 4, 2 and 3, and keep all of these results stored somewhere as well, and then try to pick the smallest value that we can. Once again, from the smallest value, repeat the same operation for the remaining elements. So even from this smallest value, we will calculate these two distances. Once again, pick the smallest one, and then from the smallest one, see that what is the remaining value. And for all the remaining values, so for this remaining node, see that currently we should have three results. One result is between node 1 and this one node number 4. Second result is node 2 and node number 4. And third result is node 3 and node number 4. And amongst these three, whichever is the smallest one, pick that one. And that would be our solution. So now let's just try to walk through the whole solution that we just talked about and see that what are all the different concepts we will have to use to complete the solution in a manner that we are proposing. Now, first of all, what we need to do is we will need to make sure that there are no cycles. In order to make sure that, we will have to keep track that all the nodes that we have currently visited. So we can use some data structure like a hash set or an array or a boolean array of size n to keep track of all the values that we have visited so far. So let's say we will use hash set for now for our understanding purposes, but at the same time we are also going to be using array during the implementation. Okay, so let's say that we currently have our hash set that we are going to be storing to make sure that there are no cycles. Next thing is we will have to make sure that for every single node we calculate the distance to all the remaining nodes, find their distance, and we need to sort those distances. So in order to do that, one of the beautiful data structure we have is actually a heap, and we can have a min heap where from every single node that we start iterating over, for all the remaining values we will try to calculate the distance and put them in the min heap, so that it would be stored in like from in a ascending order. So smallest value would be at the beginning that we should be able to find. And how we are going to be storing the value inside the heap would be in this fashion, where the first value is going to be the distance and second value would be the point. So we would say that in order to reach to that particular point, what is the smallest distance that we will have to cover? That's it. That's all we need, because we are only concerned about the cost to reach to that point. So now let's see that first node is 0. In order to reach to 0, and let's say that we decide to start from 0. It's not necessary that we have to start from 0, but let's say that we decide to start from 0. So in order to reach to 0, what is the minimum cost it takes? So minimum cost it takes is still going to be 0. So we are going to be adding the value 0, 0 over here. Next thing is from 0, now we have 4 different options to choose from, that in order to reach to all of these values. So first value is in order to reach to, let's say this one is node number 1, node number 2, node number 3 and node number 4. So in order to reach to node number 1, the smallest distance it's going to take is going to be value number 4, and we will mark it as by 4 1. Same way, if we have to reach to this value number 3, let's say that the distance is going to be 5 plus 2 7. So we can mark the values as 7 and 3. Same way, if we have to reach to this value number 2, then the distance is going to be 13. So we can mark 13 and 2. And next thing is same way, if we have to reach to value number 4, then the distance is going to be 7. So we can still mark 7 and 4. And notice that we are going to be sorting these values because this is a min heap, so it would automatically be sorted. So the value would be something like this one. So 7 and 4, and then I think it was 13 and 2. So these are the currently 4 values that, or 5 values where we have so far. We will pop, and now we have started our iteration. So we will pop the very first element, which means we pop this value 0 0, and we know that the cost to reach to value number 0 is 0. So we will also need to have a variable to store all the cost. So let's say that we have a variable that where we are storing all the cost. In the cost, we first add 0 because that is the cost to reach to value number 0. Let's say we kick out value number 0. The thing is, because we already visited 0, we are also going to be marking 0 inside our hash set. So let's say that this is our hash set and we already visited node number 0. So from now on, any subsequent entries that come in with value number 0, we are simply going to ignore that because we have already visited that inside our hash set. Okay. And let's keep on doing the iteration. Now the next entry inside our heap is node number 1. From node number 1, it takes 4 cost to reach to node number 1. So let's mark the cost to 0 plus 4. We are also going to be marking that 1 has already been visited so far, and we have this channel being established. Okay. Now from from 1 we will have to repeat the same operation, because remember, from every single node what we are trying to do is we are going out in the breadth first search manner, not depth first search manner. So we went to one of the neighbors of 4, and then we are going to be visiting one of the neighbors of 1. Same way we are going to be visiting one of the neighbors of 3, and same way we are going to be visiting one of the neighbors of 4. So this is a BFS traversal, not a DFS traversal. And now let's just mark one, and okay. So now once again we are going to leave all, we are going to be popping these two entries, but these three entries like 7.3, 7.4 and 13.2 is still going to be present inside our heap. Now from this one we have once again three options. First option is this one, the cost of this is 9. Second option is this one, the cost of this one is 3. And the third option is from 1 to 4, so the cost is going to be 2 and 5, so 7. So once again we are going to be having one entry, that is 3 and 3, which is in order to reach to node number 3 we are going to be using distance 3. Next entry is in order to reach to node number 4 the distance is going to be 7. So next entry would be 7.4, so we can also put one more entry over here, 7.4. Okay, and we are going to be having one more entry, that is 9.2. In order to reach to 2 the distance is going to be 9, so we will have one more entry, 9.2 over here, and then the 13.2 would be like succeeded to the back end, and this is going to be the current values inside our min heap. Now once again we are going to be popping out the very first element, that is the smallest element, that is node number 3, and in order to reach to node number 3 we will have to add cost as plus 3. So we will mark plus 3 cost over here. We will mark 3 as being visited because we already visited this one, and we will get rid of this entry. So now you can see that now the moment, let's say that suppose I'm just giving you for an example, suppose we say that this is the next closest node and we will try to extract this one. The moment we see that in order to reach to node number 3 it takes 7 cost, the thing is we already visited 3 inside because it's present inside the hash set, so we can simply ignore this case. And same way we are going to be ignoring all the cases that are going to be like different from the nodes that we have not visited so far. Same way from 3 to 4 we have this type of distance, and that distance to 4 is going to be 4 once again, so we can mark 4 because that is the smallest entry. And from 3 we will have to calculate one more distance, that is 2 up to this 2, and that distance is going to be 10.2. So we can mark one entry over here, that is going to be 10.2. But so once again we are going to be adding cost 4 because we visited node 4. It takes 4 unit of time to reach to node number 4, and we have visited all of these entries. Now the thing is we visited all of these. Now from 4 we will once again calculate the distance to 2. So let's say that this distance is going to be 15, so 15 to 2. So currently these are all the entries we have inside our heap, and let's see that what we need to do. So we already visited 0, 1, 3 and 4. We haven't visited node number 2, so we start popping values out. So we first pop this value 7.4 because we have visited 4, so we can just ignore this one. Same way we can just ignore the 7.4, and then we have this node 9.2. So we pop 9.2 out, 2 we haven't processed, so we are going to be marking the node 2 visited over here and add this cost 9 over here as well. And now you can see that the size of our hash set is exactly same as the size of all the number of points that we are given, which means we have visited all the nodes and we can stop our conclusion. So in order to do this one, the moment we the size of our hash set becomes the number of nodes present, we can stop our calculation, and whatever the cost we found so far we can return that as the answer. So in this case the answer is going to be 20, and this is the whole solution. So I hope it makes sense to you that how did we calculated this. We dealt with lot of concepts that how not to detect cycles. Then we also make sure that we had a hash set to understand that what are the nodes visited so far. We had a heap to find the smallest entry from any particular point, and we were doing all of this while calculating the cost of the minimum spanning tree. So this is a beautiful solution. If we understand the time and space complexity, time complexity is going to be big O of, first of all, let's imagine we will have to do n square work for any single node. Why? Because at this position we will have to calculate distance between all of these 4 points. Same way at this particular location, we will have to calculate the distance between all of these 4 points. So we will have to do big O of n square work to calculate all the distance, and then we will have to find the shortest distance, and shortest distance we are finding by using a heap. So it takes n log n time in order to find the solution from the heap. So overall the time complexity is going to be big O of n square log n. If we see space complexity, because we are storing all the entries inside our heap, it is also going to be big O of n square. So overall this is an expensive time and space complexity, but given the scope of problem, we cannot do anything better than this one. So now let's quickly see the coding solution. So the very first thing we are going to do is to define the total length of given all the points that we currently have. This we are going to be using to check against that whether we have collected all the points or not. Then we are going to be initializing our priority queue, and this is going to be our min heap. Then we are also initializing a new boolean array to store that all the values that we have currently visited so far. So we are marking it as in MST, whether it is present in the minimum spanning tree or not. Then we are defining a new class called point. So let's understand this one. So we have a new class called point, and it only contains two values. First one is a distance and second one is an index. And we can see that we are going to be using this instance of this class to store values inside our min heap, where we are storing that in order to reach to any particular index, what is the distance that it takes, and then heap would sort it out for us. And the very first element we are adding inside the heap is that we are adding the very first value, value located at index position number 0 inside the points, and we are saying that it takes 0 cost to reach to those points, and this is how our priority queue works. We are also having a variable to store the minimum cost that we have been able to find so far, and we have a value called points connected, so which we can use it to compare it against the total given length of points to define that whether we should complete our iteration or not. Then we are running our loop until our points connected reaches to the total number of n that is currently present. Then we are fetching the very first value that we currently have out of the priority queue. So we are doing a poll operation and then checking that whether this point that we found out, this current point, have we already visited that current point. So we can check that using the boolean array that we have created. Then we are checking that if we have not visited, then we are going to be marking it as visited, and we are also going to be updating the minimum cost to reach to all the nodes by the distance that it takes to reach to that particular node, and we are also updating the value of points connected so far. So now we already calculated and visited that particular point, but the thing is we will have to still calculate the distance to all the remaining points from that point. So we are going to be running another for loop that is going to span across every single n that is currently present. First we are checking that any particular index that we are checking, have we already visited or not. If we have already visited then we can ignore. If we have not visited, we will calculate the distance by using the math.absolute points, and then we will add a new entry inside our priority queue by adding that ith location and the distance to reach to that ith location, and it would sort it automatically. In the end, we simply need to return the min cost that has occurred so far to reach or connect all the points, and this is the whole solution. So let's try to run our code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully compared to a lot of other solutions. It's almost 80% faster in terms of time complexity, and also 80% faster in terms of space complexity. So which is pretty great. Once again, the solution is present inside our GitHub repository. So feel free to go ahead and check it out from there. Thank you. So the lead code problem we are going to solve now is called swim in rising water. This one is a hard problem, but a very interesting and intriguing problem. So let's try to understand this. We are given an n cross n integer matrix called grid, where every single value inside the grid represents the elevation or height at that particular point in this I and jth location or any particular cell. Now we are told that the rain starts to fall, and at t times, which means rain is falling, let's say from 1 minute, then 1 minute it keeps on falling, like 2 minutes, 3 minutes, 50 minutes, up all the way up until t times. Then the depth of water everywhere is t, which means rain is proportional to the amount of time that has passed linearly. Now we can swim from any particular square to all the four direction adjacent squares if and only if the elevation of both the squares individually are at most t, which means we can swim from one square to any four directions as long as, let's say that the current t is, let's say, 15. So any particular square that has the value 15 or less in all these four directions, we can swim from this current place. So the amount of t becomes the critical point for us to compare that are we able to traverse in between any two squares or not. Now we need to make sure that we need to reach to the bottom right square where we are starting from the top left square, and we need to make sure that what is the least amount of time we need to wait before we can reach to the bottom right square. So let's try to understand this with an example. The aim is we are given a grid like this. Now our objective is to traverse from this particular node to this particular node. We are being told that at every single moment what is the elevation or what is the height at that particular point. Now the thing is, let's say that we are currently t is equal to 0 point, right, which means and we are currently located at this moment. So the thing is, currently only 0 units of rain has fallen, which means this particular portion is entirely filled up with rainwater. So we are able to swim within this cell. But the thing is, this cell has a height of 2, this cell has a height of 7, and this cell has a height of 4. So we cannot traverse in any four directions right now. Let's say now enough time has passed, and right now currently t is equal to 3, which means we can assume that, let's say, 3 meters of rain has fallen. So if 3 meters has rain has fallen, then this portion would have filled up completely because it only requires 2 meters to fill up. But thing is, all the other squares are still not filled up, and because current t is equal to 3 and we are currently initially located at this very first spot, then we can traverse to this particular spot anytime after t is equal to 2. So at t is equal to 3 we can still travel. When t becomes 4, then at t becomes 4 this portion also gets filled up and we can also swim in this direction as well. So our aim was to reach from this particular square to this particular square, and we can only do that once the t amount of t gets 4. So notice in this case we are avoiding this path going down because this path is more expensive. So our answer in this case would be t is equal to 4. Let's try to take one more slightly complicated example. Our aim is to reach from here to here. Now we notice that there are a bunch of different ways for us to we can go from here to here. We can take as many paths as we want, and actually if we have to calculate mathematically how many paths it's going to take, I think it's going to be n divided by number of ways we can move and factorial of that. So this is going to be a very expensive operation if we have to manually brute force our way to check every single path. But lucky for us, logical thing is that we need to check only for some t positions. So let's say that initially if we are at the position of t is equal to 5, so let's see that where up until what point can we reach if t is equal to 5. We know we can swim from here, no issues with this one. Then we cannot swim into this cell because this is a higher t, but this is a lower t value, so we can go over here. Then nextly from this we can also go over here because this is also lower than 5, but we cannot go anywhere further. So we will have to increase the value of our t to t is equal to 6. Still we cannot go anywhere further. If we do t is equal to 7, then we can traverse up until this point, and notice that at t equal to 7 we can also traverse to this point because this is lesser than the current t value we have. So the minimum amount of t we need to complete all the values is not going to be t is equal to 6, even though this value is 6, it is going to be t is equal to 7. So one more way to explain this is to find a path that traverse from this one to the last, like top left to bottom right corner, and in that path find the minimum like the maximum value of t that is required. So that would be our answer. So now let's try to reverse engineer our way through this one. We already know that, let's say if we are being told that you have this particular example, and for this example you need to make sure that you need to iterate over all the values only and only if for any particular given t. So let's say that we ask you that if the t is equal to 3, are you able to reach to all of these values? So logically what we will do is we will start from here, and then we will see that what are all the cells that has less value than t. So this cell has less value than t, then next this value has less value than t, and then we can say that now we cannot go anywhere further. We can also try to do a backtrack and check for the other possibility, but still we won't be able to do it. So logically we need to do like depth first search or breadth first search in order to find the path we need to take to reach to the end. That is number one fact. The other thing is, after finding the DFS or BFS, we don't know that what should be the optimal value of t in order for us to reach to the very end. So for that there are bunch of different possibility, but one common way that is for sure is that the minimum value of t can be 0. So whatever the smallest value is, so let's say the smallest value is 0. So let's see, the possible values of t can be 0, or t has to be less than the maximum value we currently have. So in this case the maximum value we have is 24, so t has to be somewhere between 0 and 24. That is a given fact, like less than or equal to. Why? Because all the time if t is equal to 24, then we have access to traverse to every single cell in this given entire architecture. So if we can traverse to all the cells, for sure we can find a path that can lead us from top left to the bottom right corner. But so now we found one condition on where the t should be able to move. This is number one thing, that what could be the potential value of the t. Second thing is, we already know how to calculate that for any particular given value of t, are we able to traverse to all the cells and reach to the bottom right corner or not. We can do this in both the ways. We can use a breadth first search, or we can use a depth first search in order to do this one. And it's a pretty common and standard method that logically we are going to be traversing over all the different paths wherever this condition meets up, and the moment we find out that the condition is currently satisfactory, we can actually move to all four directions to find the value we are looking for. So what I'm suggesting is, instead of checking for all the potential values of t, which is going to be pretty expensive operation, why don't we use binary search in order to find the correct value of t that makes sense. So what I'm suggesting is, let's say that for this particular given value, we know that the t has to be somewhere between 0 and 24. So what we can do is, we can treat this 0 as the left pointer, this 24 as the right pointer. Then we will try to find the mid pointer. Mid pointer is going to be 12. So let's see that if we use the t is equal to 12, are we able to reach to this bottom right corner? So we can go down this path, that's for sure. But now after this 5, we cannot go anywhere because this is 16 and this is 21. So 12 does not work, which means the answer of t has to lie somewhere between 12 and 24. So we update, so sorry, not 12, like 13 and 24. So we update our left pointer and right pointer once again. We try to find the mid pointer. So in this case the mid pointer is going to be I think somewhere between 18. So let's see, at 18 are we able to figure out. So yes, we can go down this path. Yeah, for sure at 18 we can take this path, and once again we should be able to complete our answer in this manner. No issues with this one. So yes, 18 works. So once again now we have our left pointer as 13 and right pointer as 18. Once again we will do the binary search. So we will find the middle pointer to be 15. Let's see, at 15 are we able to find the correct value we are looking for? No, right? Because the 16 we would not be able to cross this threshold. So next possible value is going to be 15, and once again 18, sorry, 16 and 18. So the logical step would be 17. 17 would work because we would be able to find out. Then once again from between 16 and 17 we also have to find that are we able to do it. So if we do the mid pointer, once again the value would be 16, and for 16 we should be able to find the answer. So logically we had to do, like, instead of doing 0 to 24 steps, we only did 5 steps to find that value to 16, and that we did it using binary search. So logically in this problem what I'm suggesting is that we use breadth first search or depth first search, whichever one you would like to choose, in order to iterate over all the cells. and we do this with doing the binary search on the different values of t, and the range for t is going to be the smallest element, like 0 less than or equal to t less than or equal to whatever the maximum element we have inside our grid, and somewhere between that we will try to find the value of t. So this solution would work perfectly fine. If we have to calculate time and space complexity in this case, the BFS or DFS would take big O of n square work, because we have n cross n grids and for one iteration, and we will have to do this log n time because we are trying to find different values of t. So it's going to be n square log n in terms of time complexity. In terms of space complexity, depends on how you implement your breadth first search or depth first search. If you are using recursion and if you are using like a stack, recursive stack to store those values, then it might take big O of n square space as well. So just be mindful of that. Now let's quickly see the coding solution for this one. So the very first thing we are going to do is we are going to mark the value of n. Then we are going to initialize our left pointer and right pointer. This is going to be the cell locations. And then we are checking that while our left pointer is less than right pointer, we are going to find the mid pointer that we will have to iterate over. And on top of it, we are also going to check, or we are going to call our helper method call swim, can swim, and which checks that for any particular given grid, depending on the mid pointer, are we able to reach. If we can, then we shift our right pointer to the mid pointer. If we cannot, then we update our left pointer to go right +1. So this is our binary search method. Now let's understand our can swim method. So in the can swim, we have the given grid as the input and the different values of t we are working with. On top of it, we are checking that first of all, what is the length of the given grid. We are also having a visited boolean hash set that defines that these are the cells we have visited so far, because we don't want to be stuck inside the infinite loop in breadth first search or depth first search. And we are going to call our DFS method in this case, where we are passing in the grid, the nodes that we have currently visited, the I and jth location, and we are also passing in the different values of t. Now this is going to be our recursive DFS method, where first thing we are checking is that what is the given length of n. Then we are checking for the scenarios that if we are going out of bounds, so these four conditions are for going out of bounds, or we have already visited that node, or we notice that the location of the grid position is greater than the current t value, then we can return false, that we cannot go to that particular cell. If that is not the case, and we check that the current ith and jth position is at the bottom right, then we can simply return true, saying that yes, we are able to reach to bottom right corner. If that is not the case, then we mark the current node as visited, and then we call the DFS method in all four directions, and once again recursively repeat the same process. So this is the coding solution. So basically, after this recursive process ends, we should either receive true or false for any particular t value. And inside our main method, we are trying out bunch of different t values and making these various calls. So this is the whole solution. Now let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code beats almost 98% of all the other solutions, which is like one of the fastest solutions for this particular hard problem. So I hope you find it useful. Once again, the solution is present on our GitHub repository, so feel free to go ahead and check it out from there. Thank you. Hello friends, hope you are having a fantastic day today. So now we are going to solve an awesome LeetCode problem that has tons of practical use cases. We are going to solve a problem called cheapest flight within K stops, and all the travel companies and airlines uses the logic we are going to solve in this problem. So this is a really important and informative problem with a lot of useful properties. So basically, in the problem statement, we are given n cities that are connected by some flights, and we are given an array called flights where we have three values. We have the source city, we have the destination city, and we have the price it takes to get from like the source city to the destination city, and we are given bunch of entries like this. Now we are also given three additional integer called source, destination, and K. That defines that we want our travel to start from the source city, end at the destination city, and K is the maximum number of stops we are allowing ourselves to take. And our aim is to find the cheapest tickets that we can find within the constraint of given K stops from source to destination. And if we can find the cheapest ticket, that's great. We need to return that value. If we cannot find any tickets, then we need to return -1. So let's try to understand this problem with a real life example. So here I have given bunch of different values inside our flights array, and we also have three different values called source, destination, and K. Now we can see that every single entry inside this array contains three values, and we all know that this defines the source city, the destination city, and the price it takes to reach to that particular destination city. We are also being told that we are planning our journey from source city 0 and destination city 3. Now this 0 and 3 can be replaced by any real life values like New York and Paris, France, New Delhi, you name it. And we are saying that we want to take at most one stops, nothing more than that. And now let's try to see that what is the amount or what should be the answer in this case. So I have drawn the whole information that we have provided in this flights array in this beautiful graph like description. And now we can see that we are starting our travel from city number 0, and we need to reach to destination number 3. Now we can see that one route is that we go from 0 to 1, and then once we reach to stop number 1, this would be our first stop. And then from 1 we have to go to 3 because we are only allowing ourselves to only take just one stop. Now from 0 there are no other stops that we can take in order to reach to 3. So this is the only path that we are allowed to take within the given constraint, and the cost to reach to city number 3 in this case is going to be 100 plus 600, so in total 700, and this is what we need to return as the answer. Now say for an example, in the same scenario, instead of K being 1, if we are given the value K being 2 as allowed to be given. Now in this case, let's see the scenario. First stop we can take is that from 0 we can reach to city number 1. This is going to be our first path. Now from the city number 1 we have two options. One option is that we reach to city number 3. That gives us the answer that we can reach to the destination within $700. But the other option is that since we are allowed K to be 2, we can take one more intermediate city as a stop, and we decide to take a stop at city number 2. Now in order to reach to city number 2, it takes $100 plus $100, so $200 to reach to city number 2. And from city number 2 we also have a direct connection to city number 3, and that is also going to be adding the cost of 200. So it takes 200 to reach to city number 2 and plus 200 more to reach to city number 3, so in total it's going to be 400. So in this case the cheapest flight would be 400 that we can return as part of the answer if we are given our K to be 2. So this is what we need to return in this example. Now the first logic that comes to our mind is a very simple brute force approach, where logic is going to be quite straightforward, that we go through every single possibility of all the nodes that we can visit and all the edges that we can visit, and then try to see that what is going to be the cheapest price to reach to the city number 3. In order to do that, we can actually use the graph based representation of this given input flights array, and after converting it into the graph we can actually do like breadth first search or depth first search from any particular node for all the other subsequent nodes. So we are iterating over all the possible edges and recording the values. We can also use backtracking, recursion, you name it, in order to solve this problem. The thing is, uh, that solution would be okay in terms of like coming up with just a solution to have, but the thing is, think of the real life scenario. We are dealing with hundreds or millions of cities, flights, and costs. So that's not a scalable solution. We need to find a better approach, and that's where a beautiful solution or algorithm that comes into the picture, and that is called Bellman-Ford algorithm. So now let's see that how can we utilize this algorithm to solve this problem. So once again, we are going to be using the same example to solve this problem using the Bellman-Ford algorithm. the logic is quite straightforward. We are actually going to be focusing on the only thing that for every single k iteration, how much time it takes to reach to any particular destination city and what is the cost associated with that. And in the end, for all the given k entries, we will keep on running the same process until we reach to the end that we are looking for. And then if we found any particular cost for the associated destination city, in this case we have value number 3, then we can return that. If that is not the case, then we can return -1. So let's try to understand the logic I'm suggesting to solve this problem. For that, we are actually going to be using some sort of placeholder values where we can store that how much time it took or how much money it took to reach to any particular destination city. For that, number one thing we need is to have an array called cost that defines that in order to reach to any particular destination city, what is the cost associated with this. Now the second layer of complexity in this case is value of k, because notice that in our one of the examples we saw, if we only have to make one stop, then we come up with the different cost. But if we are allowed to use two stops, then we are able to come up with a different stop or different cost. So once again, we are going to be using the same logic. And in order to justify the value of k, if we, in order apart from using this one, we will also have to use a temporary array for every single value of k. So now let's try to understand the logic I'm suggesting. Currently I have defined an array called cost, and we are going to be seeing that in order to reach to any particular destination city, what is the cost associated with this one. This is the number one thing. And second one is this temporary array would be reset for every single k value. And once we calculate that how much time and effort and money it took to reach to any particular destination city around any of the k iteration, then we are going to be copying this temporary array to this cost array and repeat the same process for the upcoming subsequent k values. Now in this case, let's say that for first we are going to be calculating that what would be the logic for k is equal to 1. Then we will see that what would be the logic for k is equal to 2. Okay, so let's stay with me. This is going to be pretty interesting to understand and learn the whole process. Now we don't know that how we can define that whether we have a city cost associated that is cheaper or not. In order to do that, what I'm suggesting is that initially I put the cost to the maximum value possible, and after putting the cost to the maximum value possible, whenever we find some value that is smaller than the current value, then we update that value, because it is in our benefit to update the cost it takes to reach to that destination city. And now let's start our process. Now we know our source city is 0, so by default, logically, in order to reach to city number 0, the cost has to be 0 because we are already there, that is our source city. So we are going to be checking first of all updating that value inside our array. So for city number 0, currently it takes maximum value to reach to that particular city, but we are going to be defining it as 0. Okay, and now we are starting our process. So we are going to go through edge by edge for every single array. We are going to be updating the temporary value for that kth element, and then temporary array is going to be flipped over to the cost, and then we are going to repeat the same process. So currently for the temporary array, we are going to take a copy from the cost for this first iteration. So this is 0 and all of these are max in order to reach to any particular city. Now first thing is that in order to reach to city number 1, it takes us $100. So we are going to be updating that information, that in order to reach to city number 1, it takes $100. But the thing is, first we are going to check that the source city that we are traveling from, that already has some value and it is not the maximum value. Because if any particular city has the maximum value, that means that that city is not reachable. So if the source city is not reachable, how can we reach the destination city from that source city? Now in this case, source is 0 and destination is 1 and the price is 100. So we already know that we can reach to the source city because this value is 0 inside the current array. So then we are going to be updating this one as 100 because it takes $100 to reach to that particular city. Next thing is, in order to reach to city number 2, it takes $100 from city number 1. But the thing is, in our original cost array, we cannot reach to city number 1. So once again, for this one, we should not be able to reach to city number 2 as well, because city number 1 is not reachable. So notice this is going to be for k is equal to 1, only one city. So we can only make one stop, so that is this stop. And if we, so that's it. So now next thing is, in order to reach to city number 0, the cost is 100 from source city 2. Once again, for 2 source city 2, we cannot reach inside the cost array, so we cannot update any value. And also in this case, this would not be updated, because currently in order to reach to city number 0, the cost we have is 0 and this is 100. So why would we pay higher money if we already have a lower value? So this would not be used. Next value is, in order to reach to city number 3, it takes $600. The thing is, we cannot reach to city number 1. So currently, and notice that currently we are iterating over k is equal to 0 and we have maximum value of k is equal to 1. So we are going to be running this iteration twice. So currently for k is equal to 0, this one is from 1 to 3, it takes $600. But the thing is, we cannot reach 1, so we cannot reach 3. Once again, next iteration, we cannot reach any other city, because 2 to 3 is 200, but we cannot reach 2, so we cannot reach 3. So these are also going to be blank. Now notice that after the first iteration, we only traveled one city, that was the immediate neighbor of this node number 0. And this is the whole point of this exercise, that every iteration we are going in like breadth manner for all the cities that we can iterate over, and we are updating the cost accordingly. Now for the next k iteration, we also need to update the value of this temporary value inside our current cost array. So first we will update this one. So this is going to be 0, 100, and then these two are going to be max value and max value. And once again, we are going to be starting with a blank temporary array, but we are going to take the copy of this cost array. So this is also going to be 0, 100, and then max value and max value. Now let's see the same iteration again. Now 0 to 1, 100, we already have this value stored, so we don't need to update. 1 to 2, 100. Now in this case, we are able to reach to city number 1 with 100 cost. So in order to reach to city number 2, the cost has to be 200. So we can update this value to be 200. And notice that this time we are iterating over for k is equal to 1. We initially started for k is equal to 0, and now we are going to keep on repeating the same process. Now next thing is 2 to 0, it takes 100, but we don't need to update that, because in order to reach to 0, we already have the value as 0. Next one is 1 to 3 as 600. Currently, in order to reach to 1, we have the value 100. So we can reach to city number 3, and 1 to 3 is going to be 700. So we are going to updating the value as 700. And now next thing is 2 to 3 is 200, but we cannot reach 2 in this case, because cost array is still showing 2 as maximum value, so we are not able to reach this one, so we are not going to be considering this edge. And next thing is, next would be the k is equal to 2, but the thing is, notice we only have k is equal to 1 as max. So the moment we are done with this one, we will break out of all the loops. And sorry, before this one, we are actually going to updating the temporary array to the cost array as well. So now inside our cost array, we will have a couple of more entries. So in order to reach to city number 2, it's going to be 200, and in order to reach to city number 3, it's going to be 700. Now after this one, once we end our loop, we are going to be checking our cost array. We are going to be seeing that if the destination city is 3, and if this value is not maximum, then whatever value is, we need to return this one. So our answer is going to be 700. And if we cannot return 700, like if the value would have been maximum, then we would have returned -1. Now let's take one more example for k is equal to 2, just to solidify your understanding. Once again, 0 to 1, 100, we already have updated this value. 1 to 2, 100, we also have updated this value as 200. 2 to 0 as 100, we don't need to update this one, because we have 0 as 0. 1 to 3 is 600, so this has also been updated. And next value is 2 to 3 is 200. So this value, we can see that we are able to reach to city number 2. That means we can reach to city number 3. The cost is going to be 200 plus 200, 400, but the current maximum cost to reach to that particular city is 700. So we need to remove 700 with 400, because now we can reach to city number 3 with 400 cost. And now, since this is k is equal to 2, once we are done with our loop, we will update this value over here. So this becomes 400, and then in the end, if we have to return the answer, we can return 400. That after, with k is equal to 2 stops, we can reach to city number 3 in 200 cost. So imagine, see how beautiful this solution is. And now I hope you understood that what we are trying to do over here. If we have to calculate the time and space complexity, it's quite obvious that for k times we will have to iterate over all the given edges that we currently have and all the given nodes that we currently have. So it's going to be k multiplied by the number of nodes and edges, so O multiplied by V. uh, so yeah, and this would be the time complexity. And if we see space complexity, we are using couple of arrays to store the values. This is going to be the temporary storage and this is going to be the constant storage, but both are dependent on the number of cities. So let's say if the number of cities are the number of nodes, so it's going to be big O of n, where n defines the number of nodes. And this is the whole solution. Now let's quickly see the coding solution for this one. So the coding solution is actually quite straightforward. First, we are going to initialize our cost array. Then we are going to be filling the cost array with the maximum value possible. Then we are going to define that in order to reach to source city, it takes us 0 amount. So we are going to mark it as 0. And then we are going to initialize our two loops. First loop is only going to run from 0 to k value, where we are going to be starting a temporary array, where that is going to be the clone of our cost array that we have created so far. Next, we are going to be iterating over every single edge. Now for this edge, first thing we are going to be doing is defining the value of u, v, and the cost to reach to that particular city, where u is the source city, v is the destination city, and cost defines that how much money it takes to reach to the destination city. The values are extracted from our flights input array. Next, first thing we are checking is that in the original cost array, if in order to reach to city u, that is the source city, is maximum value, that means we cannot reach source city in that kth iteration. So we need to continue that operation. If that is not the case and we are able to reach to the source city, then we are checking that in order to reach to the destination city v, what is the current cost we have. And if the current cost is actually greater than the cost we are able to achieve using the cost it takes to reach to city u plus the current cost for the based on the current edge, whichever is the smaller, we are going to be keeping that value inside our temporary array. And once we are done iterating over all the flights for that kth iteration, we are going to be copying the temporary array inside our cost array and repeat the same process for the next kth iteration. In the end, the answer is quite straightforward. We simply need to check that if the cost to reach to that particular destination city, if that is the maximum value possible, then we need to return -1. If that is not the case, whatever the cost value is, we can simply return this one. And this is the whole solution. Look how beautiful it looks. Now let's try to run the solution. Seems like it's working as expected. Let's submit this code. And our code runs beautiful. It beats almost 97% of all the users, which is pretty awesome. And I would be posting this solution inside our GitHub repository. So if you want, you can go ahead and check it out from there. Thank you.